I'd like to introduce our first speaker. It's Bob Menrad, to welcome you to our very first DTN Industry Day. Mr. Menrad is the Associate Director of Flight Projects for the Exploration and Space Communication Projects Division at NASA's Goddard Space Flight Center. Bob leads his team of communications and navigation experts with incredible enthusiasm and passion for advancing NASA's commercialization efforts to shape the future of our space community at large. We're thrilled to have him here with us today. Bob, over to you.
Thank you. Good morning, everybody. Good morning, everybody. Yeah, at least you didn't say teacher or something like that, right? So it's great to see all of you here in person, and welcome to those on the net. Wendy, thank you very much for that very kind introduction. You're hired. You're going to do all my intros from this point forward, okay? So let me take a second here and on behalf of Center Director Dennis Andrusik and the entire leadership team at Goddard, welcome you all to this Industry Day. We are thrilled to have you here, okay? And in preparation for greeting you this morning, I asked Dave Israel to provide me a list of the industry partners who were participating. What an impressive list. And having worked in industry for 5 years before I became a civil servant, I was going down that list, and there were some names that I recognized, and there were some names that were new. There were some names I thought to myself, ooh, when did they fall off? And then I wondered, as we go deeper into the era of commercialization, where together the government and the marketplace work together to advance our nation's goals, I wondered for a moment what new companies might join the list in the future. And in the midst of all that change, it dawned on me. In the midst of all of the change, there has been a constant when it comes to DTN and what it is that we seek to achieve. This center, Goddard Space Flight Center. Almost 30 years ago, we connected the South Pole with the internet through TDRS. STS-107, we actually did demonstrations of internetworking. So in the past, we were with you. Today, with the PACE mission as an example, and the vision of Dr. Chris Scalise when he was Center Director to formally issue the derived requirement that there will be DTN, not just on the PACE mission, but woven into the fabric of the software that we call the core flight software, that it would be available for all future missions that Goddard fields. We are with you today. And with the leadership we are exhibiting, with the commercialization, services procurement, the LunaNet interoperability specification, whether it be industry within our nation, whether it be other government agencies, whether it's other international partners, we, Goddard Space Flight Center, will be with you tomorrow. So in an environment of change, take solace in one very important fact, that there is a constant you can depend on, and you're actually at that center right now. So again, on behalf of Dennis Andrusik and everybody, welcome to this Industry Day. I, for one, will not be able to stay, and for that I apologize. But I do share with you what my expectation is of Dave, and that gets extended to all of you, is that while I welcome hearing the discussions that you had, it's more important that I hear what the results are in the definition of go-forward plans to realize what the true potential of things like the bundle protocol, the DTN standard offer to us all. Okay? And on behalf of everybody else, I will pass the mic over to, I think Philip is next, or Wendy, to you. All right, so then let me take a second here. And you must have good words for him, just like you did for me. Maybe. Okay. Thanks, everybody. Welcome again. Have a great Industry Day.
Okay, thanks, Bob. Next, I would like to ask Philip Baldwin to come up. He's joining us from the Space Communication and Navigation Program at NASA headquarters. He is the Network Services Division Operations Manager and is also currently serving in the role of Director of SCAN's Commercial Communications Services Division. He has been working in some capacity with DTN since 2010 and continues his advocacy for DTN to this day. Okay.
Thanks, Wendy. I was excited to hear what kind of intro I was going to get because sometimes I change my hats and I'm not sure what I'm doing. So it's good to know, okay, that's what I'm working on. So Bob really gave a great intro about our excitement to have industry here, our excitement to collaborate and actually move forward. And SCAN, we're doing a lot about commercialization, our communications and navigations programs that we have. So I'm just going to give a little overview of SCAN, just to explain what SCAN is, and go to the next slide, please. And so SCAN serves as the program that's responsible for all of NASA space communications, supporting over 40 missions, actually over 100 missions, 40 on DSN and 60 or so in the space relay and the near space network. And so it's really a core program that enables human space exploration, enables science, really lets us explore beyond, from the moon to Mars. We're really there from the beginning to the end, supporting all the great achievements that NASA can achieve. So a couple of things I wanted to mention on this slide. I'm not going to spend too much time because I want to buy some time for later to have a great discussion. Is that we also cover the spectrum. We cover the formulation of missions, helping them design their spacecraft. We work to negotiate with international partners on communications as well. We support other agencies like ESA, JAXA, and others to ensure that they too can achieve their deep space and human space exploration goals. And so with that, we'll go to the next slide. So I just want to give a little view of what we have in our networks. We have the deep space network, the near space network, which is comprised of two elements, which is the TDRS spacecraft. That's our geosynchronous spacecraft that support relay. We also have our ground network, which right now for an airspace network, the ground network includes both commercial. Already we have commercial partners and we have some government-owned assets as well. Of course, we are expanding that. So pretty soon there'll be RFP that's going to expand that use of commercialization. And that's a goal that we have in the past few years of more commercial. The industry has what we need. We can leverage it. And that's our goal, to leverage what industry is working on and what they can offer to us. And so we're working hard to integrate more commercial partners into our networks, which is why today we have the DTN Industry Day. It's a great idea to see how we can leverage what the industry is doing for DTN and also collaborate. And so next slide, please. And so commercialization is underway. We are moving forward. As Bob mentioned before, we have kind of two paths we're taking right now. One is looking at what the industry has for the direct-to-earth, the ground networks. And the other path we're looking at is relay. And so for the ground network part of it, we're looking for the ground stations. That's happening here at Goddard with the RFP I just mentioned. But at Glenn Research Center, we also have another project called the Communication Services Project that is looking at how we can leverage the existing market that exists for relay services. And so we did a Funded Space Act agreement with 6 companies, and they're going to support demonstrations to see how maybe with a little bit of modifications to existing communication satellites, we can use those systems to support NASA objectives. And so it's exciting to see this move. It's a little different than how we've done business in the past. So we're changing our thinking, we're changing our perception, changing the way we want to do business. And so it's exciting to see that. We're making a lot of progress, and that's going to extend out into the moon. You know, we're right now focused on the LEO commercialization effort, but we're also extending that to the moon. If you go to the next slide, and we can see how busy this slide is going to be, how a lot going on. There's a lot going on in the moon. There's going to be a lot of elements. We have the CLIPS landers. We have the human landing system. We're going to have the gateway. A lot of activities in the moon. And so when you look at this diagram here, this directly is going to apply to DTN. How are we going to communicate with all these elements? How are we going to allow this? We'll have delays. We're going to have disruption. That's just inevitable. That's going to happen. So how do we make this work? You know, we talked about internet in space. networking, interoperability, all that is going to be covered by this this DTN project, and how all these elements, because again, unlike Apollo, we're not looking for doing it by ourselves. We're not looking at to just be a NASA system. In this picture here, this is going to be a mixture of commercial assets. Even when we talk about the lunar relay, or a lunar relay we want to have around the moon there, we want to have a commercial lunar relay. And the best way to have interoperability and connectivity, we're hoping DTN is going to solve that for us. To have that interoperability, to have that connectivity, to have that ability to not worry about what's in the middle, not worry about how an astronaut can just get data on their tablet when they're walking, they're in the EVA and they're walking out and they're looking at their tablet and they want to send a message back to the ground station or back to MCC in Houston. That should all be behind the scenes. And that's why a lot of times you hear us call ourselves an invisible network. Because a lot of times, nobody knows how it got there, it just happened. You pull out your cell phone right now, you send a text message, it gets to the person you attended, your loved one. Yeah, you're not really thinking about how it got there. You're not thinking about, okay, well, it must have went to this tower. Yeah, that tower's over there. So, okay, then it must have went to another tower over there. Yeah, okay, it's working, it's working. No, don't worry about that. You send the message and it gets to the endpoint. That's what we want to see on the moon. That's what we want to see even in the LEO domain, that we can send messages and we don't worry about how it gets there. It gets there. Us here, of course, we will worry about it because we're the engineers designing it, but the end user will have that seamless use of getting data to where it needs to go. So we are very excited to have Industry Day today. This is our first time doing it. So I'll call it a first annual. We should probably name this a first annual DTN Industry Day, because I am sure we're going to have another one. And we want to invite you all back, and looking forward to hearing some great presentations and great discussions. And so at that, I'm going to turn it back to Wendy, unless there are any quick questions. I think I have like 2 minutes maybe. But if not, I am happy to move on. Great.
Thanks, Philip. I would like to introduce Dave Israel next. He's the architect for Goddard's Exploration and Space Communications Project Division. Short intro.
Okay, thanks, Wendy. I guess to give the introduction, I realized I can sort of mark time based on hair styling. So when Bob mentioned all those space internetworking stuff, I could say when I started the space internetworking work on those projects that Bob mentioned, I was known as like the long-haired guy. and then I can also say that the beard is a measure of how long it's been since the last time we were together in person. So I'm going to talk specifically about some more details about the near space network and what we're doing, and that's the procurement, this RFP that's out. And then also about LunaNet, which is what we're calling the network that Philip mentioned. So if we go to the next slide, please. Okay, so now within NASA, we are organized under SCAN that there's two networks, organized as two networks. So there's the deep space network that's managed out of JPL, and those are the large antennas at their 3 locations. And then we have now what we call the near space network, and the definition of the boundary between near space and deep space is 2 million kilometers. So there's a picture coming up that we'll kind of show you where that is geographically. One thing though that's important to understand about what we're doing, and with the audience for today, I think people will comprehend this better than in some other audiences, but one of the main things that we're doing with the near space network is you see how underneath of the near space network, we have government space link providers, we're calling them, and then commercial space link providers. And really what we're doing is putting together where we're evolving the near space network is evolving more and more to be like a virtual network in mobile phones. It would be like a virtual mobile network operator, right? So that we're looking in the procurement, it's essentially things like to bring in service providers I've seen the things being called now like ground station as a service or relay spacecraft as a service type of thing. So the near space network role will be more and more about service orchestration and providing that top level network provider view to our users, so that the users would have, for example, like a single SLA with the near space network. It would be the near space network's responsibility to fulfill all those services, but those services will actually be provided by, we'll see through the RFPs by commercial providers, and really our direction is to use commercial providers everywhere that they're available and that we can is really the direction that we're going under. We do understand that there's certain things that there won't be a commercial market enough yet for there to be commercial providers, or it's new technology or special cases where they're just there's no reason for the commercial, there's not enough of a market there where anybody would ever do it. So we'll still have some government assets, and there might be other cases, other requirements where we would still want to have some government assets. So that NSN RFP, that the draft is out, but the actual RFP will be coming out soon, and you'll see that is for us to procure the services from service providers, right? And that's what we're looking for. So if you go to the next slide, please. So again, just the definition of the region. So that 2 million kilometer mark, it really takes you out to cover the Sun-Earth Lagrange points L1 and L2, where that's where missions, science missions that want to study the sun. Then L1 was worked out to be a great location, and things like JWST that want to do sort of astronomy and astrophysics. Then L2 is really a great location. And then you see that the moon is in that region. And so historically, because of the size of the antennas, and we have been using the deep space network as what provides the primary services now, like for JWST, and there's other missions within the near space area that are supported by the deep space network. So don't let the names sort of throw you off. But what we're looking to do again with this procurement is to build up capacity, ground station capacity to support this full volume, because we really need to use those deep space network antennas for going to Mars and the interplanetary missions where we really want to support, where you need those large apertures for it. So we go to the next slide, please. Okay, so again, for this audience, I think you'll follow it when I say that if you look at this picture where it looks like everything is specifically connected and everything is going through the near space network, don't take that literally, for data paths. I should mention that this building, if you went down this hallway and turned left, there's a room there that maybe they finally cleared it out, but for a long time you could look through the window and it was a huge bank of patch panels, and those were the actual patch panels from the Apollo missions and the old ground network, where all of the data from all the stations was manually patched to connect it through. So that was the way things used to be, and we're done here. But this is a virtual representation of that, right? But it's the idea that I described, where from what it's trying to show is that from the user point of view, there's a single service provider for them, and that's the near space network. But the reality is that those services are being provided by either NASA assets or commercial assets. And then we're also expanding to understand how we can have peer network providers that we also exchange services with, such as like ESA or other government agencies. One thing, though, is that in order for this model to really be successful, the whole assumption is that these commercial providers are going to be supporting users other than our missions. That's the whole point, right? Like we want their interface to, when they're providing support to the near space network, to be just part of the larger set of the missions that they're supporting, because that's really the only way that they're going to have a business that closes, or they're just going to be charging us, $1 million a minute or something. It just won't be practical. So, but if you look at things that are happening to support LEO users, for example, then the provider field is very wide, and now we're going to do the procurement. We're going to see what's available for lunar and out to the 2 million kilometers. So we go to the next spot. So again, I included this slide for this audience, but I don't want to spend too much time on it. But I just wanted to point out that again, it's a virtual network. We do think in a lot of cases than just to connect the users and security purposes and things, that there might be a point of presence, some demarcation where a service provider would have an interface to a near space network system, and then we would have the interface back to the user. Though again, that picture should not be interpreted as there being a physical box that's being brought to people's ground stations in order to do that demarcation point. It'll have to be engineered and worked out. What can be done in the cloud? How do we have the secure boundaries? But this is the idea. And then the service interface. So traditionally now, all the NASA missions are really just receiving at like frame level service, right? Like a lot of it is you're delivering AOS frames and space link frames. So that'll continue to be the types of services that we're providing. But where this model, what's made this type of model really successful terrestrially is the fact that you have a network, and you have network data units that allows you to do all of the routing and things. So so if we flip to the next slide, I guess if there's any questions on the near space network thing, I can probably have time to field one question. Otherwise, I'll get into LunaNet. And I'll be around during the day today if anybody has questions that are related to the RFP. I won't be able to answer. You can ask them, but I won't answer them. Okay. Philip alluded to this artist concept picture that I commissioned when we produced the first LunaNet study going back a few years now, and various. Most people like this picture. Of course, the NASA engineers that see this picture say there's no way that they're going to have a tablet and they can use it with their gloves and I'd be like, yes, I know that, but that's that's not the point, right? The point that we were trying to make with this picture is that we all go about our daily lives now. If you think about your exploration ops concept, for those of you that are here from out of town, right? You show up, you have your phone, you connect to the network, you get GPS, you put in where you want to go, you get the directions, it takes you where you want to go. If you want to figure out where good food is, you pull out your phone and you can work that all out. And what's happening is that you have a device. And you have the capability, there's infrastructure there that's giving you position, navigation, and timing signals. And then you also have a network connection. And then, and now we've got to the point where we just sort of assume that if we can just connect to the network, then we have all these apps and all these things that will just work, and we'll be able to connect to anything that we want to connect to. And it's also at the point where, unless it's not working, you really don't keep track of how you're connected, right? When you have your phone that can go through Wi-Fi or go through, cellular service, then as long as you're getting your data, you don't bother to look how you're getting your network connection. And you certainly don't keep track of like which cell tower you're connected to when you're driving around, right? You just connect to the network, and then the network is there. So go to the next slide, please. So in order to take this, that graphic in the beginning, and then pull back and say like, what are the basic services that would need to provide? So we identified 4 services, and the original report, it was all done with these pictures, these generic circles, because I was trying to emphasize the idea that that the circle could be a large satellite, or it could be a small sat, or it could be something on the surface, or it could be all sorts of variety of things, and then the links could be optical or RF, and any variety. So I wanted something very generic to make the point. But there are 4 types of services. And then you see these service interfaces, and of course the services can all be supported over the same physical interface. But these are the 4 service interfaces. So there's the communication services, which is where DTN fits in, and you'll see the mention of call it non-real-time data services. But the positioning, navigation, and timing. There is the possibility to use the Earth GNSS and GPS signals when at the moon, but not to a level that it will give us the performance that we want at the moon. So we need to do something in the infrastructure for that. The way to think of detection and information services would be, again, if I don't think it's going to happen to people this week when you're here, but if you were out and there was a tornado warning and you get that message on your phone that says, like a tornado warning, that the equivalent of that is what we have in mind, but it would be like a solar weather event, or one day on Mars maybe is a dust storm, or some other sort of alert messages that go out. And there might be other information that's important to exchange and have a channel and a mechanism to do that. And then the last category of the science services is something that is done sometimes where the signals themselves and the telemetry of the signal performance itself, the scientists can actually work out science about it. You can take ranging of a bunch of crosslinks and understand the gravity model of the moon better, for example, or when there's atmosphere and you can measure the attenuation as something goes through the atmosphere and learn and understand things about the atmosphere. So that's what the science service is about. So another thing, and this is important going back to that procurement, is that there's no requirement or expectation that every node provides all of these services or provides, like the same quality or performance characteristics of all those services, right? There could be, if you look at, if we call it EarthNet, then we have a constellation of GPS satellites that their primary function is the PNT part. So that would be like one of these balls with just really the PNT function. So again, the idea with LunaNet is that we have these nodes provided by different entities, operated by different entities of all various shapes and sizes, but together they provide the infrastructure that the lunar users are going to need. So go to the next slide, please. Okay, so there's a document called the LunaNet interoperability specification, and the baseline version, which is Rev 4, but this is the baseline version to accompany the RFP, and that just came out earlier this week, and I can put in the chat the link to it. Everybody interested in DTN will be happy to see the mention of bundle protocol version 7 and the description of how that is used to connect. If you're connecting to the LunaNet and you want to make sure that you can exchange data with anybody else connected on the LunaNet, then your application should really be a bundle protocol based application, right? There are situations where if you're in the hab and the hab has Wi-Fi and you want to use an IP application between things, then that's there's no problem with that. So there's 3 types of communication services defined. So there's the real time, there's the store and forward, which is where the DTN primarily fits in. It's understood that DTN can be real time if everything is all connected, but they're separated out. And then there's this messaging service, which I don't want to get into today, but the messaging service, one way to think about it is something to carry like those space weather alerts and control sort of messages, and the reason why you see these two simplified stack pictures is that the one on the right, where I refer to it as LunaNet applications, those are really applications where the conversation, if you will be between something that's between the infrastructure, the network, and an end user. So exchanging schedule requests in the response to the schedule, or space weather alerts, or PNT messages like I measured your Doppler and here's what it was, and those are the sorts of things that the goal is to have messaging service that carries that traffic. So you see the bundle protocol and IP both listed in this picture. Go to the next slide. Okay, so there's a document, and you see the link there, but this is an example that's in it, and the goal of this picture is again to help people to understand. A lot of times there's lots of questions about traditionally, there was a period of time when there was a battle going on between, IP versus DTN and bundle protocol and things. So, really, it's the using the right networking layer at the right time. Think of bundle protocol as that overlay that gives you that full end-to-end network. But you can have portions like what's trying to be illustrated with the cloud picture in the lower right, where you see that it's a BP network, but I was trying to illustrate that there's portions of that network that are sort of IP, and the bundles flow over IP until you get to maybe to get through the middle. Then there's other convergence layers and things that have to move it across. So what this illustration and the description in the document is trying to show is if you have a rover and a lander on the moon, and you just are talking directly between the rover and the lander, and that's as far as the data is going to go, and especially if it's like a remotely controlled rover that somebody inside of the lander is driving, then an IP-based application will work in that scenario. But the point is that if you're trying to take bulk science or science measurements and transfer them back down to Earth and have them collect at a science operations center, or share it with somebody else somewhere else on the moon, then that's where the use of bundle protocol is really where that application should be looking to get that end-to-end data delivery. So next slide. Okay, and I'm pretty sure this is the last slide or close to it. So this is I have to switch out. I didn't know that Philip had the new version of like all this stuff happening at the moon. So again, if you look at this picture and you see all the variations of nodes and the shapes and sizes, and again, the DTN is a very important element of that to really make the network a network. So I'm very excited to see all the commercial participation. It's very important for the users, the potential users, to see that there's hardware and software available for them to use, that the infrastructure really can be built and put into place to give the network capabilities that we've been discussing. So there was we flew a laser communications demonstration, LLCD, on the LADI mission, the Lunar Laser Communications Demonstration. And once that mission was flying and showed that it could do the laser links to and from the moon, then I put a DTN experiment together. We didn't upload bundle protocol onto the spacecraft or anything, but we demonstrated a scenario where there were, can't remember if it was 3 or 4 users on the surface of the moon, and used the actual location of the LADI spacecraft to determine the start and stop times of events, and demonstrated what it would be like to use DTN as a store and forward mechanism to get data from. I had the dark side of the moon and the monolith at I forget where exactly the monolith is located, but I looked it up, of course, on the internet. You can find out the exact location of the monolith. So now, I'm excited to see that we're on the verge of actually implementing this. And again, it's the scope of this is much bigger than NASA can do on its own, and all the participation from industry is really great to see. So I believe that's my last slide. To go to the next. No, that's it. Okay, thank you. All
right. Thank you, Dave. We're slightly ahead of schedule, so first I want to make sure Oscar Garcia is online. I think you can check. Thank you. And I think we're about 20 minutes ahead of, or 17 minutes ahead of schedule. Oscar, if you're online, you're muted. Oh, there you go. Okay. So our next, hi, Oscar.
We have.
So I'll
hello.
Give you a quick introduction.
Yes, we changed a bit the schedule.
Yes, we're 20 minutes ahead of schedule. Are you able to present right now?
Yes, absolutely.
Okay.
If you have.
Perfect. So
is my webcam available? Can you see?
Yes, we can see you and we can hear you.
Okay, perfect. Hello. Hello to the audience.
So our next speaker comes from the InterPlanetary Networking Special Interests Group, or as we know it, the IPNSIG. The IPNSIG has provided an environment for the vital exchange of ideas on DTN and beyond. The global organization has over 800 members that aims to expand networking into interplanetary space for the benefit of humanity. We are thrilled to have Oscar Garcia with us today to represent this group. As you can see, he will be presenting remotely. Okay, over to you, Oscar.
Thank you very much, Wendy, and thank you for having me and for this invitation for the IPNSIG. My name is Oscar Garcia. I am the Pilot Projects Working Group Lead of the InterPlanetary Networking Special Interest Group. Next slide, we can move forward. So we're going to talk a bit about the IPNSIG. The IPNSIG was founded in 2002, so it's very close in its evolution to the DTN and the Bundle Protocol and all this process. Next slide. Next slide. Yes, thank you. Well, our vision is to expand networking to interplanetary space for the benefit of humanity. In the last 3 years, the IPNC has turned very active, and we have developed our mission statement that's creating a vision for a common vision for an interplanetary network with the stakeholders. And what is important at this point is that we have built several working groups. I'm going to talk about that a bit later, and several or many of the attendees to this conference, this DTN Industry presentation, are part or participate in many of the activities of the IPNSIG in this idea of creating a vision between the stakeholders and the different participants on the DTN stage. We are also working in a narrative and roadmap to share the future of the interplanetary network by offering this narrative also to the public. So we every month or twice a month we make conferences, presentations, we invite, and all this is open to the public and with great success. We are also working in promotion of technology to promote and increase the maturity of DTN technology. I am in that area specifically. So we are going to talk about that and our developments in different areas on DTN for its use on terrestrial and space applications. Next slide, please. Well, this is our board members. Yosuke Kaneko from the JAXA Space Agency, Vinton Cerf, that I'm sure all of you know, one of the fathers of the internet, that is in Google, vice president, and he was the developer of the TCP/IP protocol and started also with the DTN and the bundle protocol. Scott Burley, that is retired from NASA and developed a lot. He was a software architect of the ION and works a lot with us. Mike Snell is one of the founders of the IPNSIG and an enthusiast, and our Secretary and Treasury, Keith Scott, that is here also in the audience, and perhaps I don't know if he speaks as well, but he works in the CCS SDS as he's our liaison with the IOAG. Well, myself and Alberto Montilla, who is a real fan of space and DTN, and with his company, he's going to present later during the afternoon, I think, some of the development he has been working with. So, next slide. In June this year, the IPNSIG was chartered by the ISOC, the Internet Society, as InterPlanetary chapter. That was because originally we were a working group, and now the IPNSIG for the ISOC is the InterPlanetary chapter. That is an important idea to be the representative of the ISOC for most of space as well. Also, the IPNSIG received the 501c3 status from the IRS. So it's a nonprofit tax-exempt corporation that can receive donations. We are filed in the state of California. So, well, we are very happy about that. You can connect for any of this topic with the email address secretariat@ipnc.org. Please, next slide. Well, we have, as Wendy mentioned, 100 members around. It's a global membership, and we encourage everyone that see our presentations to join the IPNSIG. It's free, and we are very happy when we have new members, and this member are volunteers and participate in all our activities. You have there the email address. Next slide. Well, as mentioned before, these are the working groups. The IPNSIG has a strategy working group that has been working and developed a report last year that we presented. On all the process that we are moving forward is described. A technical working group with a library, a very complete library that is online on our website, and we are adding all the time material. There is an architectural governance working group where at this moment, we are discussing governance needs about DTN, about the solar system internet, and also architecture things like routing. And well, we made webinars, internal webinars, and we are developing reports for the community. There is a pilot project working group where we work technically on the DTN protocol. I will talk about that a bit more later. This is the outreach working group with well, web page, media, webinars, and all that. And we are setting up also, and this is important for this meeting for the industry, business working group, business ideas, brainstorm, and you can contact to my email address that I will provide at the end of my presentation if you want to be part of these working groups, including the business working group, where we also try to help from the pilot project working group the industry in including DTN in their applications, because as we are experienced and experimented, we can be we think we can be helpful for all the industry. Next slide. Well, also between the outreach working group and this narrative, we have the IPNSIG Academy. Started very a lot of activity during current year. You have the IPNSIG Academy. It's webinars every month and sometimes twice a month about different about the different aspects of the solar system internet, architecture, battery protocol. You have there our program for the year, and we encourage everyone to join our webinars and give more ideas, because this is a program that we will follow up next year as well. Next slide. And as mentioned, this is the report. There you have the link, and if some of the operators can copy the address to the chat and share with the attendees, the report of the strategy working group, where we, in a certain way, give to the public our idea and the challenges and all what we think about the evolution of a solar system internet. Let's start. Well, I am now going to talk about the pilot project working group, where that I lead with members of several continents. We are working in developing technologies to test and refine the delay and disruption tolerant networking protocols to allow the connectivity between an interplanetary internet between Earth and space, as David Israel mentioned before. This is something that is going to be needed in time, and we have been working with that for 2.5 years, and I will develop several and show you several of the different projects and that you are working. Next slide, please. Well, one of the things that was like a launching of our working group in November 27, 2020 with Dr. Vinton Senfa and Larissa Suzuki, I set up the communication between cloud servers, from different clouds, and with DTN. As up to the moment, we don't know that there was a previous permanent communication as we did, and we keep this running. But the first we started transferring and messaging and transferring files and all that between cloud servers, and connected these cloud servers also with the TCP network. So it was a milestone, an important milestone. Next slide. From there, we started developing the DTN testing plan, and we tried to connect, and we are connecting corporate networks, personal computers, also universities, and we are also trying with some government organizations as well. We are also working in the project in the next months to connect also with the space with our network, where we test several things that we see that are need to be tested about DTN. Next slide. So we started building this our network. We have now a global network between North America, the United States, some in Canada, South America, Europe, some also started in Asia. We are trying to start a node also in India, and all this is running DTN with more than one implementation. At this moment, we have running 2 implementations, Ion and micro DTN, and one important thing that I want to mention to the industry leaders that are listening this chat is that we would be happy if the industry connect with us and is interested in using this network and helping us in testing, and also it could be useful to all of them to test the DTN protocols at a certain scale and growing. Next slide. Well, we have several members in the working group, small companies, small businesses, and individuals. Spatiam Corporation developed the DTN manager that we are using, for example, to test our network. Alberto Montilla, who is here, is also going to present more later for sure. Next slide. They also made a certain experimentation last year in interoperability and provided also as knowledge for the working group using the ESA OPSAT, that is a satellite that ESA provides with. In that case, using Ion and micro DTN, that is a German implementation. And following that, there was a lot of work this year with interoperability between these implementations. Next slide. Also, we are using another development that I worked during last year. That is what is called the DTN test suite. That it connects between, allows to test with different versions of implementations of the bundle protocol, and we developed this like a full system with registration forms, with software, to be downloaded, installation manuals, user manuals, well, all that one of the first DTN products in a way. Next slide. We have also provided to this a web interface to ION specifically. With this web interface, we can manage, for example, to be pinged to different servers in the network. So in a very easy way, as most know, most of the applications with DTN are still very technical in the way to be used in terms of their interfacing for the regular user. And one of the things I've been working in that very hard is to make it easier for the end user. All these tools that I am showing now are any of the person of the audience or the industry can contact us in how they can use that, and we will be happy to establish some way of making it available for them. Next slide. Well, other members of the group, I run that IT Solutions from New York State, from North New York, are working also with NASA in projects with DTN radio communications, with software-defined radios, reactive routing. Well, next slide. There is the contact information of them. So now they have obtained a grant from NASA for this project. Next slide. This is another of our members in the state of Florida, Tolerant Networking. This team is been working with several things in development and hardware and implementation of specifically ION in certain challenging environments. But last week, they started with all our group the testing of the convergence layer for IPv6 in ION. This is, we consider that this is a novelty, and it will allow to connect also very easily or more easily with smartphones, with different carriers. So we will keep the community updated about this. It's in the process of testing at this time. Next slide. Well, this is also from SolarNet 1. They've been working in this model of Internet architecture between Earth and Mars, and the possibilities of how to make this work. Next slide. Well, this is a product that is mostly oriented to healthcare. That is a unified medical record for space exploration. That is a development that I've been working myself for some years. I have experience for 20 years in the digital health area, and our system has been operational, is operational with 60,000 patients, millions of medical records and clinical tests. And we developed 2 years ago, we presented in the workshops of the IEEE the first medical record for space that used DTN ION technology connecting the medical centers with the spacecraft, and now in this new version, the spacecraft and planets. The idea is that you can, from a space, make a consultation directly to your doctor on Earth in the medical office where the doctor is making consultations at the time. We make a testing. I did that with my medical record, and it worked pretty well. Next slide. We say your medical records wherever you are. We have an award from the World Summit of the Information Society some years ago, and we were nominated for the Arthur C. Clarke Award of the British Interplanetary Society for Medical Record for Space. And we plan to make a testing on the moon in June 2023 with launch data holdings. Next slide. We consider that this technology is going to be very useful for space exploration, space tourism, and the availability also on Earth of medical records in challenge environments, because you know that if you have weather problems, you have fires, we have tested this kind of things many times, and this health information is very important to be available. You have there our website if you want to know more and request demonstration. Next slide. Well, this is a development of another of members of the group. This is a laboratory developed for research and development and education. This laboratory is a prototype, is all interconnected with DTN, and it's thought to be a very useful way to give a wide idea for students about what we are talking about communications in space. Was developed by Jorge Amodio, who is in Texas, and we all the time we use his lab that is connected to our network to make this experimentation and testing. Next slide. This is the last version of the control center, and this works. This works for real. You have there with Legos the officials controlling space communications, and it's all connected with Raspberry Pi with Ethernet, Wi-Fi, Bluetooth, and it's running ION and micro DTN and implementations. And we are planning also that this could be useful for the agencies and to give awareness, public awareness to the public of what we are talking in space communications. Next slide. Well, this month also, one of our distinguished members, Larissa Suzuki, Dr. Larissa Suzuki, presented this model for enabling space communication using artificial intelligence. That link that you see there below, you have all the presentation that she did that is public. She is technical director of the office of the CTO from Google, and this is a very interesting approach because the use of artificial intelligence to compute routing and a lot of information needed in challenging environments with this long distance communication. So we are happy to also to collaborate with everybody in this on this target. Next slide. And these are developments from the Luleå University of Technology, Samogra Sigte, and Maria Uden. They are in Sweden. They have been working in the Arctic for several years using DTN. What you see there is ice covering one of their antennas. With this technology, they have been herding, following reindeers in the Arctic at very low temperatures, and this is challenge environments for real, and using LoRa DTN connected to ion drones, exchanging geoposition information, also environmental condition, monitoring ice thickness, underwater buoys. And next slide, you will see something related to this as well. This is also an experiment, it is operational all the time. That is, these are caves in Slovenia, the Potocna caves that are very deep caves that have tourism, and Bojan Grasic developed a DTN technology there that is used all the time to monitor the internal conditions of these very deep caves, and get information and generate information on graphics, using all this using DTN. That is an experiment that we consider is very interesting. Next slide. Finally, also between these two groups in Sweden and in Slovenia, they are connecting and exchanging information of the environmental conditions in the Arctic and in this case. And to get, you know, that climate change is something that we are all very concerned, and I think using DTN in this development gives one of the very interesting applications for this technology. Next slide. I think I'm closing to my presentation. I don't know if we have some time or if you can make some questions, and I really appreciate the opportunity that the SCAN and the NASA DTN working group gave us to present this to the industry. Yes, I see a question there. James?
Hi, this is Jim Shear. I'm the chief architect for SCAN at NASA headquarters, and I'd like to add a news item that just occurred yesterday. You mentioned the IOAG as a liaison organization. We had the international meeting of the Interagency Operations Advisory Group, the IOAG, yesterday. And at yesterday's meeting, the IOAG voted to approve the terms of reference to establish an IOAG international committee to study LunaNet governance. And we will be working that among the civil space agencies, but we will also be including liaisons with a number of external organizations, including the Internet Society via the IPNSIG and the Internet Engineering Task Force via the DTN working group. And so we're looking for industry cooperation and coordination on that as well. So if there are industry members who are interested in following up on issues related to LunaNet governance, and one of the things we'll be studying will be to what extent internet governance can apply to LunaNet governance. But if there are any industry members interested in contributing to that, they can contact me through the means you've got at the workshop today. So thanks, Oscar.
No, Jim, thank you very much, and we have been following that, and I know Keith Scott is has been our liaison with the IOAG. So we also offer our services from the IPNSIG to keep in touch with the IOAG from the industry as well. Absolutely, thank you, Jim. Yes, any others, or Wendy, if
Hi, Oscar. I'm polling the room right now and seeing if there's any questions here.
yeah.
Okay, I don't see any hands here. Are there any hands online?
Well, if you, Sarah Whitney.
There.
Sarah?
Yes, thank you. I had a question about time and how your group is thinking about that, because there are going to be significant relativistic effects on, time, depending on where you are in the solar system, and moving data back and forth is going to be affected by that. So is that something that's part of your group, and I just didn't see it in the slides?
Well, we are going to have in the architecture working group I don't have the date yet. The architecture and governance, Dr. Scott Pace is working very hard related to the time issues on space. He's one of the advisors to the IPNSIG and the architecture working group, and he's going to give a conference on that. I can mention on that topic that there are international, there was an international meeting, I guess 2 months ago. And if you wish, Sarah, to send me an email to Oscar Garcia at ipnsig.org, I would be very happy to send you information related to the time topic that is very important for us as well. Yes.
Great, thank you.
No, absolutely. Yes. There was another hand up.
I think it's Jim Shear again.
Okay, so if I can add on to Oscar's reply to Sarah's question, we are working at a U.S. government level right now, excuse me, on the definition of a new lunar time standard that we expect to ultimately take to the international standards level to establish so a new lunar time standard equivalent to Universal Coordinated Time, or TAI. There are several international time standards that are all terrestrially based, and what we are looking at doing is defining a future lunar time reference that will be part of the lunar reference system that will actually be lunar based and eventually establish atomic clocks on the moon as the basis for lunar time that would be distributed through the LunaNet PNT services that would include the relativistic corrections, just as GPS, Galileo, other GNSS systems do in the terrestrial environment. So yes, you can look forward to lunar time that will be coordinated with terrestrial time standards.
Thank you.
That's Sarah, related to that, that's a topic that in the case of medical records that I've been working, and it's a very important topic, because when you determine a certain practice in digital health, it's very important to know when exactly happened. So time is going to be an issue to resolve for everybody.
Thank you.
Well,
Okay, thanks, Oscar.
Thank you, Wendy. Thank you very much.
Thanks, Oscar. Great presentation. So We are slightly ahead of schedule. We're going to take a 20-minute break, and when we come back, we're going to hear from the SBIRs and ESIs from the Glenn Research Center. Thanks again, Oscar. Okay, everyone. Welcome back. We're going to continue with the Glenn Research Center SBIRs and ESIs. We're going to start with Dr. Ricardo Lent from a scalable and QoS-driven cognitive routing capability for lunar delay tolerant networks, ESI. And after him will be Dick Stottler from the delay disruption tolerant reinforcement learning and Aurora-based communication system phase 2 SBIR. A quick note, Dick Stottler, if you are online, if you can please make sure to send your presentation to myself and Sarah Salem. We'd really appreciate it. But we can start now with Dr. Ricardo Lent.
Thank you, Wendy. It is a great pleasure to be here today. Good morning, all. I'm Ricardo Lent, Associate Professor with the University of Houston, and I'm happy to share a few results related to the 2021 ESI, a scalable and QoS-driven cognitive routing capability for lunar DTNs. Next slide. Yes, so as one can probably guess from the title, the long title, the project explores AI techniques to achieve optimal and distributed bundle routing, taking into account that the network may not be fully deterministic times, and that support for different classes of service may be required, while at the same time considering scalability, interoperability, and autonomy issues. So about the general motivation for this work, and considering that the application scope of DTN is expanding quickly as we hear in the morning, multiple network metrics become very relevant to the system operation. So this slide illustrates, in a way, the effects of different factors to the performance of a certain bundle flow. Of course, routing is one such factor that affects the flow metrics. We have here, for instance, in yellow, we have the delivery time or response time, as we technically call it. But also we have bundle throughput, we have bundle loss ratio, we have jitter. So we have many flow metrics that in a way tell us something about the performance of an end-to-end flow. As done today, it is feasible to extract a path from the contact plan, but many significant factors that drive the end-to-end performance are difficult to include, not impossible, but difficult to include in such plan. So I'm talking about things such as contact feature deviations that may happen, for instance, variations in the start and end times of the contacts, which for some reason didn't happen as planned, dynamic variations of the channel bit error rate and some other features, and also some diverse random events that can change the network topology at any time. And also non-traditional features such as link pricing is something, are things that are not being considered yet when routing bundles. And things such as pricing is a metric that may become quite relevant as the commercialization is going underway. In addition to the network metrics that of course affect the bundle flow, routing also determines, of course, what space assets are going to be utilized when forwarding bundles. And therefore, routing affects the network as a whole, which can be measured through a different set of metrics. For instance, the network utilization, the energy consumption levels, all the way to the operational cost and user satisfaction. So in turn, all of these factors and outcomes will influence the network and the factors as expressed by that arrow coming back, right, to the performance. Next slide, please. The main argument here is that while there's no doubt that latency is a key factor for space routing, additional metrics may become essential when seeking to optimize the operation, the network operation. And that will happen while we try to broaden the scope, the application and scope of the space networking. So before I mention the CSG, let me tell you that there are many questions that require answers if we want to achieve the objective. One of them is, of course, what metrics will be relevant for the lunar operation and also for future space, scenarios. Second, how to route with the selected metrics. So what about the use of combined metrics? So what about if we're interested both in pricing and reducing the monetary costs of the system, but also we're interested in minimizing delay, for instance. So what is the performance to be expected? What will be the optimal performance? And of course, related to the ESI project, how AI can help to improve the results. So this ESI attempts to provide answers to those questions, at least as best as we can. And the starting point for the project is the CSG, the Connected Space Gateway, which I briefly summarize here. The main idea with this project was the exploration of advanced machine learning to achieve optimal routing, but specifically in the form of using spiking neurons. The spiking neuron model is a model that predicts with great accuracy the electrical behavior of real cortex neurons. And these neurons essentially use a short duration signal or a pulse to communicate. And depending on the rate at which they communicate, well, that in a way carries the information. They are known to be more computationally efficient than prior artificial network model, artificial neuron models, as according to many researchers. And through a series of experiments, we demonstrated that the CSG approach was able to achieve the expected outcome. The tests were conducted on the network environment on a laboratory environment primarily, but we also had the chance of running a validation test of the core routing unit using the former SCAN testbed, thanks to NASA GRC especially. So next slide, please. So the core unit, which is shown here, is given by spiking neural network, whose architecture is depicted here for an arbitrary case of a gateway having 5 outbound links or actions. So the network will essentially try to select which outbound link should be used for the next bundle. A subset of neurons, therefore, in this architecture represent each of these possible actions. And what we do is we essentially run the system, the neural network, and we look at the spike emitting activity, and we select the associated neuron that emits a spike at the highest rate, and that indicates for us the optimal selection for the outbound link for the link bundle. Of course, this system, in order for this system to work, we have to implement an appropriate learning method. And the way we conduct the training is through reinforcement learning. And that essentially achieves a continual modification of the SNN synapses or weights according to the expected outcome of the different routing actions. Next slide, please. So in addition to testing with our home prototype, we had the chance of re-implementing HTTN with support of the GRC team to re-implementing it for HTTN by taking advantage, so implementing CSG for the HTTN architecture. By taking advantage of the modular architecture of HTTN, we created essentially a CSG module that was able to communicate with the ingress module of HTTN via 0MQ sockets. And that way, our routing decision could be easily offloaded to the CSG module. So use the spiking neural network for making the routing decisions. A few additions were needed as well, which we listed in this slide. They were essentially needed for supporting the reward estimation method of the CSG that requires certain capabilities from the prototype, and given differences between the prototype and the actual HTTN capabilities, we'll have to make some modifications, some small modifications. But in the next slide, we can see that we experimentally validated the approach using an emulated testbed, and we showed that it was possible to achieve a lower end-to-end delay for a given traffic flow, in this case flowing from the top to the bottom of the network, than forwarding the flow over the initial base or worst path statically. So just by looking at the network and just statically deciding, just go using the left hand path or the right hand path. So you can see here a few results where we compare, in a case with link disruptions, in another case without link disruptions, the results. So there's a significant difference, especially when once we move to higher or heavier data rates, as expected, as what is going to happen at those levels is that congestion is going to start building up, and by just statically sending data, we will just have congestion along the way, right? Whereas the CSG will, in a way, adapt to the congestion levels, and we'll try to avoid them by choosing a different path. Next slide, please. So moving forward, the workflow for this project involved first the identification of suitable AI techniques for decentralized routing, using the CSG, as I explained, as a starting point, and the formulation of class of service routing, which involves the definition of multi-objective optimization analysis of the problem. The methods are initially tested by using stochastic models and simulation models, which offer initial feedback of the of the usefulness of the different ideas, and allow us to further improve the approach. And then, of course, later on comes the experimental and validation part, which in turn is expected to produce new useful feedback. Now, for the time being, we are right now at the first steps of the project, so we'll comment mainly on the first two blocks. Next slide, please. Shows a simplified case, which will allow us to explain better the kind of work that we are doing. In this case, in this simplified scenario, we have a single flow traveling from left to right and crossing given DTN. And we're assuming here that can be achieved through two different paths. So we have a routing agent which have to decide bundle by bundle which path should we use. And of course, if we look at the long average behavior, long-term average behavior of the system, we will see that path 1 will be selected a certain number of times, path 2 will be selected a number of times, and therefore it will be easy to calculate the fraction of traffic that will go over one path or the other. So in this case, we're assuming that path 2 is faster, but path 1 offers longer contacts on average, and also more buffer capacity. So with path 1, there will be lower chances of having buffer overflows. On the other hand, path 2 is associated with an on-demand pricing model, which basically means that we're going to have a pay-as-you-go model, and it's going to be charged at $1 per used second. And of course, $1 may not be realistic in practice, but that doesn't really impact the accuracy of the model. Path 1, on the other hand, is priced using a reserve model, and the meaning is simply that the cost is fixed. So we pay a fixed amount per time period, and so it does not depend on how much we use the link. So the bundle decisions, like I said earlier, are going to be done by the routing agent, and the routing agent is going to determine eventually what the value of P is going to be. And we're going to use a certain field in the bundle to indicate the class or type of service that we want to receive for the bundle. And for purposes of this presentation, I'm going to assume three possible types: latency, throughput, and loss, throughput, which is equivalent to bundle loss. This one is the inverse of the other, can be calculated with the inverse of the other, and also monetary costs. Now, these metrics will be used either in isolation or combination. Next slide. So before looking at how the neural network can achieve, a proper balance between these different metrics, it's useful to observe what will be the effect of manually varying the value of P. So these four charts essentially depict, respectively, the response time, the throughput, the bundle overflow ratio, and the monetary network monetary cost rate. So we're looking at these four different views of the network flow, these performance metrics of the same network flow for the same value of P, right, which is depicted on the horizontal axis. Remember that P is the amount of traffic that goes over, the percentage of traffic that goes over path 2, or the traffic ratio that goes over path 2. The different curves that are illustrated in the charts show the outcome for different values of the bundle flow rate. So it can be observed, for instance, that there is no trivial answer, right, of what would be the optimal value of P, because it will depend on what metric we're looking at. It will depend on the traffic rate that we are handling. The model predicts, as you can see here, that it is possible to reduce the response time by increasing the utilization of path 2, so by increasing the value of P, for heavier arrival rates or heavier traffic. But also, it also predicts that action will increase the buffer overflow ratio, leading to lower throughput in the end, right? And moreover, the monetary costs will also increase. Yes, so evidently there is no easy way of telling what will be the optimal way of routing traffic here. So we need then a definition here of what needs to be optimized. So what metrics needs to be optimized, and how to achieve the optimization. Next slide, please. So the how part of the questions is given essentially by the CSG method, at least for the first stages of our current research. So I'll focus mainly on the what part for the rest of the presentation. So this part, the what part, involves formulating a suitable reward value for the reinforcement learning algorithm. And the idea is simply to formulate that reward in terms of the routing metrics that are of interest to us. So to that end, the reward can be formulated, or let's put it this way, it could be seen as a routing cost, right? The reward will be the inverse of the routing cost. So we can talk interchangeably about these two metrics. So to that end, it can be formulated then, like I mentioned, as a single metric, such as latency, as done in the original CSG. It could be formulated in terms of throughput otherwise, or equivalently in terms of the bundle flow loss ratio. And depending on the needs, it could be also expressed as a combined metric of latency and loss. That combination becomes especially relevant when retransmissions are disabled. For example, for streaming applications or when we have to support a near real-time transmission of critical data. So where there's no point in retransmitting data, but we want to ensure that the data will be delivered. And the way we are, essentially proposing how to achieve this combination is by looking at the ratio of latency and the probability of success, which is simply given by 1 minus the probability of loss. So it can be shown that this expression yields the optimal latency loss results. I won't really show in this presentation, but it can be shown and demonstrated that the ratio can give us the lowest latency with the highest possible throughput. Like I mentioned in previous slide, these two metrics may go in different ways, right? So we may need to sacrifice one in order to optimize the other. So by looking at the ratio, we can optimize both at least in a theoretical way, we will optimize both in the best possible way. Next slide, please. We could achieve something
Excuse the
similar.
interruption.
Sure.
It looks like we have a question online.
Oh, sure.
Can you hear me?
Duradola.
Hi, my name is Ola Drodola from SSTL. Just a quick question.
Sure.
Your model doesn't seem to take into consideration, especially when you mentioned when you mentioned on demand, does your model take into consideration anything to do with prioritization of a service, especially for a commercial payer? How would you consider if somebody has prioritization for a human, a person on the moon that is a human trying to contact home in response to a robot or any other? Just how do you prioritize that in your model? Thank you.
Right. Thank you for the question. So quality of service can be achieved through two different mechanisms. So one of them is by appropriately managing the buffers at every node. So in terms of creating priorities, for instance, we could have nodes with different buffers with different priorities. So 1 to whatever number of priorities we would like to support. So that way, high priority data can go into the top priority buffer and be processed first. So, but that could be one possible scenario for implementing quality of service. The other possibility, which is, so in a way, the buffer management technique is a well-known, well-established technique. So given that this SAI is essentially a research project, what I'm trying to look at is I'm looking at a different scenario or a different way of achieving or extending the possibility of establishing quality of service for the bundle flows. And that is something I'm trying to achieve through routing. So we have both things. Of course, one will complement the other. It is assumed that, in this work at least, that buffer management is already being implemented by lower layers of the protocol stack, and routing is essentially focusing on trying to optimize the resulting system. I hope that answered the question. So in a way, the different buffer capabilities or prioritization of buffer capabilities is something not explicitly expressed in this model. It can be done, but so far, we haven't attempted to include it. So hopefully that answers the question.
Thank you. Yes.
All right.
Cheers. Bye.
And I'll be happy to discuss further after my presentation. So I was mentioning that we could achieve a similar trade-off by looking at the monetary cost used as a routing metric. So we can link monetary cost to a routing objective. In this case, we can differentiate at least two different kinds of pricing models. So one of them will be the reserve pricing, where users pay a fixed amount per period of time, and therefore we can assume that the cost rate will be zero for the routing agent, as the agent cannot do anything to modify the total cost by using or not using the link. On the other hand, we consider an on-demand pricing case, which essentially is a pay-as-you-go case, where the total price will depend on how much we use the link. Yes? So these models are basically very similar to the ones used in cloud computing. So we expect that something similar will happen eventually as things become parts of the system become commercial. So different expressions could be derived for a latency money routing objective. So the following ones are proposed. If you are interested in having control over the weight of the assigned metric, then that factor can be included through a parameter K as shown in the first expression inside the box. On the other hand, if you're interested in establishing a penalty for either exceeding a certain latency or money threshold, then the two middle expressions could be used. And finally, if we are interested in the optimal trade-off between latency and monetary costs, then the best is to use a similar expression to the one we use for throughput and latency, which is basically the ratio of the two metrics. Next slide, please. So what we see here is the optimal forwarding probability. So this is obtained from the model. So this is a mathematical model basically that gives us these results. The results cannot be, unfortunately, used directly, applied directly to decentralized routing. However, give us a very good information so that we can become aware of what can be, or what to expect, right, in the end. So what we see here is we see here that the optimal solution, that's the biggest chart, gradually increases the utilization of path 2. So on the x-axis, we have again the traffic load. So as we increase the traffic load, the second path, which is the one that is on demand, becomes useful for optimizing the trade-off between cost, monetary cost, and delay. That's true for all cases except for the money-only objectives, of course, because from the money perspective, money cost perspective, it's best to use always the reserve lane as the price is fixed, right? So that is the green line depicted here. So you can see as well, I won't discuss in detail, but you can see here the effect of using the optimal value P on the different network metrics. So one thing we can observe is that it really depends on what we're trying to optimize, right? So the results really depend. Next slide shows a few more practical results obtained in simulation. In this case, again, it's a simplified scenario, but the results really, and the system also apply really to any kind of topology, but it's useful to have a simplified version to explain better the results. So in this case, we have, again, two possible paths between the source destination, source being node 0, destination being node 3. And we are showing here that one path, well, has a higher loss rate expressed by a higher value for the bit error rate. But the other path is slower. So one of the links on the lower path has a lower transmission rate. So the results are the following. On the left chart, we can observe the average bundle response time for different choices for the bundle sending rate, which is shown on the x-axis. In the right chart is the bundle loss ratio. The green line shows the shortest path performance, which is giving us a reference of what we could achieve by a standard routing method. Latency-only routing objective, which is shown by the blue line, achieved on average, the lowest latency for all cases, but also the highest, or not the highest, but a high bundle loss rate. And we observed exactly the opposite behavior with the loss rate used as the sole routing objective. Now, if we look at the power line formulation, the ratio of the two, we observe that we achieve a good trade-off between the two metrics. Next slide, please. So we obtain similar results for the time and money case. Now, in this case, the lower path is faster, but also more expensive and associated with an on-demand pricing model. The top path uses a reserve pricing model. The charts show the average end-to-end response time and money cost rate on the right. And as before, the green line is the other result for the shortest path, which in this case flows along the top path, and actually both paths are the same from the point of view of the shortest path perspective, but the program just decided to go that way. Also, as before, the use of latency only produced the lowest latency, as expected, when using the CSG, but also the largest monetary cost as a total amount, with the situation reversing when using money only as the routing objective. So in this experiment, the power-like expression was used, and it can be seen that it achieved a proper balance between the two metrics. So next slide. To finalize, the next steps of this project will be the exploration of additional metrics that we think will be significant for the lunar and space DTN context. One of them being the remaining energy available in the space assets. And the idea is that by dynamically routing, we could reduce the possibility of energy-related outages. We are also exploring new AI capabilities that are expected to further improve the scalability and efficacy of the cognitive approach. And we are also taking steps in increasing the realism of the simulation and emulation models so that the results can more accurately correlate to real expectations. So as a side comment, while developing the models, we also discovered a few very interesting system properties, one of them being that there is a time loss paradox that affects DTNs. In a non-DTN system, it is common to expect an increase of both throughput and delay with heavier traffic. However, this is not necessarily true in a DTN under certain conditions due to the long, disruption times. So there's I don't have a lot of time to discuss this in detail, but the work is being published. So I'll be happy to share the paper if you're interested in looking at this point. So as a final remark, cognition, we think offers a viable alternative to create extensions to current DTN methods that can help to achieve the autonomy and optimality needed in the future. So with that, thank you everybody for listening to my presentation, and I welcome questions if we have any.
Hi, Dr. Ricardo. I will quickly poll the room here and see if anyone has any questions. Okay, we have a couple of questions in the room. 1 minute.
Hi, it's Vince Cerf again. Thanks so much for sharing that analytics. First thing that comes to my mind in this presentation is the notion of multi-commodity flows. I'm sure you're familiar with that. Len Kleinrock has done quite a bit of work on multi-commodity flow, and so if you don't know him, well, let me ask, do you know Len Kleinrock? Okay, so you might, if you feel comfortable sending him an email, you might share the work that you've done with him and see what his reaction is. Second thing has to do with the dynamics of connectivity. I wasn't sure whether the models that you were building included the loss of connectivity from time to time among the various nodes. When I asked Kleinrock about how to analyze the capacity of a network that had this variable connectivity, he came back with several pages of fairly dense math and said this is a hard problem. I can see you're smiling because you probably concur with that. Figuring out what the capacity of a DTN is still, in my view, an unsolved problem. So I hope you could spend some time on that as well. Last question has to do with latency. I wasn't sure whether the latency you were measuring was link only or whether it was end-to-end. If it's end-to-end, it may be harder to obtain that information in a timely way. Is that end-to-end latency that you're measuring?
It is.
Okay. Thank you. That's all I got.
Oh, thank you very much for the comments and questions. Let me point out a couple of things. Thank you very much for offering the multi-commodity information. That would be actually would be quite useful. In fact, the ratio that I'm using to balance delay and loss comes from Kleinrock's work on the power metric. The power metric is essentially the ratio of throughput and response time. So what I'm doing in this work is trying to simplify throughput by just looking at loss, because I thought it would be easier to measure in the real system than measuring the end-to-end throughput. About the model, the loss of connectivity, the answer is yes. My model does include the possibility of having links going down, with the simplification that the amount of time available for a contact, the amount of time is modeled as a random variable with an exponential time distribution. So the answer is, in a way, yes, but limited to cases where we have exponential distribution for the duration, the contact duration and the disruption duration. But it does take into account the disruptions.
Thanks, Dr. Ricardo. I think we have one more question in the room.
Ricardo, thanks for the presentation. It was very insightful to see the algorithm and the results. My question is about computational requirements and how do they scale as the network scales? It's the typical, it's a typical evaluation that that is done for for any routing algorithm, especially in the DTN case. So I'm curious about it.
Yes, thank you very much for the question. Yeah, I didn't mention much about complexity. The complexity of the CSG is actually linear in the number of actions. So it's not too bad, I will say, in that sense. However, it does require a different routing unit per destination. And in this case, if we want to include class of service, it would be a different routing unit per destination and class of service. So one of the reasons for this ESI, this project that we are working on, is trying to increase the scalability of the approach. So I don't have yet a good answer to how to scale it up, but we are working on it.
Awesome. Thank you.
Yes, thank you.
Okay, are there any other questions in the room? Okay, I don't see any, and I don't believe there are any questions online. Thank you, Dr. Ricardo.
Thank you very much. Thank you for having me today. Thank you.
Okay, next we will have a minor correction. It's going to be Gregory Howe presenting for the Delay Disruption Tolerant Reinforcement Learning and Aurora-Based Communication Systems, SBIR. Mr. Howe, are you online?
Yes, I am. Can you see?
Okay.
Can you hear me?
Oh, yes, I can hear you.
And is someone sharing my slides?
Yes, they're showing right now, and we can see you too.
Okay. So I'm Gregory Howe from Stottler, Henke Associates, and I'll be presenting the delay-tolerant reinforcement learning and Aurora-based communication system. Next slide. So this is an overall view of the architecture of DREAMS. So we have three main components: a packet prediction module, a link optimizer, and a scheduling agent. The packet prediction module predicts network traffic, both scheduled and unscheduled, which is used to feed into our scheduling algorithm to provide filler tasks, which are used to reserve space in our network for high priority communications. Our scheduler works in three components, the first one being a route finder, which finds possible routes for each bundle that needs to be routed, and a bottleneck route selector, which processes each of the individual routes to select one route for each bundle, which is then passed to our detailed scheduling agent, which creates a executable schedule, which is passed to the communications hardware and communications controller. Separately, we have our link optimization agent, which is constantly working to maximize the throughput of every network communication link to help provide stability by minimizing things like the bit error rate and maximizing quantities like bandwidth. Next slide. Next slide. Next slide. Thank you. We have a concept of bundles, which are the finest grained unit that we're trying to route. A bundle consists of a creation time, a source, destination, size, deadline, priority, and type. The goal of our algorithm is to route a bundle created at some creation time to a destination from our source before some deadline. We group bundles that have similar characteristics into super bundles that all have the same properties. The reason for this being many nodes will have different computational capabilities, which bundling bundles into super bundles allows us to address nodes having different computational capabilities. For example, a highly computational capable node such as the International Space Station can probably handle routing each bundle individually, but there are some nodes who may need to group bundles by thousands to actually be able to handle the routing. Next slide. It looks like the screen's frozen on my side. Are we looking at the next slide, the link optimization one?
So it appears someone else is sharing their screen versus the one we have here on site. We could switch that back.
Okay.
Okay.
So, thank you. So our link optimization agent is a deep reinforcement learning based agent, which is trained using deep deterministic policy gradients to select link parameters that maximize the quality of service. These link parameters are such as like power, modulation scheme, coding scheme, symbol rate, and roll-off factor, which are selected to maximize things like bandwidth while minimizing bit error rate and other quantities. So to do this, we train inside of Kratos' OpenSpace quantum radio software modem capabilities, or we use Kratos' OpenSpace quantum radio software modem capabilities. This allows us to provide inputs such as the modulation scheme, coding schemes, power, roll-off, and frequency, and provides us back statistics like delay, varying match filters, Doppler effect, and simple noise, and separately provides us information that we can generate a reward function from, such as the bit error rate, effective bandwidth, and EBNO. We've plugged these into a OpenAI GIM environment using Kratos' API to train our agent. Next slide. Separately, we have a bundle prediction algorithm, which uses past traffic or network traffic history on bundles to train two neural networks, one for predicting scheduled event or network traffic due to scheduled events. So for example, maybe we have a scheduled event for a astronaut calling home. We know that this will likely predict or create some network traffic, and we also have rough times for the beginning and ending of this transmission, but perhaps we're able to predict things that typically occur for transmissions like this, like they typically start 5 minutes late and end 10 minutes early. And we also have a neural network that will predict the expected bundles that won't be tied to any scheduled event. These are periodic events that aren't scheduled, but we can learn that they typically happen. So we sum these two network outputs to get the expected traffic for any given day and time, which are used to create filler tasks for our scheduling algorithm to reserve space for high priority communications. Next slide. Thank you. Next, I'll be discussing the actual Dream scheduling algorithm. Next slide. So for an overview, our scheduling algorithm works by selecting R routes for each packet, where routes are a combination of fast routes, low congestion routes, and routes that are balanced between the two quantities. We convert each one of these routes into a set of bottleneck scheduling tasks. These routes are then passed to bottleneck scheduling, which chooses a low congested schedule. So a schedule where there aren't any conflicts between tasks and we can maximize the throughput. This selects one route for each bundle. We then convert these tasks or these routes into a set of start, store, send, transit, and receive tasks, which are passed to our detailed scheduling agent called Aurora, which creates an executable schedule that we will pass to the communications hardware. Next slide, please. Next slide, please. So a standard priority-based scheduling algorithm typically works by sorting all tasks by priority using deadlines to break ties. And then you would typically schedule tasks greedily by choosing the fastest route based on local information. This is what everyone thinks of. It's simple, easy to implement, and runs fast, linear if we ignore some logarithmic factors. But it's notoriously bad and produces pretty suboptimal results. The problem is it's being greedy and not using a holistic view of the entire schedule. Next slide. We address this using our bottleneck scheduling algorithm, which works by first probabilistically allocating weight for each task across all resources that task could use at all times. We find the peak resource usage. So, for example, if 10 tasks want to use some intent at some time, that'd be a highly congested resource that would probably create a peak. We find the largest contributing factor to that resource peak, and we remove all tasks on the route corresponding to the bundle that was contributing to that peak. And we select one of the R routes for that bundle that minimizes the new peak that's made after the schedule. We repeat this until either we've scheduled all of our bundles or there are no bundles left that can be scheduled. Next slide, please. So I'll go through an example scheduling scenario now. Next slide, please. So for our scheduling scenario, we created a set of satellites and ground stations, both on the Earth and the Moon, with realistic orbits. Our scheduling scenario was set up for about a 2-hour time window, where the main point of the 2 hours is it affects the visibilities. For example, no visibility survives the entire scenario. Every visibility changes at one point. This scenario had 22 nodes, 300 links, and 360 visibilities to choose from. We were able to route about 3.5 million packets, which corresponds to about 3,500 of our super bundles, in approximately 55 seconds. In other scenarios, we realized that our runtime was scaling approximately linear with respect to the scenario size. We compared this to a semi-naive baseline, where we still use bottleneck scheduling to provide look ahead, but we only use the fastest route for each packet, and This more naive approach is only able to route 78% of what our approach could do, and was still smarter than the original thing we discussed of greedily routing every packet. Next slide, please. So now we have a couple of visualizations for our scenario. So each of these diagrams, or each of these figures, gives a station name in the top left corner and the amount of sides that that station has. So, for example, the top left figure has TARDIS K, and each rectangle in this visualization corresponds to a bundle that's being routed on a given side. As you can see from the four figures, our algorithm was consistently utilizing these resources almost to their full extent. Next slide, please. We have a similar visualization for our detailed scheduling algorithm, the one that actually creates an executable schedule, where each rectangle here also corresponds to a single bundle that's being scheduled with like send, transmit, and receive tasks. We can see pretty high resource utilization on these sides as well. And this detailed scheduling component also ran very quickly. It took approximately 4 seconds to run our 2-hour scenario on. Next slide, please. Now I'll talk about a few modifications that we can make to make our algorithm distributed. Next slide, please. So our distributed simulation environment will be done using Quarry Main, which is a realistic network emulator. So we'll feed packets that we're going to schedule into Quarry Main as a custom service, and also use HDTN as a service. Our Dreams routing algorithm will then be added to HDTN as an instance of the bundle router class, and it will provide bundle actions, which are what we will use to execute our schedule. Next slide, please. So as I presented it, Dream scheduling is an inherently distributed algorithm. So how we'll deploy this across the network is we'll deploy one instance of Dreams on a node, where a node could be something like the International Space Station, a ground station, or any other satellite or ground station. And we'll use diffs to update the schedule. So to transmit the schedule across all other nodes to keep every other node updated on what it's going to need to route. So all of these, all this scheduling is going to be done on every node, but only for bundles that are going through that node. So these nodes will be able to make dynamic adjustments in real time. For example, if they see a visibility link that they expected to exist no longer exists, or they create network traffic that needs to be routed that wasn't part of our original schedule. Our correctness proofs also rely on enforcing that only nodes that the route goes through are able to reroute the communications. Next slide, please. Here we have a diagram of what Dreams may look like when deployed. So we have 4 nodes in this scenario where most of the nodes can talk to each other except node L, node I, or node I, which this can represent true network limitations. For example, node L and node I not having a direct link to each other due to interferences such as the Earth being between the 2 nodes. So in this diagram, we have that we're deploying one instance of Dreams on each of the nodes, and these instances of Dreams are routing data packets to each other and letting other nodes know about any updates that they made to the schedule. Are there any questions?
I'll quickly poll the room and see. Okay, there's one.
Hi, it's Vin again. So this is an interesting tactic. One question I have is whether the statistical models will work well when we have relatively small size networks and not a huge amount of traffic. I worry that machine learning algorithms, for example, which rely on some stability in the statistics, may get distorted in the smaller networks. Do you have any feeling for how well does it scale up? Does it work better at larger scale than it does at small scale?
We would expect that it'd work better at larger scale. Like you were saying, machine learning algorithms and statistics models tend to do better with more access to data. We have that we're using these to create filler tasks for our scheduling algorithm. So it not scaling as well to lower traffic doesn't affect us too much, because in those cases, we're not needing to create nearly as many filler tasks for high priority communications. So in the cases of trying to predict where data is sparse, it's not as big of a factor to how our scheduling algorithm performs.
I think I almost believe that. The only reason I'm hesitating is that if you have traffic which is not easily modeled statistically, then the learning doesn't work very well, because you learn sort of the wrong things. So this raises an interesting question about under what conditions is this likely to work well? And it may only be in the cases where the traffic model has aggregated enough traffic that you can rely on the law, literally the law of large numbers, to produce good statistical modeling of the traffic demand.
Yeah, I agree. We have to have a large amount of data aggregated for the model to perform well, which will happen for the more utilized links.
So the good news, I guess, is that if we deploy this thing and it gets used a lot, it gets better.
Yeah.
Okay, it looks like we have a couple of hands online. First, Dick.
Yeah, just to follow up, and maybe more for the larger audience, just to make something clear. So the machine learning is used for two things, but one of them is not scheduling. So it's used for optimizing the RF links, and it's used to predict future packets. But even if you had no prediction whatsoever, and you were just scheduling things as they came, as they showed up, or maybe your prediction is horribly terrible, and you're just scheduling and routing packages as they show up, it's still an optimizing algorithm. Obviously an NP complete problem, so I won't say optimal, but an optimizing algorithm that's totally, symbolic, declarative, prescriptive algorithm with guaranteed runtime. It's not. There's no machine learning component to that. So we'll do better with better predictions, and therefore better as you learn over time. But it still performs very well with no prediction whatsoever.
Okay.
Over.
Okay, thank you. And there's one other hand, Ola Duradola.
Hi, my name is Ola Drodola from Source Satellite Technology. Just wanted to question, in one of the slides you showed, you identified bundles having sub-components, creation time, source, destination, size, deadline, priority, and type. I just want to know whether or not you have a limit on the file size itself in order to be able to determine whether or not you actually fragment some data if it's too large, or whether or not you will have a limit to that size of data? Thank you.
Right now, we're having a limit to the size of data there. We aren't doing any fragmentation.
Thank you. Cheers.
Okay, thanks. It looks like we don't have any more hands online. I'm going to quickly poll the room to see if there's any questions here. Okay, thank you so much for your presentation. Next, we are going to have JPL. We have two members of the JPL team here to present. First, we'll have Felicia Sanders presenting on the status of Deep Space Network DTN operational infusion, followed by Jay Gao presenting on the DTN ION open source development and status. So first, Felicia.
Thank you. Great day, everyone. Again, my name is Felicia Sanders, and I am the Deputy Manager of the DSN TTNC End-to-End Data Services Office. My office provides programmatic DSN oversight of the DTN infusion effort, along with oversight on many of the other ground-based subsystems that are used to provide DSN telecommand services. Next chart, please. All right, so starting off, I'd definitely like to acknowledge the small JPL village of engineers that continue to play a large part in engineering, developing, validating, and delivering the DTN node to DSN operations. This team is responsible for the work that I have the honor of presenting today. So we'll go on to the next slide, please. All right, the DSN was tasked to implement the full DTN capability over 3 phases. Phase 1 of the infusion effort was delivered to the network in May of this year, with the primary goal of implementing the DTN capabilities necessary to support the Korea Pathfinder Lunar Orbiter, or KPLO, mission. To ensure compatibility with KPLO, ION version 3.7 was inherited to ensure we remain compliant with the BP version 6 protocol that was used by KPLO. The phase two effort, which is now in progress, will upgrade the DSN node to service multiple spacecraft, along with implementing those DTN capabilities that were not necessary in support of KPLO. And then our third phase of our development will include updates to permit the DSN DTN node to interface with other SCAN network DTN nodes, where we should expect to exercise bundle and contact plan passing between the nodes. And of course, we could have additional development phases as standards evolve. Next chart, please. Now, to recap the DSN at a very high level, the DSN consists of 3 operational complexes at Goldstone outside of Madrid, Spain, and a complex outside of Canberra, Australia. Each of those complexes is equipped with a 70-meter antenna and several 34-meter antennas that are used to track spacecraft in deep space. It is important to know that as telemetry or signals are acquired by those antenna, that telemetry flows back to the Deep Space Operations Center at JPL, where communication from DSOC at JPL is established with many of the mission control centers around the world for the delivery of telemetry and command services, among other DSN services. It was the decision of our task to deploy the DTN node at the Deep Space Operations Center at JPL This deployment was completed several months ago and is currently being used to support the KPLO mission. I should point out also that as we learn more about operating the DTN node at JPL, we acknowledge that there may be a need to deploy additional DTN nodes at each of the complexes in the future. That's a decision that we'll make at some time in the future. Next chart, please. So in terms of the KPLO high-level data flow, we have our DSN DTN node deployed at JPL. The KPLO project also has a total of 3 nodes. There's a single node, DTN node, on a payload on board the spacecraft. And there are also 2 additional ground nodes. One DTN node is positioned in the KPLO Mission Operations Control Center, and the other DTN node is deployed at the Electronics and Telecommunications Research Institute, or ETRI, where the DTN node on board the spacecraft is controlled. I'd like to point out as well that all DTN LTP return communication is first passed off to the KPLO Mission Control Center, where any DTN LTP return segments are encrypted and then sent back to the DSN as CLTUs for radiation to the spacecraft. Next chart, please. So I'd like to give a little bit of a status on where we are with our in-flight interface testing with KPLO. As many of you are aware, the KPLO spacecraft was launched on August 4th, and I'm very happy to report that last month the DSN and KPLO project implemented and completed our first successful in-flight demonstration involving DTN on a lunar mission. So we're pretty excited about that. During this test, there were 3 applications that were successfully exercised. The first being the message transfers. We also exercised image transfers. And we also are happy to report that we exercise streaming video via the bundle streaming service protocol. Next slide, please. So all data that was transmitted from the spacecraft was received as expected for all of the 3 applications that were exercised. However, there are a few noteworthy observations that we should keep in mind as it relates to the bundle streaming protocol service. Again, BSSP worked well, and all data was transferred from the spacecraft and it received on the ground as expected. One of the things that I'd like to point out is the DTN payload node and the KPLO nodes on the ground had to be rebooted after the first video playback. This is due to a known configuration on board the spacecraft, which at present time can't be modified by the KPLO team, but work I'm sure is underway to try to remedy that situation. Additionally, video playback by one of the ETRI DTN nodes was observed to be a bit sensitive to the network transmission rate. KPLO is working to improve the playback capability at the KPLO DTN node at ETRI. In terms of simulated ground testing, I want to drop a pin here. I cannot express and stress how helpful it has been to have access to the JPL protocol test lab. under the direction of Leigh and his team members, some of which are in your presence there at Goddard. This helped us with the emulation of the spacecraft DTN node, as well as other ground nodes to help with many of our pre-launch as well as post-launch DTN data flow checkouts. The data end-to-end testing in the laboratories has been extremely beneficial in helping to ensure the best outcome for DTN use in flight. So we're pretty happy with our testing efforts, and this, of course, will continue and is highly recommended for other users. Now, leading up to our next DSN, KPLO, DTN in-flight exercise, there are additional tests that are planned on ground to help clarify and solve some of the observations that were noted during the August 25th in-flight demonstration. And of course, as we prepare for our next in-flight demonstration with KPLO spacecraft and their DTN ground nodes on September 29th, we will also look to including a case where we purposely drop, DTN traffic to see how DTN responds in an in-flight demonstration. Next slide. So in summary, with the completion of our DSN DTN phase 1 effort, the launch of KPLO, the first DTN in-flight demonstration has completed, as I mentioned before. Our second in-flight experiment is planned for later this month on the 29th of September. And our DSN team continues with the development of phase 2 and the DTN Infusion effort, which is planned for delivery in the September 2023 timeframe. And again, because there is strong evidence that pre-launch as well as post-launch ground system data flow testing is so beneficial, we look forward to reconvening our technical interchange meetings with our friends at the Near Space Network to plan interoperability tests between their communication standards and technology lab at Goddard, as well as our protocol test lab at JPL. I think that concludes my portion of the presentation. I'm gonna now, if there are no questions, there looks to be a question. There is a question.
This is Felix Henke. Okay, can I just go ahead or?
Yes, please go ahead.
Yeah, so this is Felix Henke from the European Space Agency, and I'm really excited to see these demonstration activities here and to see really DTN working in the cross-support scenario. I would have a question on the interfaces you have to CARI. Especially, I've seen you are using LTP for retransmission of lost data. So you're providing for the uplink, you basically go back to CARI and they use the usual SLE connections for uplinking LTP segments. So I was wondering what this interface is looking like, or if there are some standard interfaces are used for this, sending this information back to CARI, because it seems very similar to situations we have for using CFDP protocol.
I'm going to direct that question over to Leigh Torgerson, who is in the conference room there. Leigh, do you mind taking that question?
I think this is on, yes. Yeah, this is Leigh Torgerson, JPL. Hi, Felix. Yeah, we have basically a custom interface between the output of LTP in the DSN. It would normally go, the segment would normally go right to the UPL uplink process. However, in the case of the international program, the uplink encryption had to be done in Korea. So we had to put a special piece of software in at the bottom of LTP to send the segments to the remote operating system, ROS, in Korea, where they went ahead and did the encryption that they needed and then put it into a CLTU and shipped that to the UPL process with the normal SpaceLink extension forward frame service, I believe it is.
Yes.
So it was a kind of a unique situation. In the future, we hope that eventually CCSDS will come up with a international standard for allowing uplink encryption when we have to use uplink encryption to be carried on right at the DSN or the NSN, as the case may be. And that would require some sort of a trusted repository that's internationally agreed upon for the security keys and all that. But in the meantime, with the KPLO mission, we learned that we had to, it was a fairly simple system, just mail the segment had to be uplinked to a computer in Korea. There had to be some, it was over TCP, and there had to be a keep alive system, and there had to be IPsec tunnels, and all that business had to be arranged. But it worked out quite well. We do need to think about that in the future as to be something to be standardized or worked on when we do the international DTN communications. That's it.
Thank you, Leigh. Are there any other questions?
There's one other question there. One moment.
Hi, Felicia, and thanks for the update on the Infusion program as well as KPLO. Given that this is DTN Industry Day, my question is what role you think that commercial companies could have in future infusion phases, as well as supporting, international programs as well?
I'd like to direct that question to either Leigh Torgerson or Jay Gao. I believe you also have Jay Wyatt in the room.
Well, we certainly have to have international, commercial participation in DTN. And one of the things that we look forward to is opening up an interface with commercial organizations with the PTL so we can start trying things and experimenting with interfaces before they get to the phase where we're going to have to talk to the DSN. And that insulates the DSN from having to open up the operations network, ops LAN, or the development LAN to outside people. So the DTN engineering network is one possibility, and we're going to be discussing more network connectivity between JPL and commercial organizations. We look forward to that. That's a definite thing to plan. Is that an adequate answer, Felicia?
Yes, thank you. Thank you, Leigh. That definitely is on the books. And we definitely see great benefit in trying to increase our compatibility, testing with industry customers as well. Are there any other questions? If not, I'd like to turn the floor over to Jay Gao, who will give more details on the ION development at JPL. Thank you.
Okay, hi everyone. It's an honor to be here to present to industry on ION status and the development there. So I'm Jay Gao from JPL. Next slide, please. So in this talk, I'll briefly cover, give a brief intro to ION, a pitch, and the development, the current snapshot of where it is. Talk about release and status updates and some infusion activities that's been going on recently, and then followed by a 2-year outlook. At the end, I want to talk about some ion versioning and product line that we're developing, and ion core. So you guess what that is, and we'll be there in about 25 minutes. Okay, next slide, please. Okay, so yeah, I got to look here. What is ION? It stands for Interplanetary Overlay Network. So it acknowledges that there are regional networks that above which the ION can be a glue to deliver data across multiple regions. So it's the most complete implementation of DTN capability to date, and it supports the NASA DTN roadmap. And it's also used internationally for both demonstration, prototype, mission operation, mission planning, and as well as research work. ION has been demonstrated before. It was, I think the earliest instance might be epoxy spacecraft, and also on EO1 and LCRD, which is mostly a ground demonstration. And then recently on the Korean Pathfinder lunar orbiter, and that demonstration combined with DSN, which is now running the very first operational DTN service in NASA scan. Last night we just had a test, and the DTN node that's been the ION instance running in DSN has not shut down since August 25th. So we're running that continuously as a form of stress testing. Yeah. Additional demonstrations are planned for MSU to support the Lunar Ice Cube mission. And on the ground, it runs ION. I think on the Lunar Ice Cube maybe was core flight software. And so, although the flight demo hasn't occurred yet, the ground has gone through extensive end-to-end testing, and they've been very successful. And also, finally, the ION gateway has been on board ISS for 5 years, and it's currently running 374, and it supports up to 40, or maybe actually more realistically, 30, and most actively 5 payload. I'm trying to push that up a little bit, but and they're using the LTP's reliability capability to downlink science data from instruments. And next slide, please. Okay, so a current snapshot. This is where ION is today, and you can look at this diagram from the left to the right. And the color code kind of gave you a sense of progression. On the very left is early design work, or protocol definition work, or research conceptual development work. So that involves the research community as well as the standardization body getting together, trying to define a service. And so that will produce capabilities in terms of a design, of a specification. Then we can take that into a software design cycle to build a component implementation, and then it becomes, when it's more complete, becomes a prototype, and then after that we go into a testing and hardening phase, and finally take that into operation. So currently ION is a set of modules that are at various stages of maturity. Some of them are really, as you looked at them, for example, the BPSec refactoring, it's at a point of a prototype, and it's going into testing. And APO has released it early for us so that we can have opportunity to make that available. Multi-duct is a feature that's been used on with the KPLO mission, and it's somewhat of a prototype. And really, if you want, you could give it a little tinge of green because it's been in space. It's also running in DSN, but overall, you can think of it as a feature that's been matured to the right side. And then obviously we have BPV6 that's been running on ISS. We have BSSP that's just proven itself in operation, although we need to do some tweaks. And then LTP has been stable for delivery, reliable services, and BPV7 is kind of coming online, and we're doing ground testing. So the acronyms are listed down there if you want to. This presentation should be available. So the stabilization and maturing of the features is progressing to the right, and this is where we're at right now. Next slide, please. So a little bit on the release status. So this is the most current news since January of this year. First, in May, we released the ION NASA baseline, acronym was IMB. That release is based on ION 411. So it's IMB version 411. And the difference between ION that you can download from SourceForge and the IMB version is that this IMB version has the actual API that allows you to use a real cipher suite. Okay, whereas if you download the open source version from SourceForge, it has a null suite, just kind of bypasses the encryption capability. And we're also, since January, in fact, I think started earlier than that, is that we have been initiating a new versioning and release process for ION, which I'll get into more detail. And the basic motivation is because we recognize there's a wide range of users. There are university researchers who really want to go into advanced research. And then we have mission user who wants to lock everything down, do the most basic, solid, robust thing. So we have two competing interests, in a sense. I think they work ultimately together, but when they actually want to deploy ION, they want slightly different products. So we're trying to address that now in a more formal fashion. And then we also are developing alternative packaging of ION, so that process can be easier. As far as ION 412 is concerned, we originally tried to release that by early summer. We're still in the final testing integration phase. So we hope to cut it this month. But as far as what there's a whole set of updates to it. I'll just rattle off some from my top of my head, and also based on this. There's a set of updates. For example, we have some updates on LTP algorithm to make it more efficient in terms of handling the segments that were transmitted out of order by the underlying protocol. We updated BSSP so that it has a more graceful failure situation and behavior. We also updated some of the ICI module that handles how a user application attaches to ION. And that's actually an interesting case where we're approached by an instrument team that says, well, we want to run two instances of ION as a redundancy and be able to have my application without quitting attached to ION instance 1, use it for a while, detach, and reattach to ION instance 2. And typically in the past, the only way that you can reattach to another instance is to quit. And so we made some enhancements. So now they're able to, without quitting the user application, that they can attach to dynamically change which ION instance they attach, and therefore changing which network that user application becomes a part of. So that's, we got that idea from a real user because that's what they needed. Also, we have some critical bugs found by DSN. They run ION continuously and send about 50 or 60,000 messages for days. And after 3 days, there's a crash. And then we found there's some bugs. They're all bugs. But we fixed that, and I think we'll make it more robust. One of the major updates to AMS is a 10-time improvement on latency. We also have APLs, obviously the beta release of the BPSec. So there's, a whole range of things that we try to improve. Many of these are the outcomes of the ION hardening task, where they did a lot of probing and stress testing and finding the problem, and so that we can fix them. And also we got a lot of help from all the NASA centers, APL helped get the BPSec in shape and enable early release. We talked to Bill on ISS and David Zoller. They found some bugs that we fixed. We have talking to the instrument team. We have DSN testing that tell us how to improve ion. So we got a lot of help. So I'd like to acknowledge the contribution from all across NASA. Next.
Jay,
yes.
Pardon the interruption. There's one question online, Oscar Garcia.
Yes, please go ahead.
Oscar, you might be muted. You can continue, Jay.
Okay, so let me give some status on some infusion activity. As Felicia has already went over, we did a lot of KPLL support, lots of testing campaign. We had some successful first flight checkout, so I don't want to gloat too much there, but the work is still down the road. We did some gateway support, interacting with Bill, trying to support memory issues and troubleshoot other performance issue. We talked with the Dexter deployable vision system. That's a Canadian instrument that has that need to attach to multiple ion instances. We also provide some consultation to the PACE missions in one of their testing consultation, where they observed some behavior from TCPCL, and we came up with some operational concept to work around that. And I also jot down very good notes on what kind of improvement we may need in the future. And obviously we have other infusion activity with Johnson and MSU that'll be going over by later a presentation this week. Okay, next slide.
It looks like Oscar.
Okay, yes.
Oh, can you hear me now?
Yes.
Okay, Jay, well, we have changed some emails some time ago, but about the previous slide, I would like to say that from the IPNSIG, we would be very happy because we are doing some kind of work in the same line of detecting some bugs and trying to fix and detect how they happen. So we would be very happy to establish some kind of collaboration formally with DPL and with your team to move forward and help you in the deployment of ION.
Yes,
Thanks.
great. Yeah, and yeah. Okay. Okay. Leigh has a question in the room.
Pursuant to what Oscar just said, I wanted to mention, I forgot to mention a minute ago when I was talking about commercial cooperation and what have you. Several vendors, shall we call them, some of which with two-letter stock market symbols, called me up and said, hey, we got this ION business and we're trying to figure out how to work it and how to configure it. And so we're more than happy to give tech support in that direction, of course. And we got them started. One was an RNTD project, a local RNTD project that had nothing to do with NASA, but we're more than happy to help commercial industry get ION fielded and working. And the advantage to that is that when the other people start testing it, they find bugs that we hadn't found, or they find use cases like Jay had mentioned that we hadn't thought of, that with a minor tweak to ION could incorporate features that they would need. And the case in point with one company helped us with BSSP because they were doing video. And we discovered when you relay video, BSSP protocol needed a multi-duct capability. And then the other was with the asynchronous messaging services, which we've been testing with JSC for 5 years. We had another company that was interested in it because it's in the requirements document for HLS. We started looking at that and we realized there's a bunch of improvements that needed to be made, and you'll hear about those in a full presentation later in the week. So another reason where we're very happy to work with Oscar or anyone else in the industry that wants to work with ION, work with us on ION.
Mm-hmm. Yep. Yeah, and we value all the inputs. Thank you very much. Mm-hmm. Thank you. Thank you. Okay, I think we can go to the next slide. Okay, so just a short 2-year outlook. Don't hold me to it. You know, I may not make it, but I'm trying to be reasonably ambitious. The next release that we're targeting, the ION 4.2x, that means various minor bug fixes will be required. For 4.2, we obviously have the official BPSec release, and because 4.1.2 will make it available for testing, I think by then we'll really make it solid and shore up every issues that people can find. And so that'll be the official release. We'll have more updates to on AMS. We're doing more extensive testing now to harden that behavior. We also want to formalize the multi-duct support. Right now, it's a compile time feature. It's a little bit of a customization that's required. It's not so obvious to a user how they can enable that. So we'd like to make that a more of a accessible feature. And then, of course, we're trying to update the ION regression test suite and the bench test suite. Right now, there's a regression test we do every time we run a release, but I think there's also, those tests are focused on functional pieces, specific prior bug fixes that must be, that must not break. But for a bench test, we want to focus on creating a nominal setup of different traffic over different convergence layers so that user had a template of what they can exercise in their platform and in fact conduct some form of platform dependent performance measurement. So they can run it on their Solaris box or their ARM single board computer, and they can look at performances and using those bench tests. They don't have to craft their own. So we're trying to shore up those tests. And then in 4.3, we'll have some updates on the CGR-based multicast update. We already have that capability, and we have a regression test case for that. But we haven't gone through extensive tests. For that, we will have to create a much more elaborate topology. And also the delay-tolerant key administration with the trust collective, that will be in the process of hardening and doing testing, and hopefully issue some really good sets of update for that. And another ambitious thing I'll try to get at, and I think it addresses a previous question about interface, is we understand that when you take ION to a provider or a mission, they're going to run it over their own link layer. And the natural place would be LTP. So they're going to run LTP not over the UDP LSO, which is the UDP underlying services that goes over Ethernet conveniently, but they're going to put it over AOS, TM, TC, Prox1 maybe. So we're looking at how DSN does it. I mean, they are a forerunner of how to pioneer and how to do that. And we're looking at how they approach it. And we want to come up with a more general API that allows you to take ION and say, I'm just going to switch out what runs under LTP. So that API, we're working on that. Okay, next slide, please.
Excuse me, Jay, there's, oh, no.
Question?
I think you answered their question.
I answered the question? Great. Okay, so I'm 5 minutes, okay. So I'll go a little quicker now just because the clock is telling me. So as I indicated before, we have a wide range of users. So I'm trying to formalize a different way of distributing ION and packaging it. So let's go to the next slide. I think so I'm going to go pretty quick, but these fine, tiny print lines you'll be able to read at your leisure. We're going to have some product lines, and as you'll see, each will kind of be tailored to different users. The first one is just our standard ION open source baseline release, and which you are familiar with from SourceForge. Is always called ION X.Y.Z. And this is just the code base that we have right now. And it is a mixture of experimental, prototype, and stable features. So our work right now is continuing to focus on maturing each piece based on the priority order of what we see the missions will be using in the near future. So we're going to mature them as quick and as diligent a job we can do to move that forward, so that everything is as solid as possible. So that's what you'll continue to get. Every release, you'll get bug fixes, you'll get updates. And so if you are able to upgrade or pull in the changes for each release, you'll get updates, and that will make ION more solid. Now, we then have a next sort of product line, as I would call a per feature experimental release. So we'll take, and I call it ION XYZ-E, E for experimental, and then you can add a name, feature name. So, for example, the creator of ION, Scott Burley, he's already contributed a feature called interregional routing forwarding, interregional forwarding, IRF, and that is a very extensive and powerful feature, but we don't have the time to test that right now. So what we do is we say that can be an experimental release, and we post that release in SourceForge. So that allows people to, in fact, develop by pulling down the repo. They can fork a copy, clone the repo, and work on it. They can submit, push to it. And we expect these features to usually have a lead contributor who oversees what code gets in, that kind of thing. But we keep that as a playground on SourceForge, so they can continue to develop the code, and they can continue to get community-based testing. NASA may devote resources also to test it. So that's, and also an experimental feature, although it primarily lives on SourceForge, we could have an internal NASA team that wants to create a feature. So on a case-by-case basis, we'll decide whether that internally initiated feature will be put housed inside on GitLab or be released on SourceForge. So that'll be a determination we'll make, each time a feature is originated from NASA. But for the community, all the features are primarily will be hosted on SourceForge. The next slide, please. And of course, our third product line is what we've already been doing. It's the IMB version that has the API for cryptographic capability. And this release is usually just cut on a need basis. If there's a customer, DoD, private industry, or even NASA mission needs that, they'll let us know, and we'll try to take the latest and greatest and cut something that fits their needs. And then this next one is called a long-term support. I call it LTS XYZ with a mission name. So this release is tailored to obviously a mission or a provider or institution that has more strict formal operations requirements, that kind of stuff. And XYZ is really inherited from the baseline ION that this release will be cut from. And I have a graphic to demonstrate that. So basically, a user can come in and request, hey, you have ION 4.1.2 right now, but I really want 4.1.1. So for my mission, cut me a release. So I'll call it LTS 1411 and some mission name. And they also have the options of getting a ION core package, which is a slimmed down version of it. And that can streamline the product to just their needs. So I'm going to go super quick. Time is up for me. Next slide, please. Okay, so this is just a graphical depiction. I really feel like walking up there to point. But anyway, in the middle, you'll see the main product line, the solid blue line. That's where the baseline ION open source code is. We'll march along, make updates, incorporate features. We may have underneath that line, so for example, 2 features that came out. One is internally sourced, one is externally sourced. We can put them in different platforms. For example, the internal one, we may put it on GitLab, but the external one, we put it on SourceForge. They'll go through some a certain amount of time in terms of updates and testing cycles, and at some point they can be incorporated into the baseline. Above that, we have the IMB, which is a derived release from the main open source. And then above that, the 2 projects, they can create a fork and they can even repackage it based on specific versions of ION that they requested. And then from that point on, there'll be a different source code management entity that steps in because we don't manage mission source codes. Okay, we don't have the capability and the resource for that. So what we work on is the open source code base, but we do provide long-term support, quote unquote, in terms of consultation. If we find a bug in the open source, we're going to have to fold it in, and we can work with them and see if they want to fold that into their software. The next slide, please. I want to go real quick. Oh,
there's one question online, okay. Oscar Garcia.
Okay. Yes.
Yes, Jay. Sorry for this short question. 2 topics that we have also been working in the IPNSIG is what the first one is compiling in different platforms in terms of different hardware platforms, because these different platforms require adjustment specific to the operating system and the hardware, of course. And the second is one idea that I've been working for some time is to develop modules that can communicate ION with different programming languages. There is an application for Python, but to make more deployments, it would be great for the different programming languages to have objects or something like that to connect with ION. Thank you.
Yes, that's great. Those are a great idea. And just a very quick thing about the first part targeting different platform. Currently, our main development is done, of course, on Linux. But we, when we do releases, we test them out for Mac OS, Windows platform, WSL2, MinGW. We also do Solaris. And so we try to test a range of platform, but yeah, anything more specific and you have experience on how to custom and tailor those will be greatly appreciated. And we try to, if there were general needs to have support for that in the libraries, we'll try to incorporate that. Yeah, and in terms of your second concept, that's a broader software engineering topic. Yeah, I'd love to get back to you on that and understand how you're approaching the problem. Right now, we're strictly C in a sense, and we do have a PyIon that was some capability to wrap ION codes, Python codes into C, and then use that to interface with ION. But in terms of the code itself, we have not been moving to that point of looking at multiple languages. But I certainly think that's really great. I would like to learn from your experience. I want to go to. Okay. Yes. Thank you. If I can indulge me for a few minutes, hopefully you don't have dinner or lunch reservations. I have just one chart. Okay, actually 2 charts on ION Core. This is something we came by Dave Orozco's at JPL. He's trying to compile ION on a very, very old Windows server. And then he goes, I can't use .configure and automake and all that. I can't even use the Windows installer. So he basically studied the code and just ripped it all out and repackaged it and make his own makefile and restructure the entire directory without changing a line of source code. That's very important. So he repackaged it. And when he repackaged it, I say, hey, I bet people love to see, because when I look at his package, I said, it's much cleaner, frankly. No, I'm not trying to criticize ION, but ION is trying to combine documentation and experimentation and everything. But he slimmed it down so beautifully that I'm definitely, once we put it out, I encourage everybody to look at it. It helps me understand the code, frankly. And so we see the potential of that. Especially for mission, because the mission may come in and say, I'm never going to run CFDP. It's just not in my requirement. Please don't make me do a verification on that software. So I'm not going to fly CFDP, so I don't want the CFDP module. So we want to provide the ability for them to customize a set of features they want in a slimmed down package. And that also allows them to do integration with their own software, because it becomes more accessible for them, simplifies their VMV, which VMV is like very time costly and money wise. And so because ION Core does not alter a single line of source code, you can inherit the benefits that we do on the community source testing. Is simply repackaged. You essentially get the same behavior. I wouldn't say you don't need to do any further testing, but I would say you get almost as good as just having the stock SourceForge download. So right now we support MintGW, WSL2, and Linux. I haven't tried on Solaris. That'll be an adventure. And then our first ION Core package will be this year. We'll go through a DTN Infusion task to put that into the F prime flight software at JPL. So we're going to have an exercise of seeing how this package positively, hopefully, impacts an infusion process with flight code. Okay, next slide is just a quick, please, yeah. So right now, ION Core 411 is basically derived from 411. ION 411, and we include only these modules. As you can see, we only have the LTP convergence there. We don't even have TCP. We don't even have UDP. Okay, and this is because when Dave Orozco is running his instrument team scenario, he doesn't even need those. So he just ripped them out, and he's got them working fine. You can also limit the number of utility, like BP driver. I mean, some utility programs you just simply don't need. So you can, and this is a completely customizable set. It just, right now, this is what Dave needs for his project. So he includes only these. And we hope to have an automated process where you can select and pick, okay, I want these process, do a little Python code, goes in there, pull things, put it in different, and then there you go, voila. And then obviously BPSec's not here because we'll wait for the official release, 4.2, and we'll work on that. Okay, so that is my presentation on ION. Any other questions? Yes, Vin, of course. Always.
It's Vin again. Just so people understand, I don't get to participate as intensely as most of the people in this room to keep up with everything, and hence all kinds of questions, some of which are probably naive and ignorant, but I'm never afraid to ask them anyway. No. This particular description of what you're planning to do sounds attractive in some dimensions because of the narrowing of the functionality to fit needs. So fit for purpose is attractive. What scares me, though, are two things. One of them is the sharding of the code tree and the potential difficulty of propagating bug fixes to various code branches. I've lived through that in my world, where I won't name a router vendor, but you can figure there's a small number of them. And they've implemented their router code and specialized it for everybody. And then you hear about giant bug, 327, and you call them up and you say, so have you fixed the bug? Yep. So in which code branch? Well, the XYZ one.
Yeah.
Oh, that's too bad because I'm running XYW. Oh, well, that's a change order and that'll cut you right. So I do worry about that. I hope you worry about that, and maybe you've given some thought to what to do about that.
I worried more now, but I do worry a little bit. I have a hand waving notion of it, but I do think what I was thinking was for experimental branches as well as mission branches, the LTS, there will be what we call a shepherd, someone who's technically plugged into what's going on with ION, and they can say, I see that commit that you have. What is that? And then we can have more of a human interactive way of pulling thing in. But once they fork and they start putting customization for the mission, there is that danger of then you just, it's going to be very labor intensive to pull in a fix. So I'm cognizant of that, although in my diagram, if you roll back about two slides, you'll see this naive pull fix arrow that I drawn from the main line back into their code line. I mean, that's, like you said, that may not be a easy process. That might just be very intensive. So I should be worried about that. Thank you, Ben.
Well, here's something else to worry about, and that's interoperability. This network isn't going to do its job if all of the various pieces are so diverse that they don't interwork with each other, or they don't interwork with the bundle protocol forwarders. So somehow we have to pay a lot of attention to that. Otherwise, building this backbone network and running it and operating it won't serve its intent. Yeah. Which is that all of those things that have been shipped out there can be supported.
Yeah, yeah. I do, for example, if you have a network and one of the node don't have multi-dock, and you were thinking, I'm just going to flow BSSP through these 3 relays and get to my end destination, how do you know they don't have it? They don't have it because they thought they don't need it. And so, yeah, it's a balance of, first of all, how do you know what the player's capabilities are? We don't have discoveries like Handshake that talks about, okay, what kind of RTP are you? What kind of RTP am I? And negotiate. A lot of it might be, at least in the early stage, sort of a manually figuring out what people are. Yeah, I don't have an answer for that. I don't know how to deploy it in such a way to minimize that divergence of I think if you're a relay mission, if you have a requirement to do that, you will need to. Please take over.
All right. No, come here. All right. Look, this just seemed easier, man, instead of handing the hot dog around. So one answer to the question might very well be to distinguish between edge devices that are performing a function, have people on board, or have scientific experiments, and things that will, let's call them routers just for the sake of argument. Their intent is to be a relay network. And so we might ask ourselves, how do we make sure that the relay system functions as opposed to relying on nodes that were intended for scientific purposes and everything else? Right. If a scientific mission gets turned into a relay, that might mean uploading new software and functionality so that the relay has the ability to interact with a variety of different specialized edge endpoints. So maybe that's how we should think about it, so we don't end up trying to make cats and dogs, interoperate in ways that they might not be able to do.
Yes. I'm starting to look to Keith's direction, because TCSDS might create a profile for a service provider. For example, if you're a relay orbiter and you have a charter to support relay, you better fly multi-duck, you better fly certain things, even if it's not your own scientific primary goal, something like that. Something to get that into the requirement chain, because I think working with mission practical experiences, the comeback line is always, it's not in my requirement. And then you're like, well, okay, what can I say? It's not in your requirement. There's no budget for it. So, right, something that has a governance over what people commit to fly. Yeah. Yes. Thank you, Vint, and everyone here. Any other question?
Yeah, I have questions. Yeah, so this is Blake LaFuente from GRC. So you talked about testing with Ion Core and sort of working different operating systems, but if it's meant for flight, I just want to know what kind of hardware you're testing on. How low level are you going for this work on CubeSats or anything like that? I guess how low can we go?
Yeah, right now what we're testing when we release these things, I think it's Ohio University. I don't know if they're online, but we have basically test bots that runs 2 versions of Ubuntu, right? The 22 and 20 right now. Runs Solaris. We're trying to run Solaris 11, but that's mostly, a lot of it is based on DSN demand. And then we run Mac OS, I think 15.2. So we have, there's a range of test bots that we try to run things on, trying to be, looking forward to new releases at the same time, cover a little bit like older systems. Yeah, it's a little bit of a mixture of those. And if you have any, like for example, I personally compile them on ARM Raspberry Pi 4. I was trying to, Leigh Torgerson there compiled on the ARM64 Ubuntu on a M1 Mac running a VM. So, if there's emerging a platform that's very popular, we include it. For example, we're moving into WSL2 because of MinGW, just like very few people. Okay, I mean, we can look at SourceForge and get the download statistics. It's pretty low. We know what people are downloading.
So I guess following up on that, then why are you sticking to SourceForge per se than say GitHub or some other open source platform?
You know what? I don't necessarily know. I think that's sort of the contract was set up that way because Ohio University manages that through a NASA contract, and that was the platform they use for distribution. I don't really know the pros and cons and what led up to the choice for that. So, but we can find out. Yeah. Okay. 18 minutes over. Thank you.
Thanks, Jay. Thanks, Felicia, and congratulations on the KPLO demonstration. So we are breaking for lunch now, scheduled to begin 1:30 with a demonstration. Thank you. Welcome back, everyone. Hope you all had a good lunch. So we're going to start off with Alberto Montilla, CEO of Spatiam Corporation. Alberto will be providing an industry demonstration.
Okay, hello everyone. Good afternoon to those here at Goddard. I hope you had a pleasant and fast lunch, and I also hope it was a light, so you don't suffer food coma today. And good day for those that are online. My name is Alberto Montilla. I am CEO of Spatiam Corporation. We are a startup aiming to contribute to the creation of the interplanetary internet. And today, we are going to do a demonstration of the capabilities of our DTN network platform. So let's start. First, we are building a DTN network platform with the goal of creating networks that are operational. Operational by, for example, having the capability of supporting multiple administrators from agencies and from commercial companies collaborating in the same networks. Also networks that are multi-implementation. That means different implementations of the bundled protocol. We believe in standards, but at the same time, we also believe that innovation comes from different angles. So why not having implementations that are, using a combination of implementations, pretty much how, internet works today. And the third one, networks that are integrated into mission operations, because at the end of the day, that's a large part of space operations. We have a portfolio. The DTN platform is composed by, a manager, DTN nodes or DTN managed instances, as well as CLI for operations. I'm going to get some detail into that. And it is currently being used by the IPNSIG in the IPNSIG terrestrial network, as well as parts of it has been tested with the ESA OPSAT in collaboration with DTN and some other organizations. It was tested last year. So without further ado, what I'm going to demonstrate is basically how the three main components of the platform operates, starting with the DTN manager, which is the manager of the network overlays. Then the managed instances. These are basically the DTN nodes that are exchanging or forwarding data, and at the same time are managed by the DTN manager because they are part of a network overlay. And last, this DTN CLI, which is basically a way, an asynchronous way to operate with the nodes. And you will see it providing more granularity into the operations. So now I'm going to switch to the live demo. So this is a demo time. What you see on the screen is the DTN manager. At its center is the concept of the network overlays, which is a logical construct in which different nodes forward information and different endpoints send application traffic. So in this dashboard, you see there are several networks. I'm going to go and create one network from scratch. And for this demo, we're going to say this is the LunaNet demo. And demo for NASA DTN Industry Industry Day. This is a logical construct. You see down here, it is created. If I click on it, it doesn't have any node. It has one user, but it has an identity, and that's very important. It has a network UUID. That's the way the system will know which network we're talking about. Think of it that I'm showing you a UI, but all these can be instrumented through APIs. So the way, for example, a mission control center on a higher hierarchy node would talk about a specific network is through the network UUID. In addition to that, you see that it has a network access, and this is basically giving control of the network for control and visibility of the network to other parties. So for example, if you want another organization or another person in your organization to have visibility, basically you go to network access and then you can add. Right now it's just me, but for example, what I can do is I can add Alberto Jr. The same way you will be able to add organizations. So saying, hey, there is a network overlay in which two organizations are cooperating. That's the way you give access to view or to perform administration functions on the overlay. Let's go back to the nodes. The additional action, the first action you can do is to add your first node to the network. And to add the first node to the network, first thing is you add the endpoint ID. So let's say this is node 300. IPN scheme, of course. The external IP address, we don't know it, so we'll say it is an unknown address. If we know it, we can basically put it there. The system will discover, very likely discover the IP address. And then the network port, this is very important. This check, we're telling the system that this node that I'm creating, it's going to be managed by the Spatiam DTN manager. So it has an Spatiam AMI and Spatiam image. Then we define convergence layer and the DTN implementation. In this case, I'm going to choose ION. So this is meant to be, as we said at the beginning, multi-implementation. Right now, ION is fully supported. We are working to finalize the support on micro DTN, and we can add, as needed, other type of implementations. Let's say HDTN as next. So I go and I add the node, and this takes a little bit longer time. Node is added, and you see here that I get this information You see that the system is telling, hey, this pending, the node has to be initialized. What that means is that I have created a logical construct, but the node is not created there. And I can go and add a label. Let's say this is the Earth node. Again, consider that all of this can be instrumented through APIs. I'm just, doing the UI because it's easier to see. And then I can go quickly and add a second node. And this node, as you may imagine, I'm going to say that this node is on the moon. So this is the moon node 1. I could also choose ISS, but let's continue with the LunaNet demo. There are multiple actions I can take on it, but very important in a similar way as there is a construct around the concept of the network overlay. There is also a construct around the concept of the node. And for example, each node has a UUID, which is the unique identifier for that node in the entire system. So these nodes are logically created. I created the overlay. What I'm going to do now is that I'm going to go and also create from scratch the instances, the physical nodes. And for that, I'm going to be using AWS. I'm going to go quickly and fire up some images that basically are going to turn into nodes and are going to connect to the manager. We right now have images, they are still private, but we have images based on Ion that works on AWS. We also have images that are supported on embedded devices so that they can be deployed into multiple elements. So let's launch an instance, and this should be pretty quick. So first one, let's say this is the Earth node. And I'm going to pick one of my AMIs. This is an image. It's just an image like any other image that has Ion, our Ion implementation. As you may imagine, it has Ion, but it has our stack for management. I select a security group that already have the necessary firewall rules to allow for communication. And then on the advanced details, I'm going to give a couple of commands just to tell the system who this node is. Okay, I'm going to set up this node as the Earth node just by passing the UUID. I launch this instance, and I'm also going to go ahead and create the second node. Need to copy the UUID of the second node in the same way as I did on the first. And then copy it here, and voila. So it will take, consider 2 or 3 minutes, and these are samples. So instead of waiting, I want to show you a couple of additional information about the manager. And for that, I'm going to enable demo mode, so I don't expose information I shouldn't be exposing. And I'm going to be going back and select the IPNSIG network. So this is the IPNSIG pilot project working group network. It has 28 nodes, around 12 administrators. Potentially might be the largest civil non-agency network out there so far. And people from multiple countries, they have their own implementation primarily, and this is because where we started from, all the implementations are using Ion, although we recently integrated micro DTN as an implementation. I think there is 1 or 2 nodes here right now that also uses, the TCP convergence layer. So those nodes are active. They are, sending traffic. There are applications, and as you see, because I can view the network, but I'm not an administrator of any of these nodes, I cannot take any action on them. So now let me go back to the LunaNet demo, and let me disable demo mode here. And now you see that the nodes are up and running. Okay, so what did we do? We created the overlay, we created the logical nodes, we created those physical nodes, in this case in AWS. They started and immediately called home from their default configuration to update their configuration from the central manager. So what we're gonna do now is look at the third feature of the platform, which is the CLI. On the CLI, what I can do here is that by clicking that button, I can get to the Spatiam CLI. And the Spatiam CLI uses a prototypical IoT architecture with an IoT hub so that you can have asynchronous messages between the endpoints. And I'm gonna launch the second one as well, right here. So this is a CLI, and as you see, it is telling me that the node is online and it's identified by the UUID. If I run the help command, it's basically telling me all the stuff I can do on the node. Operations like understanding the health, understanding the status, the version of the image that has been loaded. Through the IoT hub, you can have, and then that's a part of the interesting piece, which is through the IoT hub, you can have a device-wide information like what is the default version I want each node to be running, which you could enforce or not. And then some application-specific commands like BP source, BP sync, and BP trace, etc. So first thing I'm gonna do here is identify, sorry, let me go here. Issue the identify command because I wanna know which node this is. This is node 300, so this is the ERD node, and I'm gonna identify this node, which is, should be node 301. Okay, and then the real test, see if we can exchange information between them. Let me get this probably a little bit bigger, right? And then BP source. So basically issuing a basic command, it's received on the other side, and the other side can basically reply in the same way, which I'm not gonna repeat. If you want to look at more details, and again, this is for illustration purposes, you can see that if I do a cat IPNRC, you can see that each of the nodes from scratch were able to get the proper configuration, contact plan, the proper outlook, even CFDP is pre-configured so that you can use CFDP as well to send and receive files. So with that, let me go back to the presentation. So we saw through this basic demo, the capabilities of how the DTN platform could help operationalizing. It has a default contact plan. Through the APIs, you can update contacts on the system so that you can add as soon as a node is added, for example, contacts get updated in the different nodes. And that's great. I want to show you, before I go, one more thing. And this is about how, by operationalizing the network, you can enable additional applications. Sorry. Let me try to solve for the resolution thing. Okay. It's not appearing here, so it's a bit confusing. Sorry. Which is how by operationalizing the network, you can add applications in a much easier fashion to do interesting stuff. So this is one of the experiments we did, and it's about Avocado Phone. Avocado Phone is nothing else than allowing there you go. It's a DTN application that allows any telephone user, any user of the telephone network to communicate via DTN. And the name, I love avocados, but the name comes from the color of the phone that was used for the first phone call to the moon. The architecture is very straightforward. There is a telephone, as we call it the Spatiam connector, is a connector between the telephone network and the DTN. So basically, on one hand, it is talking to the telephone network. On the other hand, it is a DTN node. And of course, there is an application that maps the two. And then on the far side, in this case on the moon, you have an Avocado Phone instance, which is a DTN node that has a DTN application that is composed by the telephone logic as well as the user interface, the UI. For this demo, what we have is we have simulated basically a more complicated or complex contact plan in which there is a series of satellites that has polar orbit. They have 15 minutes windows, or they have a 15-minute pass with 5-minute contacts, and then the connector would go from one of the DSN stations. And in this case, we assumed that each of the DSN stations would have its own DTN node. And then each satellite would be a DTN satellite. That part is emulated. So what you're going to see on the manager is just the two external instances, the Avocado Phone instance and the connector instance. So let's go back to the manager. And I go to a network, and here I want to just show you that this is the overlay. Spatiam connector, Luna rover. We could have the other 10 nodes. We didn't add it for cost and simplicity, but would operate exactly the same way. And from here, you can launch the Avocado Phone client. So this is, keep in mind that this is the moon side. This is what the user on the moon, the user on Mars would see as a client. They would see a series of conversations, and then inside the conversations, whatever is sent. And then let me get my mobile phone because I want to do this as real as possible. And this is my mobile phone live. And what I can do is I can do the same thing. Hello from Goddard. This is a plain vanilla SMS. And then we are lucky, we are in window. Actually, the window is just starting, so I just received the hello from Goddard. And I can say hello from the moon, sorry. So this side DTN, this side SMS. So let me show you what happens when you are not in window. We're not going to be able to experiment it because the window lasts 5 minutes and I don't have 5 minutes. When the system sends a message or any user sends a message, the connector would get that message and would query, in this case, a CGR process that has the contact plan and say, hey, tell me the estimated arrival time for this. That's the computation. And that, for illustration purposes, is sent back to the user. So every time I send a message, I receive a message back telling me, this is what you're trying to send, the content. This is the expected arrival, which depends on, the contact plan. And then this is the bundle route that is taken. And that contact plan, currently, we are updating it every 6 hours so that it's continuous. We can, use it for forever and ever. Then when on the client side, we also send that metadata where you can see basically the same information on the moon on the moon side. So when we think about the potential applications of this experiment, it's basically pretty straightforward. It's there are a bunch of IoT platforms today that are based on telephone numbers, just because of the fact that they use the mobile network. Well, they can be extended very easily to support to DTN. The second is as experimentation on real-time type of applications for in delay and disruption tolerant environments. Think of it as using it as a test bed. And then, farther down the road, enabling true deep space communications, when we think about Mars, where there is no other option than going this way. This example use, a telephone and humans in both ends, but, it could be machines very much the same way as it is on Earth. So with that, I want to say thank you. Without, I didn't want to leave without, giving you the phone number. You can try it yourself, so it works, and you can experiment with it. Thank you, and very happy to, answer any question, concern, any comment.
Howdy, Keith Scott. In the CLI, can you get it? Presumably you can get in and edit all of the ION config files. I know, for instance, I noticed that you had endpoints for 1, 2, 3, 64, and 65. Are you limited to those or what?
No. You can actually, through the manager, you can add custom contacts. You will be able to edit. Right now, that functionality is not implemented. Mm-hmm. But I think the level of how operational you want to make it, that's the part that we are exploring to see how far, because putting it on a CLI is something that might break existing operations. I don't know, how far you want to go. But technically is, right. Is very feasible.
And your default contact plan is just always on
right now, yes.
All of the things?
Right now, yes. The whole idea is as each node and each network is identified, you can do templates, pretty much like the cloud automation. You can do templates where you say, for this network, this is the default contact plan, or for this type of device, this is the type of contact, the default contact plan.
And then and when you add nodes to a network, you push the modified contact plan out to everybody else?
Yeah, so the thing is right now, and this is where we are versus where we want to be. Right now, either you use a Spatiam image, where, it's basically call home based. Mm-hmm. If you don't use a Spatiam image, we have a code. It's not an SDK, but we have code that can make the link to this interface between ION. Yeah. Where we want to end up is doing fully asynchronous management. And the reason we haven't moved there yet is because, the reference implementations are not mature enough yet. So, we have been experimenting a lot with AMP on ION, having, conversations with Ed and his team to get to a point where we can implement that reliably. But I think that's the end point where instead of loading an entire contact plan, all you say is add this contact, remove this contact, add this out duct. And that's where, it's basically make it command by command based instead of load this contact plan, which it could also be possible, but, you shouldn't need to reload the whole thing just to add or remove a line.
Okay, and that setup script that you were running, that's the call home script? Yeah. Which essentially says, call home, use this UUID, pull all of that config information out.
Yeah, and there are other things like, because the way the CLI works is in parallel to it, because keep in mind that you are not doing SSH, right? So as part of this construct, it performs this IoT hub connectivity, because the system checks also, hey, it checks with the manager for configuration, but it also checks to the manager through the IoT interface to say, hey, am I on the latest version? Am I on, and those operational things is a, slightly different interface.
Okay. Thank you.
Okay. They couldn't. Yeah. Hello.
Jay from JPL. You provided a estimation for the bundle delivery time, basically. Two questions. Do you simply model the contact graph, mathematically compute that? Or would you be able to take into account traffic conditions?
That's a great question.
Also, second follow-up was, actually, I forgot my second question, so go ahead, just answer that.
Okay, let me start with the first one. In this crawl, walk, run approach, what we said is, hey, let's give an estimation that under normal conditions it will be accurate. It's like going to FedEx or UPS and it tells you it's going to be 2-day delivery. You don't know if it is 2-day plus 50 seconds or not. So what we're doing technically is that we have a CGR process, which, by the way, is not the same CGR process that ION has. It's different code, but it's the same logic. And we queried. We load it to the manager with the contact plan, and we queried and say, hey, when is this, going to be delivered? But it doesn't take into account, because you are not querying the machine itself, right? Or the router itself.
It hasn't appeared to me, so thank you.
This is Bill Polchuk at JSC, ISS, JSL. So maybe this kind of follows up Keith's question, but I saw you created the nodes in the demo and you assigned them LTP. Where did the connection between them happen? How do they get connected to each other? I didn't see how you did that, or maybe that was behind the scenes.
No. Right now it's behind the scenes, right? Okay. The moment when that's the part of the beauty of the cloud automation. The moment you initiate a virtual instance, you can tell additional commands, and these additional commands are basically, CLI directly into the machine commands. And what we're telling them is, hey, run the bash, which is the first command, and the second is run the setup script, and this is who you are. This is your UUID. So automatically, what the instance does is basically today it issues an HTTP request to the manager and say, hey, manager, here I am. This is who am I, and hey, IoT Hub part of the manager, hey, this is who I am, and they tell him, hey, you are on a, you need this later, you need this version, and this is your configuration.
Okay, so you created those nodes and ran that setup, and that's what created essentially the contact plan between those two nodes and the LTPRC file.
Right.
Okay.
Right. All of that is done by the manager. It's just that it's
in that command.
Yeah.
Okay.
There is one question online. Scott Burley.
Hi, just a comment. I think there is a contact plan synchronization.
We can't hear you. You're coming in faint. Okay, you're good now.
It's okay. There's a contact plan synchronization protocol that I think is implemented in ION 4.1.1 that automatically propagates a contact plan change made on one node to the other nodes in that region. I think that may be in 4.1.1, or it may only be in the feature branch for interregional forwarding. But the mechanism has been developed and tested anyway. So I think that's a way to address the Keith's question from a little while ago.
Yeah, indeed. One of the things we are trying to do, God, is we, in some areas, and management is like one of those, we are looking at something that would work today across implementations. So, this is something that, as far as I know, it's only available on ION. It's not available on, any other of the other implementations. So that might be the end goal. So it might be great for us to experiment, and we will do that. But in terms of, a product, probably, we're not there yet.
Sure.
Thank you very much. Thank you. Get this out. Oops. Thank you.
Okay, thank you, Alberto. Philip Baldwin was watching remotely, and he's sorry he wasn't able to be here, but he did want to mention that this lines up with our 5G plans and some of the upcoming demos we're doing with cell phone technologies. So, okay, so next we have someone that doesn't need an introduction, but I will try my best. Please welcome Vince Cerf. He's Vice President and Chief Internet Evangelist at Google. He's also visiting scientist at the Jet Propulsion Laboratory. He's often referred to as one of the fathers of the internet, and we are lucky to have him here today. Thank you.
First of all, I don't know how lucky you are to have me here, but I appreciate the opportunity. I don't know about you, but I'm really excited about what I'm hearing over the last day and a half. I mean, there's the level of energy and the concrete things that people are doing. I'm really encouraging, considering the 24 years of evolution of a lot of this stuff. I have to say, Alberto, that was an astonishing demonstration, and the fact that it was the CEO who did it and it was live is nothing short of spectacular. So, you know, you get A triple plus for that. That's very convincing, very encouraging. You don't need to hear from me for very long, so I'll keep this fairly brief because you have more important demos to see from Leigh Torgerson and Lara Suzuki. Now, I'm listed up here as Google, and it's true, I do work for Google, but my interest in all this precedes my employment at Google, and so it's important that you know that even though this is Industry Day and there is going to be some Google-related stuff, I just want to emphasize that my interest is broad and deep for all of this, not only at JPL and NASA, but at the IPNSIG as well. I want to make a couple of comments about what I heard yesterday, and I hope I want to emphasize the importance of what we heard between people who are trying to use this stuff and the engineers who are building it. We really need to get them more connected. We need the feedback loop. The engineers want that feedback loop. When I was running engineering for the MCI mail project, the VP of operations and I had adjacent offices, and I made my engineers wear pagers along with the ops guys. So when things broke, we woke the engineers up at 3 a.m., just like the ops guys were. It was amazing how much incentive that created for getting things fixed. And so I'm a big fan of increasing that level of interaction. So if there's something that we need to do to increase the opportunity for ops and engineering to work together, let's do it, whatever that is. Now, yesterday, I came away with the impression that it was hard to get information off the International Space Station about conditions arising in which the systems didn't work well or broke. We need to do something to fix that somehow. If there is a policy issue, I want that escalated. And if that's not something that can be escalated through the DTN working group, I will escalate directly to the associate director. Because I believe that we need to make sure that we don't allow policy to interfere with our ability to build solid products. So that's a commitment I will make as a consequence of these meetings. I also want to note that unless we use this stuff, we won't really get much of a sense for how well or how poorly it works. And so it needs to be in use all the time. And we're starting to see more and more of that. The IPNSIG working group, the project working group, is increasingly running all the time, as Alberto was just describing. So I have an idea which may turn out to be stupid, but I'll try it out on you anyway. Some of you may know that a long time ago, I registered something called sol.int in the domain name system. Int is supposed to mean international, but I thought since it's only INT, we could call it interplanetary and nobody would know the difference. Sol.int, since it's registered, could allow us to build domain names that are, you know, earth.sol.int, moon.earth.sol.int, and so on. We could have email addresses that are drawn from that domain name world. Now, some of you know that there's this concept in the internet email system of MX for mail exchange. What that means is you can map what looks like an email address to go to a place, a host somewhere, that isn't the destination. It's the intermediary, the proxy, the mail exchange. And so you could easily imagine being able to build a mail exchange which receives mail using SMTP, but in fact is capable of running the DTN protocols and could go to some other mail exchange, which is also, running DTN, and just move the email back and forth. And so I could imagine just deliberately creating some email addresses and then using that system, including the intermediary DTN part, in order to carry on our work. And so I don't know whether that's crazy or not, but I'm looking for things that will allow us to use this in real, depend on it. Until we depend on it, we won't care. And when we do depend on it, we will care a lot. And that's the only way to get anything done. So that's another possible suggestion. For the past several weeks, there's been a lot of discussion about routing and naming and forwarding, and in the back of my mind, scaling. And one of the big worries some of us have is that flat namespaces and flat address spaces and so on often have scaling problems. We have a problem with the interplanetary network and its principal problem of speed of light delay. And so freshness is a big challenge. And the idea of having a central database which is up to date more or less all the time is not your friend in this environment. So figuring out how to make sure that our architecture really will scale properly and provide for mapping of names into addresses and addresses into routes and so on is still, for me anyway, a worry. I'm also concerned about the situation where we have nodes in the interplanetary network that are moving around. And there's two kinds of moving around. One of those kinds of moving around is I just move from one radio link to another. That's theoretically the easy case. But it's dynamic, and so we have to figure out where is it now? How do we discover where things are and how they're connected? The more complicated case is the one where it started out on Earth and it went on a long trip and it ended up in Jupiter. And the question is, what has to happen to make sure that that node is discoverable and accounted for in the places where it ends up, or if it moves around from one region to another? And there's a lot of debate about what's a region. I think I would like to suggest to you the simplest possible definition of region is anything that's part of a region, it can reach everything else that's part of that region eventually, assuming, of course, that connectivity eventually happens. And that simple definition allows regions to span arbitrarily large territory because it's about topology and connectivity. It's not about physical location. A node could be more than connected with or associated with more than one region. Some of those nodes will turn out to be gateways or pathways, passageways between regions, but they don't have to be. It's entirely possible for a node to be part of two different regions and not perform any function other than exchanging data with nodes that are in the regions 2 or 3 or 4 regions that it is associated with. But I think these concepts should work. And if they don't work, I think I want to know why, because theoretically they don't, I don't think they conflict conceptually with anything. So final point that worries me is flow and congestion control. This has been a real problem in the internet world, and that's a low latency world where ping is your friend, and things happen in sort of more or less real time and allow you to respond and react in real time. And in our environment, we don't get to do that. So I am worried about the potential for nodes, especially intermediary relays in the system, to become overloaded with traffic that they can't get rid of because the connectivity isn't available. And just to give you an anecdote, this is old guys like me, that's what we do, we tell anecdotes. So way back in the ARPANET days, literally around 1970, Bob Kahn, who was one of the architects of the ARPANET, came out to UCLA where I was still being a graduate student, and he said, we're going to break the net. And I said, oh boy, that'll be fun. So I fired up a whole bunch of traffic going, this way across the net, and we killed the net within, 2 or 3 minutes. And I wanted to put a stamp on the side of the imp, like you do when you shoot down airplanes. And we kept doing that. We kept killing the net in various and sundry ways. One of my favorite ways was the Mexican standoff. This is where 2 imps, router to you, were full of packets, and they couldn't get rid of them because they were going this way. And nobody had any room for anything, and so they just stood there, and it all froze. And there were a whole bunch of other situations like that. And it turned out that it was really hard to figure out how to fix those problems. We had another situation where we don't have time for this, but we had a swarming ball of packets were converging on 1 imp and killed it because it just ran out of room for anything. And then after it died, they all moved to the next imp. It was like it was like bees, flying around from one, and it polluted the entire network. The whole thing fell apart. I don't want the interplanetary backbone network to fall apart. So we need to make sure we can solve those problems ahead of time. And this is a challenge not only for the engineering side, but it's also a challenge for the analytics side, because we need better models than I think we have today. This is not a simple network of queues problem where everything is mostly connected. This is a system which is deliberately and unavoidably disconnected, and figuring out how to model that well without having an explosion of state space, which is the classic problem in queuing theory, is a non-trivial exercise. So I'm going to stop there and tell you that the real reason that I'm standing here is because Leigh Torgerson and Lara Suzuki, who is a Google employee and very much engaged with the JPL team, are actually doing real stuff on multiple cloud systems, including the Google Cloud and the AWS Cloud, and also the Azure Cloud. So Leigh, I'll turn this over to you and Lara.
Thank you, Vint. I'm Leigh Torgerson. Good point. Anyway, I'm Leigh Torgerson from JPL. First thing I want to do is I want to introduce Lara Suzuki, who's up there, kind of frozen in space and time at the moment. She is, as the sign says, the technical director in the office of the chief technologist office at Google. I've been working with her for 1.5 years, 2 years now, working on various DTN projects and tasks. I want to brag about her a little bit. She's a specialist in applied artificial intelligence and machine learning, federated learning. I've learned a lot about all of those subjects from her. She's an associate professor at University College London. She's based in London. And in 2021, she was named the UK Engineer of the Year by the Royal Academy of Engineering, which I think is a particularly noteworthy accomplishment. So over the years, we can go to the next slide, please. We've talked about various ways of applying artificial intelligence, machine learning, federated learning to helping us with the DTN situation. And we've looked at video, we've looked at a number of things over the last 18 months or so. And recently, with our experience with the Korean Pathfinder lunar orbiter and pulling our hair out, trying to decode what was going on, I used to have a lot more hair up here, realized that machine learning and AI would come in real handy in interpreting watch characters. Now, I'm going to have a quick couple of slides on what watch characters are in case people don't know what watch characters are. Thank you. The watch characters are essentially like debug code that is put out to the terminal, usually on a machine running ION. It's not in-band, it's not bundles like the EdBrain, the DTN amp, and all the things that you need for the moral equivalent of SNMP, the router control. It's put out to the console, and along with the log data from any ion process or application has a problem, it writes its concerns to the ion.log file. And so normally when we're running, we see these, each person who's sitting in front of a console running ion sees these watch characters going across the screen. And when the pattern of the watch characters indicates there might be a problem, you can go look at the ion log. We've got quite a presentation in a couple days by Tayo on some of the things we've been doing to make it easier to look at watch characters in real time. Meanwhile, this is just a quick example. If you, the watch characters are alphabetic, A through whatever the last letter is. If you present a piece of information to the bundle protocol, the BP, to send somewhere, it'll put an A on the terminal. And then when the bundle protocol gets it and accepts it and says, yeah, that's a good valid bundle, it'll put up a B. And then when it decides, okay, it's not timed out, it's not expired, it's a good bundle, it's ready to send below at the convergence layer underneath, it'll put out a C. And then the LTP, in this example, I'm pointing at something you can't see, but the LTP protocol would say, okay, I've got a bundle, but I can put multiple bundles into an LTP block. So it says, okay, I've accepted the bundle. And then when it fills up a block, it puts out another character saying I've filled up a block. And then when it's ready to take that block and put it into segments so that there's an impedance match with the link layer underneath, you know, like an Ethernet with 1400 MTU or whatever, or AOS with a 4090, so whatever the frame length is. When LTP puts out a segment, it'll send out a watch character. And when it's finished with the block, it'll put out another watch character saying, okay, I've done the whole block, send it out. And then there'll be a request to the sender, to the receiver, to send a checkpoint message back. And it's kind of, I tell people, it's like, I'm going to send you a book, but what I'm going to do is I'm going to send you the whole chapter. And at the end, I'm going to say, did you get the chapter? And you send back, yeah, I got everything except page 42. And then I'll send page 42 back to you, and there'll be a little handshake about that. And then finally, when the chapter is done, that's a tantamount to an LTP session. And then there'll be a session closure transaction. And so all these different transactions have watch characters. And if you can see at the very bottom two boxes, one of them says ion window, B, C, D, E, F, G, S, T, G, Y, Z, S. That is indicative, that's a pattern that's indicative of a successful transfer of a single bundle. And on the receiver side, it's slightly different because he's not sending anything, he's just receiving it. So the first thing are LTP watch characters saying, yeah, I got all these segments and now I've turned it into a block and now I've handed it up to the bundle layer. And then the bundle layer says, okay, I've got it and I've handed it up to the application layer. So it's a very tedious debug code. They're optional. You can turn them on and off. You can select which ones you want to see, which is nice. But it's easier to see the pattern of what's going on by watching the watch characters than it is to try to look at Wireshark and decode individual packets and then go figure it out. So if you go on to the, one more thing, the red text, these are all letters. And one of the clever things that Scott did once upon a time when he cooked up this scheme was to make error conditions pretty much punctuation characters, non-alphabetic characters. So when you're looking at a sea of alphabetic characters and then all of a sudden you see a bunch of equal signs and stuff like that, that immediately cues you to, okay, something's up. Figuring out what is up is a whole nother can of worms. Because of delay, you can have, I can send 5 bundles, 6 bundles, 10 bundles out before I get the first indication back from the receiving side. And so the things can be like interleaved and it's really hard to decode and sort out. Go to the next one, please. This will be my last slide and we'll turn it over to Lara. Next slide. There we go. So it's all fuzzy, but you can kind of tend to see if there's the sender and a receiver side by side. And if you're just sending a whole stream of data and there's some errors, you can see the kind of patterns you get, and you can see the punctuation marks. I introduced some errors in here to have some equal signs and explanation points and whatever. And then down below are the ion log entries. And when you start seeing errors, you can look at the ion log and figure out what the errors are. So we spent a lot of time, and we're still spending a lot of time. We did it last night. We're doing it tomorrow night with the Koreans. They changed their relay node at their ground station to a new computer, and they apparently compiled ion incorrectly or something, and we're still trying to debug that. But we're all going blind looking at watch characters from 4 different nodes simultaneously in 2 different continents. So what we decided, what Laura decided, and Laura and I decided to do with her AI machine learning research was to start taking a look at using federated learning and machine language or AI to assist in decoding these things and maybe be an automated way of evaluating watch characters for not only test purposes, but maybe even operational purposes in the future. So with that introduction, I'm going to turn it over to Laura and go sit down.
Can you guys hear me? Yes?
Yes.
Thank you so much. Okay, thank you so much. So as you pointed out, what we wanted to understand is to decode this language, this ion language, and try to interpret what the watch characters they mean, because the sequence of the watch character is really, really important when we are looking into the network. And when we think about watch characters, we could think about using rules to model it. So think about this scenario here, where we try to model what activity a human might be performing. If we try to cover all the cases in rule-based systems, our logic will become too complex and difficult to grasp, especially in edge cases. So what we see here, for instance, if the speed is lower than 4, then it's, of course, is walking. If that's bigger than 4, then the person is running. And then if the person is cycling, what we are going to do. And then if the person is golfing, yeah, what we are going to do about that. So we won't be able, if we try to model everything in rule-based system, we won't be able to generalize, especially to not seen cases, like things that are quite new, we have not seen before. And in our case of watch characters, it becomes even more difficult because the sequence of characters is really quite important. So for these cases, machine learning scales much better than hand-coded rules, because we could just take like those watch characters like exclamation point and all those and try to model and do something about it. But the sequence of what happens after that watch character is really, really important. So the best thing for us to do is to scale using machine learning. In ML systems, we can create a special encoding for each example that we see. It could be an image, it could be a sentence, and that will make our lives much easier. So instead of having those hard-coded rules, we try to see a pattern, and then we encode a particular pattern that we see. But the secret here is that we need a lot of data and loads of data so that we can really see all the possible ways that we can do something about a specific case that we are trying to understand. And the journey to applied AI is really not very straightforward when we think about it. So for instance, if we want to create a recommendation system, for instance, to recommend a course of action, we cannot just model like recommend what I should do if I get this watch character. We first have to understand, with the first use case, to detect whether we have anomalies, like a particular watch character present or not. So that is an AI detection problem. Then we can move into what type that X is about. So is this an anomaly? Is this a fraud? What that means. Then we can then run another machine learning on top of that to see what extent is that X present. And X could be an anomaly, could be anything we're looking for. And then we can then make a prediction on what is the likely outcome due to X being present. It could be a failure in the system, could be a security breach, could be like a loss of data. And then later we can do something about how should we address the presence of X and provide recommendations. So we should like reset the TCP IP stack or do something about what is going on, or to perform some command line operations that will allow us to overcome a particular issue that we have. So when we think about machine learning here on the my left side, we see like the basic flow of machine learning is that we have our training set features. Sorry guys, I have a very annoying dog here. Just give me a second. Sorry, I have two golden retrievers. Sorry, and they were boxing in my living room. Okay, so going back here, so we have a training set features that it's all we are looking for in a data set. Then we have the model weights, so the weight that each one of those features is going to be kept in my model. And I have a prediction function that is going to be a neural network based on the weights that we are passing through a vector or a matrix W. Then at training time, we can have like training data sets that we are going to use labeled information. That is like things that we know, it's a cat or a dog, it's an anomaly or not. And then we are going to calculate the loss of what I'm modeling and compare that with the ground truth. And then we repeat that process until we get an optimal prediction. In the case when the sequence is really, really important, we use a different type of network that is called recurrent neural network. So RNN is a neural network intentionally run multiple times where parts of each run fit into the next run. So I train machine learning now, and then the result of that output of that machine learning output will go back into the system to help us to predict what is going to come next. So specifically, the hidden layers we might have in this network will, what we run at time x0 will feed, the result of that will feed into what we run on time x1. And so we keep doing that process until we are satisfied with the sequence, with the prediction of text that I'm having. And recurrent neural networks are a class of neural networks that give us a lot of flexibility in the way we make predictions. So they are specialized for inputs that correspond to a sequence of values. So where the sequence of variable is also variable in terms of length. So for instance, we want to predict the next 10 characters or like all the watch characters that we are going to see the next 10 or 20 seconds. So we can also vary that out as well. And recurrent neural networks allow us to have a variable number of outputs. We can tell how much ahead we're going to be going in the future. And in contrast to normal feed-forward neural networks, we have those loops between those units. So if I use the word author, then I know, like, for instance, the next word has to be something, for instance, the author is, so you can compose like sentences that makes any sense. And what we're trying to do here is to detect how the language of ION works. So the core of the model consists of a recurrent neural network that will process one character at a time, and we compute the probability of the possible values for the next character in the sequence. And the memory state of the network is initialized at 0, and then as we train the neural network, we start having those matrices of the memory state updated at all time that we see in the future. So it's all about like having the loops, the output, feeding this into the next layer of the neural network. So this is an example of what we have. So we took different IO nodes running, and I'm going to show you an example of an IO node that was running for 3 hours only. So we only have like 3 hours worth of data, but we managed to get something quite interesting. So the ION data scene here, you can see, for instance, in the first column, when you see data set, we have like over 1 million rows. So we have like the identifier of the row. Then we have a watch character. So we can see like exclamation points, the letter S, and then we have the timestamp of at what time that watch character was saying. And then if you see on the right, we see the encoding of that watch character. For each watch character, we have to encode them. Otherwise, we're going to have to create those rules, if this and that, if it is and that. So below, we have some examples of some watch characters that we have. We have the exclamation point, the hash, YD, and then we have that. And then through running the network, we can learn what is the expected sequence that we should see happening. And then the idea is, if we manage to understand the language of ION, we can create an assistant that can tell a mission operator, like, pay attention because in the next maybe 20 seconds or 20 watch characters, we're going to miss a bundle. There will be an error in the network. So I put here at the top, like, I've run this for several epochs, like runs of the training of the machine learning. until I got to a point that I got about like 85% of accuracy, but it's just like with 3 hours worth of data. So think about what we can do if we have like months of worth of data. And at the bottom, there are some examples of what we run. So monitoring the events. So what you see in black is actually the text that we saw at a particular time 0. And then what you see in blue is what the recurrent neural network predicted that's going to happen next. So if I see like those 5 A's and an F, then I can predict what is going to happen in the next few seconds. So it's going to be like a segment of block is likely to be popped up from the transmission queue. And then the idea is that we can extend this as many characters as we want. So we say we have 1 character per second, we can say what is going to look like in the next 1 minute based on what I have seen on the network now. So the idea is that we can create an assistant that can help a mission operator, like, hey, pay attention here. I can detect some kind of anomaly might come up in the future. So that mission operator can go and check what is happening in the network. If that was a false positive, that information can be fed back into the neural network that we can learn to not raise an alert based on what we just saw. And let me just do something here. And you guys can still see my screen, right? So I have like a Jupyter notebook here that I have like some code here that I've used to encode the neural network. And I'm gonna go to the bottom of this. So this is like the implementation of the recurrent neural network. So if you see like on line 682, this is like how we can call the prediction using a neural network, a recurrent neural network. So I'm gonna pass the network here. And this number 10 is how much in the future I want to predict what the next watch characters are going to be. And then I can select a sequence of watch characters defined by the word prime. So for instance, I'm going to run this using the sequence. So I'm seeing like a bundle queued for transmission. Then I can see the bundle is popped from its transmission queue. Then I can see that the bundle is appended to block for the next section. Then I can see the segment of block is queued for transmission, and the block was successfully segmented for transmission. And then I start seeing some G's here. That means the segment popped from the transmission queue. But then I have like some equal signs here, and that means that we had an unacknowledged checkpoint was retransmitted. So if I run this part here, let's see what the recurrent network is going to tell us. So it's going to say to us that after we run this particular watch character sequence, what we are going to get is like we are going to continue having some information that the segment was popped from the transmission queue. If I increase this from 10 to 40, I'm going to see the next 40 expected watch character. So we're going to see a pattern of this normal transmission taking place. If I change this to something different, I can in fact predicting what I'm going to be seeing here. So here I see a normal sequence because I cannot see an E and then see a B happening because that violates the sequence. So what we have here is like the bundle queue for transmission, popped from the queue. Then we have the bundle appended to block for next section. And then we have like those bundles being the segment of block queued for transmission. And then we see the generation of watch characters we are expecting in the next 40 seconds. I would just run another example here. So with this prime that we are saying that, okay, so the bundle was accepted upon arrival and the bundle is good for delivery to an application. And then let's see what's going to tell us what is going to continue happening. So the idea is that it's going to continue happening following the BCT sequence. And then we're going to have like the sequence in which we segment the block and queue them for transmission. So the idea for us is that if we see something anomalous in the watch characters that we are watching, and we are going to be likely to work as an assistant and tell the mission operator, hey, something anomalous might be happening in the next 5 seconds or so. So the idea is that we are working with the system. We can make sure that ML systems, they are aiding the evaluation of watch character because we might miss them in the midst of all those watch characters and link this to ion log events. Because the idea is not only predict what is coming up, but to say, this is coming up, I recommend that you, mission operator, run command X, Y, and Z to fix this problem. So we want to build an assistant. And we want to automate the corrective activity when we detect something is wrong going into the network. And also use ML to provide automatic network configuration and other network monitoring and control functions. So publishing, I'm going to go very quickly to something that is the use of ability learning, as Leigh mentioned. So the idea is publishing ML in space is quite difficult because we cannot get all that data coming down and coming up. So what we can do is like to train our models here on Earth, and this is just an example of a setting up here. And then when we train our recurrent neural network, we can distribute this model across all the nodes of my network. Then we can train locally on that data. And then that data after we train, we can send the model configurations, the model weights back to Earth. And then here we can combine what we learned together with them, like different sequences of one characters and this. We can aggregate that model and create something much better and propagate that back into the network. So we can keep learning on this, avoiding having a lot of bandwidth taken by processing and getting data from space to here. We can do stuff on the edge in space and then improve how we run the machine learning algorithms in space. So this is what I had for us today. So thank you so much. And if you guys have any questions, Leigh and I would be happy to take.
Thank you, Laura, and thank you, Leigh. I'm polling the room right now to see if anyone has any questions. Okay, and I'll check online very quickly. And it doesn't seem like there are any questions. So thank you for your presentation. I would like now to turn the floor over to Kyle Hart and Nate Haynes from AWS's Solutions Architects. They're in person.
They are. Is there a clicker too? Sorry.
No, there's not.
Okay.
But,
They'll track me fairly well. Well, good. I appreciate that. And thanks for the invitation to come talk. My name's Kyle Harton. In the back is my colleague Nate Haynes. We're both solutions architects in our federal group at AWS. And I've been at AWS now for 6 years and supporting NASA in some capacity for the past 5. And it's been a real pleasure. I've got a number of customers that I work with in our federal civilian business, from healthcare to the research, Department of Energy, some law enforcement customers. But it's been a lot of fun with NASA. I can remember my first meeting here at Goddard was with JPSS, kind of on the edge of the facility here. And we were doing a workshop, some hands-on training. And we went around the room and everybody did their introductions. And, you know, it's the name and the program they work with. And a number of the people worked on a program called Gravity. And I was kind of taken aback. I'm like, I knew NASA worked on some cool stuff. I didn't know that they were doing a lot of research into gravity. And it turns out Gravity was just another acronym for something completely unrelated to gravity itself. But it's been a fun ride working with NASA, supporting them on some of the challenges they have with their workloads and how we can use AWS to meet those challenges and enable NASA to be more effective in their mission. So if we can go to the next slide, please. So what I want to talk about here a little bit is, you know, some of you probably have some familiarity with AWS. Can I maybe just get a show of hands? Who has worked with AWS, launched an EC2 instance? We saw that an hour ago. So thank you for that demo. We'll refer to that a little bit. But, you know, AWS, cloud computing platform, I think most are familiar with that. Over 200 fully featured services that we have. And what I really want to talk about today, and I have just a few slides, is how you can leverage AWS's terrestrial capabilities to support your DTN requirements. So we do have some assets in space. These are public, public references. Several years ago, we did the first 4K video broadcast from the International Space Station using an elemental media encoder. That's an Amazon service that we have. We have what's called a snow cone device on board the International Space Station. Think of that as a portable mini storage device with some onboard compute, which could potentially open up some interesting use cases if you have to deploy compute processing nodes with a storage platform at distant locations. And this has also been in the public news lately. We're working on sending an Alexa device on the upcoming Artemis launch. So we've got a couple of things in orbit, but what I will talk about today is how our ground-based infrastructure and networks could potentially support DTN capabilities riding on top of that. So next slide, please. So some of the things, sorry, I'll stay with the microphone here. Some of the things that we've done with NASA that I've been involved with that have been a lot of fun to work on. Some of the work that using NASA ground stations as the spacecraft makes contact with that ground station, downlinks that data. And for some of these missions, they have a very low latency requirement to receive that data, turn it around and process it very fast. And so how we can use the cloud to do that at scale in a cost-effective fashion. And that's one of the key advantages of the cloud is what we call agility and elasticity, where you can move very fast, experiment very fast, and you're only consuming and therefore incurring costs for resources as you use them, and you can turn them off. So if you have a mission and you're only making contact with the ground station for 10 minutes every hour, you don't have to have hot infrastructure for the full 60 minutes. You can consume it for the 10 minutes, pay in for a particular service, we bill by the millisecond for as it ingests that data, processes that data, does level 0 processing, turns it around and sends it downstream. Some other things that we've had the fun with working with NASA on, some high performance computing, some weather modeling and simulation, the long-term storage requirements for a lot of the geospatial data. You can store that in the cloud. And we have a storage platform that we offer 11 nines of durability, meaning you can kind of do the math of what that means. But it's a highly durable, low-cost storage option that can also serve as your ability to distribute that out to people that may need to consume your data. And of course, then the work we've done in supporting the global connectivity for some of these other missions. It was kind of fun in the past couple of years during COVID. We were working with one of NASA's commercial satellite partners to bring the Punta Arenas site online and connected directly backhauled into AWS. And it was kind of like the United Nations with KSAT in Norway, the Telefonica in Spain, their partner in Chile, and how to bring all of that together to connect up to an AWS point of presence. And so that global network, I think, is a key asset that we can leverage. And so if we can go on to the next slide, please. And let's go ahead and hop onto this slide after this as well. That global network really is a key asset we can leverage that you could potentially think about using to architect and deploy DTN-based solutions. So this is an example just to help visualize the global footprint of AWS, and it's color-coded to kind of also show how we've grown for the past 15 or so years of being in the cloud business. You can see we started with 4 regions in those first 5 years, and we're now up to 27 operational regions. And the term that AWS uses to define region is, it's similar to the term that was used in the previous presentation. But a region for AWS is a collection of autonomous infrastructure that has connectivity with the elements in that infrastructure. And within regions, we have a capability called an availability zone that I'll get to. But just one quick comment on this slide. You can, of course, see our global footprint. We have our 4 commercial regions in the United States. And for those that work for the government, you may be familiar, if you're on the IT side, with a regulation called FedRAMP. We have the FedRAMP moderate accreditation for our commercial regions in the United States. If you have ITAR requirements, we have 2 GovCloud regions, one in Ohio and one in the Northwest in Oregon, that meets the FedRAMP high requirements as well as complies with those ITAR requirements. And then for certain missions or certain requirements, you could leverage AWS globally, and we have some NASA examples where they're doing that with international space partners. How can they use space telescopes? It's probably the wrong word, but the Great Telescope. How can they use space assets from other countries to connect up to AWS? And then funnel that data through their AWS pipeline back to their processing regions in the United States. So this is an example of where our regional footprint of AWS is today. And if we can go to the next slide, please. This is kind of a double click, zoom in, a representational example. The arrows point to Singapore, but this is really a representation of any one of our regions that shows how we comprise and think of running our data center facilities. So what we're showing here is what we call a region with multiple availability zones. In some regions, like US East 1, which is our largest and oldest for AWS, which is here in the Virginia area, it's got 6 availability zones, which does not mean 6 separate data center facilities. An availability zone is a cluster of 1 or more physical building facilities that are interconnected, separated by a meaningful distance, but interconnected such that you can run applications with very low latency requirements, but still have a degree of geographical separation within the region. So they get separate power feed suppliers, separate, they're not on separate power grids. There's only like 5 power grids in the country, but they're getting power from separate suppliers, separate substations, such that if there's, a regional disaster that of a certain scale, that will be contained, and it may disrupt one of our availability zones, but it's unlikely to disrupt all of the availability zones in that region. However, for certain mission critical missions, you may want to choose an architecture that is a multi-region architecture, and that's something that's quite common, and that's something we support NASA with. And that's a pattern that the flexibility that our platform supports if you indeed have those requirements. But I wanted to convey, if you're building DTN requirements to support data processing needs from critical and very expensive space missions, you've got a reliable infrastructure environment and architectural patterns that give you redundancy that could potentially meet your mission requirements. And if you're pulling down data to be consumed by science missions that have to process that data at scale, and many of them do this on AWS, if they need 10,000 CPU cores for an hour to process that compute job, that's the kind of business that we are in and can support them with. And a whole range of compute options. If they, depending on the RAM and CPU configuration, what sort of processor type is appropriate. AWS entered the business several years ago, and we have our own line of processors now, an ARM-based processor called Graviton that's 40% more kind of price compute efficient compared to traditional processor models. So a number of options when you get that data into an AWS region that you can leverage to make your compute process more effective. So next slide, please. So more discussion on availability zones, and we kind of hit these points, but to give you an idea of scale, these are availability zones within a region. Again, not a single data center. These are data center clusters of hundreds of thousands of hosts in these facilities that customers can use. Fully connected with redundant metro fiber, et cetera. Next slide, please. So here's an example. Here's a representation of our global network and why I think this might be interesting for DTN type applications. So the green dots, which are a little bit smaller on this graphic, represent our regions, the 27 regions we have online. The blue dots, of which there are more, represent 100 or so AWS point of presence for direct connect. If you're looking at some of the stats, we have another service called CloudFront, which is a content delivery network. If you have to deliver content over the internet, so kind of outside the scope of DTN, but if you have people consuming your data after you've already landed that data and processed it, a content delivery network would be very effective for that. And it's not shown here, but there's 400 or so POPs for that. But for direct connect, what direct connect is are peering locations where you can connect in to AWS, attached with the AWS backbone, and from there ride the AWS backbone to an AWS region or to other direct connect POPs where you may have facilities that also connect to those direct connect POPs. So what this really enables If we can go to the next slide, please. This enables a concept called Cloud WAN. And this is a newer concept. This is within the last couple of years, not the last several years, but relatively recent, where we've enabled this capability that customers can, using local fiber from their particular provider of choice, connect to that AWS POP, and then using that AWS backbone, connect to, not even route their traffic directly into an AWS region, but route it to another node on the AWS network, or route that traffic to an AWS region. You've got that full kind of global networking capability at that point. Next slide, please. What kind of shows this example of different clients, and this is a back office example. This isn't like space specific, but different clients using different connection modalities from different locations. Some are users or sites connected directly in to that cloud WAN, that blue line, that virtual cloud WAN representation. Some are data center connections connected into AWS. But the key takeaway here is when you're connected to that cloud WAN, again, using a direct connect, ideal for your use cases, it would be a direct connect here at one of our POPs. You're connected to the AWS global backbone, and you can then route into those resources in the top of this graphic, those Amazon VPCs. And a VPC, without getting too deep in kind of the networking weeds that are AWS specific, stands for virtual private cloud. So it's your own IP space and that you define and control. IPv6 support as well, if you have those requirements. If you launch a virtual machine, a guest operating system, that will launch in a subnet in a VPC, and you can have internet connectivity in and out of that VPC, or you can completely lock it down with no internet connectivity and only have private connectivity back to your private network that has either a VPN or that direct connect to connect into that VPC. You can then also connect VPCs with each other within the same region or cross region if that's a requirement for the workload that you're trying to architect and develop. But the unique thing here is, for example, using this graphic, clients in North America on the left, again, end users connected up, or clients coming from a facility in North America via DX, that's the abbreviation for Direct Connect on this slide. They can connect into that cloud WAN, and without going back and hitting assets in the VPC, which would be in one of the AWS regions, they can ride our cloud WAN and get to another node on that network. So for example, if you have a mission in Australia, you can peer with the POP in Australia and connect to a mission in Spain and use AWS assuming those missions are also using AWS, you're going to want that peering anyway. And since that exists, you can now connect those two sites if you have those requirements. Hopefully that makes sense. Next slide, please. So this works great when you can bring your data to the cloud. If you don't have that option, or how can we support you in that case? If your requirements are such that you need to run DTN nodes co-located with your ground station receivers, but you want to take advantage of cloud capabilities that AWS offers, and that's one of the key things with AWS and with the cloud in general is the ability to do infrastructure as code, the ability to manage your infrastructure like source code for a project, the visibility, the instrumentation, the monitoring that you have. We support all of that in the cloud with our API. And so the demo we saw earlier, that was launched through the console, through the web console with a few clicks, and you can launch that. That could also have been done, or demos like that could be done where you have a template, a JSON file or a YAML file with a couple of dozen lines and one or two clicks, and that entire environment is deployed in the cloud. So you get management, you get automation, you get standardization and version control for your infrastructure as native cloud capabilities. If you want to do that same type of thing at your location where your ground stations are, we have a relatively newer option where we can extend the cloud into your facilities, either your campus here at Goddard or distant locations where you may actually have satellite receivers. And so that's a capability that we call Outpost. And so if I can go to the next slide, please. So Outpost, here's a great picture of an Outpost. It's a rack of hardware. It comes in a couple of different flavors. This is the full Outpost size, but really what this is an extension of AWS that you can run on premises. And in the case of NASA and space missions with DTN requirements, that on premises could be really anywhere in the world where you have the proper connectivity and power, and where you need to run that outpost equipment to support your mission. It's not just a normal rack of hardware that you would get from any hardware vendor. This is managed by AWS. It connects back to AWS. And when you go to launch your virtual machine, just like he launched a virtual machine in a particular region, you can launch that virtual machine on your outpost, and it would run co-located in hardware that's in the same facility where your receiver is. And then you can then connect that, that would then sync up and connect back with the rest of your environment and assets that might be running on AWS. It's a subset of the cloud. Not all of our 200 services are available on Outpost, but the types of services that you would need to effectively operate a network of virtual DTN nodes on AWS would run on these Outpost devices. So next slide, please. So it comes in different flavors. If you don't need a full rack, if your compute requirements aren't such, we've got smaller units. And the other nice thing is since this is the cloud on hardware in your facility, your DTN requirements may be a small slice of what this hardware is able to produce or provide. So you could have other NASA mission requirements on that same type of hardware managed and controlled and connected with and to AWS. So that's something to think about. It doesn't have to be just dedicated hardware for a single mission purpose. Your requirements could be a small slice, a couple of virtual machines, and your own VPC for your purposes on this hardware that's supporting a dozen other missions on hardware that might be running, an extension of the AWS cloud into your ground station facilities. You can certainly have more than one of these and manage as a single environment if you have larger facilities that have requirements of that scale. So next slide, please. And so this is just a representation of some of the different services that would be available on Outpost to support this. The big service, and these are Amazon product names. So Amazon EC2 is our elastic compute cloud. That's virtual machines on AWS. EBS is our elastic block storage. So that's the disk that you attach to your virtual machine to run your compute. S3 is object storage, and a number of other, database and some other services that may be part of either a solution to support DTN requirements or a solution that another NASA mission may have that's economizing and leveraging some of that same hardware that you procured and deployed to your edge. So next slide, please. So yeah, kind of my last slide. This is a bit of an animation, my only animation build slide in this, and it's back to our global network. So really what I wanted to kind of show is paint a picture to help tell a story about how that would look on AWS. So we do not make the VTN virtual node software at Amazon. We provide the cloud platform where other partners like Spatiam that we saw could come in and deploy that and run that on AWS's network. And Outpost is a way to extend that AWS network to remote locations. So if I can get the first click at the bottom of our slide here, if I can get the first click on the slide, please. There we go. So what we have here is an oversized Outpost device connected up to, this is my very good PowerPoint skills here, an Outpost device connected to a receiver represented in Punta Arenas. And in this particular example, you would probably want to have redundant connectivity using the fiber that's in place. And so we'll represent that with a link to Santiago and a link to Buenos Aires, which would be our two closest POPs to Punta Arenas. So next click, please. And that fiber then puts you on the AWS network. At that point, you can reach back to the US East 1 region, or you can reach back to any other node that's connected to AWS's network. So if I can get the next click for us here, please. So the orange dot represents the DTN virtual node software. Next click. Which would be running on that box in Punta Arenas in this example. If I can get one click, please. And you could potentially, if you have a requirement for this, and if your network parameters are such, you could run DTN software at the AWS Brazil region in one of our facilities in the availability zones that we have available in Brazil. You could also, one more click, please, reach back and run that DTN software in the Virginia region, where you may have existing centers of gravity where NASA has large data collections, where the mission customers of this data may do some of their processing, or they may do it in another AWS region. If we can have another click here. So yeah, we build this out. So you could have the Alaska Space Facility have an outpost there connected to the POPs in it looks like Portland, or I'd have to look at the map to see where the closest POPs are to Alaska, but a fiber connection into one of the POPs, which then puts you on the AWS network. And these orange dots are a mix of representing DTN virtual nodes in AWS regions on an outpost at one of your sites, or potentially they could be on not outpost hardware, but on regular hardware at one of your locations that has those connectivity requirements. And you can then use AWS's network to route that traffic. Because of our global footprint, hypothetically for the NISAR mission, if you need to run a DTN node in India, we could support that out of our region in India and connect that to where the other DTN nodes through the AWS backbone, and then of course reach that back to NASA and your other science consumers using that same network capability. And for the IT people to manage this infrastructure, the same template that you deploy to manage that VTN node in an AWS region anywhere in the world, you could deploy that on your outpost, and it's gonna make your IT portion of supporting this. It gives you the capability to have that highly standardized and repeatable from kind of a security and an audibility and a maintenance perspective. So, any questions? That's kind of where it's, again, representation of how you can use AWS capability to support your DTN requirements.
I had a question over
Yes.
here. This is Bill Polchik from GSC ISS. I noticed on your slide you talked about all the different regions, but it said except China. Does that mean it includes all the other countries except China, or is that something different?
So, yeah, that's a good question. So we do have regions in China, but they're in China, right? So the connectivity is so China is separate. So customers in China that do business in China can use AWS, but it's a separate environment than the rest of AWS.
Okay, thank you.
Yeah. Yeah, we don't have anything in Russia. So yeah. Now, I mean, certainly there would be telecom providers, and it's not on this map, but we've got public case studies here. If you're partnering with somebody in China or somebody in Russia, right? Then of course working through the network conditions in those countries. But those two may be bad examples. I don't know. But we've got examples, a published case study where the telecom in Thailand, well, we do not have a region in Thailand. We have one in Singapore, we have one in Indonesia, but we do not have one in Thailand. But the big telecom provider wanted to support AWS customers in country with data residency and sovereignty requirements. And so the telecom provider procured a number of these AWS outpost racks, and they're running mini AWS as an offering from the telecom company there in Thailand. So that's an example for countries that we do not have an established presence. Outposts can open that up for you. The other use case is not directly related to space requirements, but to give you an example, so Outpost is an offering that customers can run and run on their own premises for either, again, data sovereignty and residency in other countries is a big piece. If they have extremely low latency requirements, or if they just need to keep some stuff on premises, but they've standardized all of their IT on AWS, then Outpost becomes a great solution to support that. We also have an offering within AWS called local zones, which local zones are smaller than a region and smaller than an availability zone, but it's AWS managed infrastructure that customers access through their console, and it's in a facility that will be geographically closer to them for latency reasons. So our first local zone was in Los Angeles, and the primary use case there would be people working in the movie industry and the gaming industry doing high-end video, where they would be using virtual desktops to do hosted on AWS with high-end graphics on AWS, and they wanted to reduce the latency from their users doing that video and graphical work, and so we placed a local zone close to them for those types of requirements. We have a similar offering called Wavelength, which you can think of the same type of thing, where it's extending a slice of AWS, and we co-locate Wavelength with the telecom providers that run 5G networks. So people are running, developers are writing applications that have extremely low latency requirements. Then we eliminate the cloud portion of that latency by putting a Wavelength co-located with the telecom provider, so it's directly on their network. So those are like the types of use cases. But I think in the NASA use case, again, wherever you have a ground station facility, either NASA or commercial, and if you want to extend AWS into that, as well as use AWS as your global WAN provider, then that would be a fairly simple use case and a fairly simple requirement to meet. We also have our own ground station services that were AWS for low and medium orbit satellites. We have our own ground station offerings co-located with our regions. Not every region, but the key regions that you would potentially, if you look at the map, Cape Town, Sweden, we have one in Stockholm. We also have an AWS ground station in Punta Arenas and one in Hawaii where we don't have regions. So the one advantage of using AWS ground station and how this would work, using that with a virtual DTN on AWS concept, is the satellite receiver is at the same facility as your computer running that, or your host running that virtual DTN software. So we eliminate that latency from the satellite receiver to that first node on your ground-based DTN network. And that's how ground station would work. It's a managed service where you use our receiver, and then it pumps into that VPC environment I defined earlier, that virtual private cloud, where you can run your own software to consume that communication and then send it downstream further. So thank you. Any other questions? Yes, sir.
Thank you, Kyle, for the presentation. My question is around any plans for edge computing in space in LEO?
Any plans for edge computing in space? Well, we have a snow cone on the International Space Station, so that's there. I mean, space is like the next frontier, right? So we definitely are making investments, and it's certainly a big area of interest for us. And you can see the patterns there with like what we have with snow cone already on the space station. That's a smaller device than the outposts, primarily used for data migration purposes. But our snow cone devices also have compute capability on that device, where you can launch, for example, depending on the RAM and CPU requirements of your DTN virtual node software, that could potentially launch on a snow cone and be on an orbiting spacecraft someplace. Yeah,
one of the reasons I'm asking is, one of the benefits of using AWS is that it basically opens, the imagination of builders, like, yep. Application builders. Right now, one of the challenges is that as soon as you go to space, there has to be some infrastructure where you can even to start testing. And yes, AWS ground station, like other providers, give you that ability. But the first thing they ask you is, okay, where is your satellite? So it's like a chicken and egg problem. If there is edge computing available for experimentation, that would help the builders to accelerate the process, because for applications and even for for their own hardware.
Yeah, that's a great question, and definitely a requirement that our planners are aware of. But I can't speak to any concrete plans today, other than to point what we already have as a path, and just our history of innovation in this area is kind of the best answer I can give at this point.
Okay, and you have one question online, Oscar Garcia.
This is Oscar Garcia from the IPNSIG, and in my company we have been clients for 11 years from AWS, so I know more or less the system. In your list, I can see that you were missing DTN as a service, and from the IPNSIG, I could tell that we have been running DTN in cloud, and specifically we have some control servers running on the AWS network. So for controlling our DTN network, global DTN network, that is a more humble, but it's running DTN all day long in several nodes. So I was thinking that perhaps we could talk with you and with AWS on how to establish a collaboration in a way more or less permanently to keep up running this kind of applications like Spatiam, like you have seen medical record for space exploration that is also running on DTN, and that I know healthcare is one of the areas that you have been working as well. So well, I think it's very interesting, and I could also offer the knowledge that we have been gathering in the IPNSIG with related to the use of DTN in clouds and connecting all around the world. That's it.
Yeah, no, thank you. I think absolutely. We could certainly arrange a follow-up. But you hit on a key point, right? Like AWS is a platform that organizations, that end customers, as well as organizations that have a service provider type capability can build and innovate on and extend their reach to other customers in leveraging these types of services. Yeah, we don't have a first party DTN as a service, but we have a platform where a number of vendors can set up that capability and operate that and take advantage of our global network footprint, our regions, our availability zones within those regions, and the durability that gives you, and partners that would build something like that out can grow with their infrastructure as they grow with their business and their demand. So if the demand is relatively low in terms of usage, therefore CPU, therefore cost, you can have a smaller footprint in the cloud, and as requirements increase significantly, it's literally a button click, unless you write that into your code to auto scale, and then you don't even have to click the button, and it will scale up as your demands increase. So yeah, I think our contact information is part of this event. So if you want to follow up, I can connect you with some of our aerospace
I would
folks
appreciate
if
that
there's
for
interest.
sure. Because the IPNSIG also is thinking in the project working group in making experimentation with satellites. So ground station service, I think it's something we are going to be very important for us.
Oh, for sure. Yeah. And that will definitely, if you can somehow if we can get our info, I think I've got a ground station person that may be dialed in as well. Maybe in the chat in the meeting, we can exchange info, but yeah, we'll figure out a way to connect you with the right folks at AWS.
Yeah. Fantastic. Excellent.
Great. Anything else? Cool. Well, thank you very much for the time.
Okay, thank you. Thank you, Kyle Hart, for your presentation. Next, our next guests are 5G Open Innovation Lab. They're a group working to solve Comm and Nav's greatest challenges. We're joined today by Jim Brisimitzis, the founding partner, and Bill Wood, representing Menrad Networks, a company within the 5G Open Innovation Lab.
Good afternoon, everyone. Thank you very much for your time today. My name is Jim Brisimitzis. I'm the founder of the 5G Open Innovation Lab. And prior to starting the 5G Open Innovation Lab, I was a 14-year veteran at Microsoft. Kyle, please don't hold that against me. And I've seen various iterations of computing from my times as starting at Nortel Networks in Toronto, Canada, where I'm from, to client server at PeopleSoft and Oracle, to web, to now what we've just heard in the cloud. And what's really interesting about 5G is it's not yesterday's telecommunications platform. It's actually a pretty pervasive, containerized, modern platform that carriers such as Verizon, AT&T, or T-Mobile could really transform the value and services that they've delivered beyond dial tone. The problem was that they never really explored that. No one's really actively building a startup ecosystem or really a software ecosystem around that today. So as part of my talk today, I'd also wanted to introduce Bill Wood, who's on the chief side of Menrad Networks, and he'll talk through a little bit about what they're doing. And what Bill is going to really tease out is the types of innovation that is actually happening in this world, some of which Kyle talked about from an AWS perspective. And we wanted to give you that flavor. So next slide, if you please. Okay, so we're going to talk a little bit about the inflection of wireless and computing. I'm not here to bore you on it, but there's some really exciting stuff that we're seeing. We've now had 87 teams come through our program. They've raised over $1.3 billion in capital from venture. It's a real big opportunity. And the driving force behind that are entities like NASA and the enterprises. Combined, if you're not already familiar, the enterprises will spend about $3.4 trillion a year on IT and services, according to Gartner. That is 3 times larger than all the CSPs' revenue combined globally at 1.1 to 1.2 trillion. So there's a tremendous amount of upside and potential. And then I'll have Bill talk a little bit about what Menrad is doing. We are chit-chatting behind the scenes. I think there's a lot of perspective and insights that Bill will share with you relative to DTN as well. All right, so next slide, please. Now, if you go back to the early days of the Industrial Revolution, from Industry 1.0 or mechanization to electrification to where we're supposed to be with Industry 5.0 and where we are today with Industry 4.0, the dependency on technology has exponentially grown generation over generation over generation. And the share of wallet or the investments going into technology capabilities, whether it was mainframe back in the early days to where we are today in cloud, has also been growing exponentially as well. But here's the concerning piece. The cost of connectivity has been dropping in that same period. As we've been moving from generations of wireless standards from 1G to 2G to 3G to 4G and now 5G, the cost of connectivity has been plummeting, not increasing. What's more alarming in the 5G world, if you follow this world, the densification of the networks are going to demand more capital outlay, meaning if you want to truly provide millimeter wave connectivity, you're going to be building much denser networks. And as a result of that, capital invested in 5G networks is far greater than 4G is today. So we looked at that and said, well, that's really interesting. But as these networks are becoming more containerized and in many cases programmable, there's some really interesting innovation that can be built on these networks. Next slide, please. So when we when I started off the lab back in 2019, I took a page out of John Gage's playbook. This is the early days of Sun Microsystems. I believe he was employee number 20 or 21 at the time, where he coined the phrase, the network is the computer. In many ways, applications don't understand what boundaries are between where they are today in the cloud and where eventually they're going to be on the edge. And the edge is really the next major frontier of computing before we get to quantum. And so when I started looking at this, there are really no barriers to entry on this. We have set up a private 4G LTE-based network in our offices back in Seattle, Washington, less than 30 minutes. So the cost and the complexity of what it means to build cellular networks is plummeting as well. You might have heard of a phrase called private 5G. Many enterprises are exhausting the limitations of Wi-Fi as a wireless medium and exploring cellular networking. I was talking to one of our partners just last week. There's 12 major airports here in the United States. I won't name names, but they're fighting as hard as they possibly can to have zero dependencies on any of the telecommunication providers for providing and building private cellular networks. Why? That old adage that we used to say, no one wants to work with a telephone company, maybe that's coming to roost. And so today, if I'm an enterprise and I want to build up my own private 5G network with a few $1,000s and some licensed spectrum, you're in business. It's that simple. One of our teams called FreedomFi that was acquired by Nova Labs 2 weeks ago for less than $300 on an Intel-based PC and a $3,000 radio from a buy-sell or whatever the RAN choice was, you're up and running. In fact, 200 national parks actually have Freedom Fi infrastructure connecting parkgoers. So this barrier to entry for the industry has dropped quite significantly. The landscapes are evolving as well. I've talked exhaustively about private 5G. We're pretty excited about where that's going. We're unlocking private 5G as not just a connectivity solution, but we're unlocking it as an edge computing solution as well, because behind these private networks are typical enterprise computing needs. Back in the day at Microsoft, we used to call that branch computing. So what is private 5G? It's just better wireless. It's a step up from Wi-Fi 6, Wi-Fi 7, future generations into bigger spectrum, bigger capabilities, more security. But behind that is all computing. We heard a lot about that earlier. The programmable networks piece is real. Bill's going to talk on a little bit about this, but there's a lot of self-healing capabilities being explored today with networks. So not only is it hard to set these up and orchestrate and run them, there are teams that are actually building capabilities where these networks will be self-healing itself. I firmly believe that the ubiquitous of cellular networks for the enterprise in the next 10 years will be in place. There's a lot of investment in that. I see the edge as a big enabler. We all see very famous cars rolling around like Teslas that have autonomous capabilities. At some point, we might be like the Jetsons, where we hop into some sort of a droney thing that flies us to our destination. Those are all going to require compute. In many cases today, these devices have onboard compute. The average vehicle today will generate about 300 gigabytes of data a day. We talk to auto manufacturers that are trying to extract 300 gigabytes of data a day because they want to process that data for preventative maintenance and other needs. When we get to these use cases that really require data centers and data center access on the far, far edge, the telecommunication players are actually ideally suited in that, because in many cases, they have POPs that are thousands in any given country, plus fiber connectivity and such. So we see the edge as really synonymous with where connectivity is going, and many of the teams that we're working with are really building capabilities for that as well. What's alarming about 5G is when you get down to the specification levels, single poles can go from supporting 100,000 concurrent connections to 1 million plus concurrent connections. But when you get to such density of devices, your threat vectors for security rapidly expands. And so the security paradigms that enterprises have been accustomed to, when we get to the billions of devices globally, those paradigms not go out the window, but they change so significantly. We have to think about cyber, we have to think about zero trust, we have to think about all these things very differently when you get to that scale. And so security is actually a very big world for us too. We have a number of teams that have been exploring that. And then last but not least, and I'd like to acknowledge Kyle touched on this earlier, these are platforms. And so there are use cases that we're aware of today, and then there's certainly going to be a set of use cases that we're not so familiar with in the future. And the whole goal with the lab was to really create an environment where we're inviting those innovators and the platforms together to explore what those use cases are. Next slide, please. Since we've launched, we've had 87 teams come through the program. Just on Monday, we launched our 6th batch of 16 teams. These are teams that are across the United States, across Europe, across Asia. I think we've had our first team now in South America. It's a completely virtual program. So we work with these teams on virtual bases. We now are up to 17 corporate and founding partners that support the lab. They lend their support by way of technology, platform access, go-to-market support, and others. Last thing I want to say is that these teams are really they span the scale of teams that are both early stage to teams that are much, much later stage. When I was at Microsoft, I had many hats, one of which was launching their venture program. The other was launching the Microsoft for Startups program. These are not early stage teams. These are teams that are really, truly from the range of seed stage to, we have a couple of teams that have raised north of $110 million. We're not here to accelerate teams. We're really here to give them a platform to bring their capabilities and to explore those capabilities in the context of 5G and Edge. So we're pretty excited about the program. This current batch of 16 teams has some really exciting technologies that we're just getting our hands deep into with our partners. And so with that, I think the next slide will introduce Bill, please. Yeah, perfect. So when I got asked to come and speak, I could speak about this all day long, but I figured the best way to kind of share with you and impress upon you that there's so much opportunity out in networking and computing, and as those two fuse together, was to actually bring one of our teams that is much more senior, that's actually doing that as we speak, and very appropriate actually for this audience as well. So I'd like to introduce Bill. Thank you, Bill.
Thanks, Jim. Hello, everyone. Good afternoon. Pleased to be here. It's kind of an old stomping ground of mine. By way of introduction, I spent more years than I care to admit doing, Department of Defense and other kinds of military applications going back into the 80s with the old Audited days and dealing with a lot of the satellite and communications infrastructure dating back then. And since then, I spent a number of years working in the battle space, looking on the land war net architecture and dealing a lot with the ISR community and the battle command community. So I spent a lot of time out at Fort Huachuca working with all the military intelligence folks, as well as doing other travels, dealing with other kinds of scenarios on the battlefield. So as we move forward with the conversation, I'll be drawing upon lots of years of history of dealing with mission critical IoT and data applications, as well as how all that rolls up and actually gets used by people, analysts, and so on to do intentions and get other kind of inferences and act on that data. The next slide, please. So Mangata, we're early stage. We've got our A round done. We're working on our B round now. We're actually a satellite company. We're building satellites. So the founders of the company are extremely accomplished builders of satellites. They come from O3B and OneWeb. And so they have a lot of satellites up in the air running right now. And we're actually building HEO and MEO satellites. So we're working on our constellation now to get deployed in that space. And so there's a lot of capabilities they're building into those new satellites based on what they've learned over the years and so on. So, not only are we going to be talking about terrestrial type things, but in a non-terrestrial space as well. So, when we talk about DTN and what's going on there, I'll try to highlight the non-terrestrial part as far as what we're doing relative to edge computing. But the company itself also has a kind of a social justice aspect to it. If you look at this chart here, the digital divide, you'll notice that there's many parts of the world that don't have a lot of communication capabilities right now from a connectivity and access perspective. So, one of the things that we're trying to accomplish as a company is to help kind of close the gap and get more availability of resources and bandwidth and access to different parts of the globe via our network. Now, the one thing that stands out as well is when we start talking about the non-terrestrial versus terrestrial as far as how our network is going to get deployed and where we're going to be dropping terminals and ground stations and so on. One thing that's important is that many parts of the world aren't going to get fibered. So there's a lot of need out there for some of these non-terrestrial solutions in order to get that capability out there, especially in economically challenged areas like Africa, South America, and so on. So those are important drivers for us as a business, is to help enable that as well. So next slide, please. There's a lot going on right now from the pandemic perspective and so on. Anyone that's been kind of following the news, the supply chain has been a nightmare. There's a lot of different issues disrupting what's going on in the economy. A lot of businesses are trying to digitally transform, but they're running into issues for a variety of reasons. One, it may be dealing with labor shortages, skills shortages, know-how, how to actually go about doing it, make it happen as well. But, there's a lot of pain points being experienced by a lot of businesses as well as a part of this endeavor. Everyone's seen in the UK all kinds of shortages of goods. There's ships sitting out in sea in lots of different places and so on. So there's a lot of things going on as far as the ripple effect from various supply chains that are going on that are driving a lot of impact. So a lot of the discussion around edge and so on is how to get that data sooner, to get it into the intelligence pipeline so people can act on it sooner. And then how do systems, from a system of systems perspective, take advantage of that data, leverage it, and work with it as well. So that's one of the things that's important as a part of this as we move forward, is getting the information is in one thing. We'll talk about the kind of the data triangle. Having a lot of data is one thing. Getting it to information, getting it to knowledge, getting it to wisdom that you can act on it and actually get some benefit out of it is another. And that's the part where how we kind of mature and evolve and process that data and generate insights. So next slide, please. So the resulting challenges from a technology perspective, many of the use cases that were brought up earlier also apply to what we're dealing with in our business as well from a commercial perspective. So for instance, Can't activate talent in the digital desert, and there's limited technology infrastructure, data privacy, sovereignty, all that. But there's also the use cases that were mentioned around crew satisfaction or crew health. There's also things around remote telehealth, telemedicine. There's even other things like the maritime industry dealing with remote maintenance. When I'm using AR, VR, or other kinds of things to get skilled people to help repair things from remote, so on. So there's use cases like that. Remote diagnostics is another one, whether it's health-related diagnostics or even predictive maintenance on equipment and so on. So there's a lot of the use cases that we might be looking at from like our business perspective. The use cases convey into the lunar mission as well. So, for instance, maritime, oil and gas, or even mining. Similar scenario. You have people living remotely that are just taken away from their family, living as part of a crew scenario. There's business systems that also have to operate. There's equipment that has a lot of telemetry and other kinds of data that has to come from it, and so on. So it's not only how do you help keep the crew happy, healthy, the morale up from a social justice perspective, how do you get them to be able to phone home and talk to their families and so on. In some scenarios in the maritime space, crew members go days and weeks without actually talking to their families, even though they're on a ship with, potentially satellite downlink to those ships and so on. There's not a lot of bandwidth. So it's a bandwidth starved environment as well. In some cases, the ship getting 2 megabits down is a lot, and in often cases there's 512K and below. So, these are important scenarios around how do we help get that connectivity there? And then once it's there, how do you leverage it to help improve quality of life as well as manage the risk, as well as enable the business systems? So next slide, please. There's a number of requirements that come out of this space as far as how to get the technologies to help drive this change. So as we go through the list, you can see it's around how it embeds into the business, how easy it is to integrate, how do we maintain the cost and keep the cost affordable, and so on is an enabler. But then also, how do you use AI in a way to help weed through the chaff, get what's important, act on it, and then kind of triage the data and move it along. So in the DTN space, we've heard lots of conversations around shuttling data around, but I'm more interested in the context of the data, the timeliness of the data. How long does it have to stay before it's no longer relevant and we can flush it because it's just no longer valuable, and so on. So just because it's sitting in the node somewhere and hasn't been moved, it's aging and decaying at a very, very, very quick rate in different use cases. So how do you have the intelligence in the middle to filter that out and dump it instead of wasting time sending it when it's not needed anymore? So there's business rules and other kinds of things, whether it's infrastructure as code, policy as code, whatever kind of cloud conversation or kind of cloud semantic you want to apply to it. It's very important because you might be moving data around that's just not relevant to anyone anymore. Or when it gets to a place and it gets processed, it might actually skew the models as opposed to help them. So something to discuss. And then also, when you look at, the observability is an important one too. So when we look at DTN, and when we start talking about edge and working with non-terrestrial solutions that are communicating via satellites and so on, observability is important. So, going back to the quality of service discussion earlier, how do I prioritize what is command and control data versus just data that shows up? Whether it's just opportunistic from a FIFO perspective, or is there some kind of layer 3 or 4 switching going on where the routing is more intelligent based on the priority of what has to get sent? Or are you doing command, the classic command data from a CUPS architecture perspective in the telco space? Do I have my control plane, my data plane, and my observability plane, and so on, as far as how I prioritize moving the traffic? And then lastly, dealing with ingestion of the data. You heard mention of the 5G, and I'm going to talk to it from this perspective, from an IoT perspective. When you ingest all that data from all these IoT devices, I have a slide here in a few minutes that goes into the data problem from an enterprise data management perspective for a lot of organizations. There's a ton of it coming in. How much of it's really useful versus just noise? And so when you're ingesting, in some of these distant nodes, literally gigabytes and terabytes of data, but only megabytes or potentially gigabytes is actually even relevant. How do you flush it, triage it, and kind of sort through it and figure out what you actually want to pass along versus just passing it all along? So there's a sense that, when you go back up to the first line on the intelligence stuff, it really is important to be able to figure out and prioritize that and make some decisions on it before we kind of introduce it into the DTN network for movement. Because once you submit it into the DTN movement, it's there, it's locked in, it's going to get guaranteed delivered and so on. So the big question is making sure from an applications perspective, it should be in there in the first place. So, and I don't know if it sounds as though you had conversations yesterday where you walked through some of the applications. Sorry, I wasn't here for that. I would have loved to listen. But next slide, please. So from a topology perspective or a quick, we have a bunch of different form factors we're looking at from a cloud and edge perspective. We have different, form factors and capacities based on the role that this equipment plays in our topology. The one thing I'll note, and they're really small numbers, but even in the smallest footprint, we can put a boatload of capacity out there. And the challenge now in today's equipment is that, literally being able to put several hundred cores, several hundred terabytes out with just 10 or 12 U of rack space is phenomenal. That's a lot of horsepower though. So what do you do with it? How do you keep it busy and so on? Part of the challenge that we're running into is that many of the ISVs and many of the application architectures that are deployed out into the world are still client server based. If I had a node out there that was intelligent that they could get insight from, or I could throw notifications to them, they couldn't act on it because their applications aren't designed to actually accept and respond and kind of propagate those events. So there's a bigger challenge in the portfolio in the application realm around how do the application portfolios evolve to take advantage of the ability to have insights thrown to them and drive dynamic workflows and dynamic decisioning and so on. So next slide, please. So topology-wise, this is kind of like our, call it theater of operations, but essentially this is one big cloud operating model. So we're going to have, a sense, everything from the far edge where we have, either, a very, very small footprint based on whether it's on a ship or, some other mobility-based, transportation thing, or we're going to have a little bit larger nodes, a little bit more capacity and so on. The bottom line is that we're going to have the ability to move data around both in a non-terrestrial and terrestrial way that will drive, from an enterprise perspective, lots of insight and lots of data creation and event creation, as well as, more importantly, how do we enable all of the 5G capabilities, whether it's from a SaaS platform, like a software as a service, as well as what other capabilities can we put out close to the user, whether it's content distribution, whether it's OTT type stuff from, working on second screen and other kind of experiences. The one thing that Jim mentioned, which is really important, is that with the advent of 5G, I designed smart cities and smart stadiums and other kinds of stuff. Instead of 60 to 70 milliseconds of latency dealing with Wi-Fi, we're talking 10 milliseconds with 5G. So that extra 40, 50 milliseconds of time is a lot of computing you can do at the edge. So you can actually change and alter business workers' experiences, end users' experiences, machine-to-machine interactions and so forth very significantly in that time. So when we talk about it now, when we provision these edge nodes closer to the workers, the ability of the businesses to transform what they do and how they do it is significantly impacted from not only a workflow perspective, but the world of the possible becomes significantly enhanced. In fact, I've sat with a lot of customers when we started whiteboarding and we start talking about, if you didn't have bandwidth as a problem and or you had the ability to do X, Y, and Z, what would that mean to your business? And many folks are they have a hard time getting past the fact that they're used to being smacked in the face with a bandwidth limitation of X or Y or Z. So the world of the possible is a really hard conversation for them. So it's really like an ideation / consultative type conversation around, what would it mean to you to transform how you do this? What business process would change here? How would this business worker do this differently? What process could you do now that you couldn't do before? And so on. So the dynamics change a lot on the business space. Same thing, when you start looking like in the military, the ConOps and the doctrine changes phenomenally and so on. I remember, dealing with Even like brigades on the move versus, when they stop and so on. Everything that, the different leaders in the brigade would do is totally different now because they had this kind of capability versus having none of it before. So I think that kind of, in a sense, the rhetorical question is, what could you do differently if you had this kind of horsepower that close? So proximity matters, and then also, it's a little bit different from a DTN because it's really around, I'm backhauling a bunch of stuff for core processing versus what do I do here and now close to someone? And then what do I backhaul? Like in this architecture here, we can actually backhaul data to different places to stage it to do different levels of aggregation and analysis. We don't have to haul it all the way back to the core to do heavy lifting. We can do incremental and move pieces of it over time. So the value in that is that, by the time I get it to the core, it's only what I really need, and it's already been pre-processed quite a bit. So it's additive to what I've got to do, as opposed to distracting indoor noise. So I'm not paying a bunch of money to store a bunch of data that's not relevant, because we'll have another slide here in a second where data sprawl, has been a huge problem for many enterprises. There's so much data they don't know what to do with it. They're just lost. There is no master data management in anything they do. So it's just overwhelming. So the fact that you're slamming all this additional IoT and other data on top of it is just further exacerbating the level of being overwhelmed. So now the one thing with this too is that we have some instances where some of our nodes may be terrestrially backed as well. So we have routing options. So now we're talking about, do we route this way? Do we route that way? What's the most effective way to move this data based on its TTL, its priority, its value to the organization? So I can move all the really important stuff a certain way, and I can make the other stuff show up when it has to, just as long as it gets there. So now I have choices how I backhaul the data as opposed to just having one mechanism, which is important because not all data is the same. And then, you'll notice that we have places where we can pull it into a POP and we can go into the public cloud and so on. The big thing is that what tier of the architecture is going on? What insight do I need to act on at that tier? How quickly can I turn that around and put something back to my end user, help inform something that they're doing? How can I change a process, help inform, get an insight, and so on as a part of this process to add value at every point, as opposed to relying on getting it back to the core and then getting something back eventually later. So next slide, please. So this is kind of, I alluded to this earlier. This is kind of a classic problem with a lot of organizations. I've been doing multi-cloud and cloud strategy for Fortune 250s for a lot of years. And there isn't one I haven't run into yet that doesn't have a glut of just stuff that's accumulated over the years from just how they processed. They didn't do it on purpose, but they back into it. And so they've got enterprise legacy applications that do this. They've got tranches of data here that do that, and so on. So, many of them have 6, 7, 8 different, redundant sets of data that they just can't deconflict because it's too expensive and so on. And so especially when we start pulling data in from remote into this, how do we do that? So in a cloud native world, whether I was doing microservices or some other thing, right, there's a single source of truth that a cloud native / microservice application needs to draw from all the time as a way of being able to give a consistent answer. So there's different kinds of techniques for doing that. But the bottom line is that if this kind of data strategy isn't addressed as a part of how you architect this stuff, it's going to become even worse. So, that's just a cautionary tale, but it's also something that's important to make mind of when we have so much data that could come in through the edge. And through IoT, whether it's Wi-Fi based, whether it's, this LoRa stuff that was mentioned earlier, it doesn't really matter the mechanism for the data coming in. It's a matter of how do you sort it, sift it, pound through it. Because you notice in the challenges, there's so much data that, it's actually muddying the waters on the training of models. And so how do you really isolate what's valuable data? Because just because I have a boatload of data, sometimes too much data is a bad thing. You don't want to have, not enough is a problem, but too much garbage data is a problem too. So next slide, please. So in this representation, it's really around depicting the kind of data and the kind of processing you do on that data as a part of whether it's doing, am I doing deep learning on something, or am I doing just quick insights based on the transactionality of the data? And you'll see that it progresses through the architecture. But when I'm forward, like the near edge out, that's really like in the space where I'm influencing real-time decisions, real-time actions. So the kind of techniques I'm employing there are different than the deeper type analysis I'm doing at either like the gateway or, a regional data center and so on. And the reason why is that I'm doing more aggregation at the gateways and back, whereas when I'm at the near edge and out, I'm doing more sniffing of what's going on around me. And the example I use is that many years ago, whenever a brigade got onto an airplane to go deploy, we had to create what's a care package for it. So what that basically was here all of the signatures of all of the different things you're going to see when you get out there. So all of your SIGINT equipment, your ELINT stuff, and all of your different sensors can get their signatures ready. So when they land, they can go into the operating theater and be ready for battle. It was, basically called preparation of the battlefield. And the challenge now is that signature-based models don't work anymore because it's all around behavior. It's around, ML stuff. How am I doing caching? How am I doing cache coherency and all of that? So different regions are going to have different characteristics. So a model I trained back at the core, when I put it out to a different edge in a different part of the world, the behavior is going to be different. So, the purpose here is doing, I don't know if anyone's got a signal processing background, but the concept of a finite response filter versus an infinite response filter comes into play. So in an infinite response filter, my coefficients are evolving based on revising and updating the model as the data comes in. So I'm subclassing and sniffing the data as a way to update my algorithms to make sure that my ML model is evolving and that my AI endpoints are correct and they're evolving as well. Because I can so essentially it's like dealing with model drift. So doing machine learning on the edge tied to the business processes is important to address drift. So and so the coefficient drift is real important. Because if I don't do that, then I have to spend all of this data back and so on. And then I'm taking data from different regions and forecast, and so I'm still having issues aligning my model with what's going on regionally around the node, as opposed to what's going on, collectively, globally, where the behaviors might be different. So there's skewing going on as well. But the value of all of this, though, is understanding that there's different techniques I have to deploy at different places on the data as a part of my data triage. Now, Kyle mentioned earlier data sovereignty that's very important. So we're literally going to have hundreds and thousands of these micro data centers out there around the world. And so data sovereignty, data privacy are all extremely important. So in topology, when you send something over a country, that's one thing, but there's certain countries you can't send anything through. You have to route around them. So talked about intelligent routing. We have to have intelligent routing in order to move things between the nodes in our network to avoid crossing lines, to avoid sovereignty problems so that we don't have compliance and regulatory issues and so on. So there's very, very intense compliance things we have to go through to vet that we're doing this properly. But this is very real as well. So, you mentioned, I've heard a lot about supply chain issues and global supply chain and so on. This is very important, especially when you have a lot of these, non-terrestrial edge nodes out there coming back over these satellites. And so in our scenario, we're going to have a large volume of these non-terrestrial nodes out there tied to our with our antennas talking to our satellites. And so this is a big problem for us to address, but it's also something that helps us understand, when we'll be forcing and updating our software remotely over the satellites. So it's not like we're going to have a fiber line or whatever. So the remote management of these nodes is remarkably important. So it's not just sending back and forth data. It's also doing all the provisioning, all of the spinning up, and so forth. That's a part of managing these nodes, command and control, security, locking them down, doing behavioral analysis of all of the different attack vectors going against it in a cyber perspective and so on. So the data coming back is not just business app data from an IoT perspective. It's all of that observability data and everything else we have going on as it is a platform out in the world, presuming that every bad actor in the world is going to want to attack it. So there's a lot of things that we have to look for as a part of our data movement and so on. Next slide, please. So this is important kind of conversation here as far as, there's certain event process chain data that has a half-life, which is remarkably short. Going back earlier as far as, what data do we have to act on right away in order to make sure that the relevance of the data is appreciated and so on. So in this scenario, we're just kind of talking about, this is really around, mobility operations for different things, whether it's land-based, air-based, or on the water. But this is just an example where some information we get on these nodes expires extremely quickly. So if we can't get some insight from that, act on it or whatever, and get an answer back to someone within a certain amount of time, we miss an opportunity to avert a risk or avert a problem or exploit an issue or leverage an issue and so on. But at some point in time, the TTL on this data, the value of it starts to really, really decay really fast. So how do we take advantage of that as a part of what we're doing in these intelligent edges, as a part of, whether it's supporting digital transformation, supply chains, it's a whole myriad of different use cases. But the important thing is that for some use cases, timeliness matters, and so if I take the historical data and move that back to the core or move it to different staging points and so on, and then explore it further, that's fine. But in the meantime, I have to make something now in order to impact some other thing. Example, it's kind of like an over-the-top example, but it still makes sense. The minute that the ship going through the Suez Canal knew it was going to go ashore, everyone said, oh shit. But at the same time, how many other ships behind it now could have been notified that something was going amiss? And oh, by the way, all the people that had orders in the containers that were on those ships behind it, how many of them could have been notified to start making supply chain decisions to alter? Like if I had a company in Wichita, Kansas that was reliant on something on one of those containers on the ship behind the one going into the shore, how valuable would it have been for them to know that so they could start making alternate decisions instead of waiting weeks to find out what was going on and so on. So there's a immediacy from a ripple, that's an ideal world, but that's something that's going on real world in different ports around, what's in a container on a ship, getting off the ship, going into the port, getting on a truck, and the movement of all the things in the container is now becoming part of the reality through the edge world. Port command and control, understanding, I talked, next slide, please. So I'll use this as an example. So when you're dealing with different ints and different data coming in, so I'm using an old school representation of fusion. So if anyone that is familiar with like the intelligence world and so on, when you have a lot of different classes of sensors, you have different data coming in with different data types. So how do I take the different data from the different sensor types, synthesize it together to come up with singular views of an object, as opposed to having lots of alerts and events going on? And so the example would be someone cutting into a fence. I have video, I have sound, I have motion, and I may have other things going on as well from different sensors that are in the environment. It could be temperature, it could be body heat or whatever. So all of that, how do I deconflict that to one event, someone trying to cut into the fence, versus all of these separate events that could cause alarms? Same thing here is that, so there's a lot of things going on as far as how I'm getting insight out of the data, but I'm also then refreshing my intelligence, my caches, updating my inference engines, and so on as a part of how I deal with classifying and interpreting and leveraging the different kinds of data from the different kinds of sensors all coming in at the same time. And so this is, in the DTN world, this is all the payloads that goes on the packets that you're sending around, but this is the real-time info that needs, so there's delay in moving it through the DTN world. So some of this might be an application question too, as far as what applications are putting what data onto the DTN to move it around and why. And then, how do you then sniff those packets to see, there's a TTL on the packets in the DTN, but is there another dimension required from an importance or business value of that data beyond just the time to live? So maybe that somebody can help me understand that from a DTN perspective or not, if there's another dimension to it. But the important thing here is that, there's a lot going on the edge that requires some of this kind of insight and leveraging, I think, in the non-terrestrial world. So I have data that I'm processing, getting insight from, staging it. So, in our scenario, we have good connectivity, so we'll be able to move it. But even if that sits a little bit, I'm still able to operate and provide value to the business workers and the automation actors that are based off of that edge node. So I'm not sitting idle waiting for connectivity in order to provide value. I can still do stuff. So when I get the connectivity, I can move all the data that was pending into or so forth, you know. But then it goes back to the other point of, you know, how long is it atrophied? Is it, you know, if it sits out there for a day or two and it gets back to the core, how is it going to skew whatever models I was building in the back? So I have to build logic now into all of that to look at the timeliness of the data. So there's other things I have to do algorithmically in my model training efforts in order to identify and de-emphasize some of the data that's old or dated from a longitudinal perspective. But, you know, as you can see, the far edge and the near edge are kind of doing similar things, but the context is different. So there are different roles in the hierarchy or the architecture from a tiering perspective. So they're potentially doing different things on the data to get different insights. So, you know, I know this is kind of a busy chart, I apologize, but really the discussion to me was around, you know, in the IoT world, there's like 15 major kinds of sensors. So each of those major kinds of sensors is going to provide different kinds of data, and how we act on it and what we do with it, it's going to be slightly different, but it's all sometimes tied to the same events. And that's the part that's important, is how do I synthesize that? How do I use AI to do that? Because in the old school days, we would have a boatload of data go to the military intelligence analyst sitting in the tent, you know, sweating your butt off because it's really hot. And they would have to sit there and just manually connect all of these things together. And that's what they did all day long. Every day it was just this, you know. But in you know, right now with all, you know, like, and I'll pick on the MI folks, you know, in asymmetric warfare, there's so many different things going on in different places. There's like 2 people here, there's 3 people there. There's all of this stuff going on all around them in the battlefield. You know, even in Iraq and Afghanistan, there was all of these asynchronous events going on. And how do you make that manageable so people don't, you know, can understand what's going on and infer the intent and all of that? That's where some of the automation comes in, as well as the being able to do the synthesis and AI and so on. And then the ML part, you know, how are you doing ML cache flushing? How are you doing cache coherency and all of that? How are you dealing with events and so on? So it gets complicated, but these are patterns. As I mentioned earlier, the patterns around, you know, oil and gas versus mining versus maritime versus what's going on in the lunar. They're very similar in that respect. Some of the specifics of the business systems are different, but there's a lot of patterns there. So even though what we're doing in the commercial space looks kind of, it doesn't tie into this, it actually does, in my mind. I can see a lot of similarities. So I think that's where some of the use cases going on in industry may be able to help to accelerate you as far as some of those thoughts. But I believe I have one last slide. So for us, dealing with the digital divide is important. You know, being able to get capabilities out to extend access, provide capabilities to people, that's important. Providing innovation is important. You know, like in Africa, for instance, a lot of the telecom operators haven't really innovated because the ARPU there is so low that there's no money in it for them. So how do we help them create capabilities so they can, you know, so if I'm a business owner in Africa and I rely on my cell phone and my operator hasn't done anything to evolve their technologies, you know, how can we help there and so on? I mean, that's a kind of a simplistic view, but it's important. Same thing with South America and other. But, you know, automation and machine learning are essential. But the last point I really drive home too is, you know, the offensive cyber community is way ahead right now. So we have some catching up to do. So how we can mature, you know, cloud operations and cyber capabilities in remote environments is really important. You know, if we're going to put potentially hundreds of nodes out there, every single one of them is going to be attacked like ad nauseum. So we need to be able to defend that and then lock it down in a way that has some surety to it and provide quality of service while we're doing it. You know, some of these really advanced DDoS attacks and so on, there's routing table attacks, there's all kinds of different vectors that are going on, but that's incumbent upon us. But it's kind of a community issue too, because you're going to face it as much as we are. So I think, you know, how can we help each other get in front of this as well, I think is important, because at the end of the day, there's a handful of companies that are going out and doing this stuff at scale. You know, we're looking to be a market leader in this, so we're going to be aggressive after going at it and so on. But there's a lot of data that we can share just from what we learn when we're out there doing this, so that's the thing I'd like to extend the olive branch to is, how can we partner on working on making sure whatever we do out there in this environment, we can do securely, and at scale and provide excellent service to our customers. So, any questions or? Yes.
It's Philip Baldwin here. Yeah, no, I didn't catch the beginning, but definitely the end and definitely the part about the cyber taxes definitely resonates. That's for DTN, it's one of the biggest pushbacks we get. We're going to have all these nodes, maybe have nodes in areas that aren't our adversaries or are not friendly to us. And so how do we handle that? You want edge computing, is that an entry point into shutting down your entire network? And things like that. That's what we have to collaborate on, work with industry, work with all others on our designs and our resiliency, because it's going to be important to move this forward and make it widely adopted as something that we're going to do in the future. That's just not full of holes, right? Because we're just, like you said, it's going to be attacked like crazy. We're going to know they're aware they're going to be attacked, and how we live through that? Unless we just want to live with constant, breaches.
Yeah, there's some things that we're looking at specifically. I won't get into a lot of detail because I don't want to bog down the conversation, but there's a lot of things we're looking at using AI as a way to kind of aggressively defend ourselves, to make sure. So, if we have excess capacity and so on some of these nodes, why not, in the old days, doing embedded systems, you do JTAG and look for, what part of my black box is going to, break so I can replace the parts or replace the box. Now, using the down cycles to actually start looking at behavioral modeling of all the interactions and so on is a way to start understanding the nature of the interactions to make sure, is this someone masking their behavior as a friendly or and so on. So you can start doing deeper learning around some of the touch points. So that's where observability becomes so important, not only at the edge, but if you can roll that back and look at it, more horizontally and look at like multi-regional attacks concurrently, because sometimes they're going to be very sophisticated what's going on. But even then, short of having ability to backhaul data, if we're in a degraded situation or there is some, delayed transmissions going on, I can still actively do some work in the construct of the node I'm at, with the horsepower I have and so on. But that's part of those are architectural things that we need to kind of bake in.
Thanks for the response. There are 2 questions online. We can start with Oscar Garcia.
Hello, this is Oscar Garcia from the IPNSIG PWG. Doctor, I see you're used to integrate different technologies for us to get products running on the ground for real for years. I've been doing more or less the same thing for 40 years. I agree with your point that it's very important that it's not only communications, but an excessive of data aggregation nowadays, that many of most of the data is not relevant in terms of to be transmitted or can be processed on the edge. I think that's something that we would like to keep following up with this kind of concepts, also from the IPNSIG and from my experience also in the healthcare area, because show also a process of decay of value of the data as time goes by. That is very relevant to what needs to be communicated, and DTN is a great solution for that as well.
Great, yes, absolutely, definitely makes sense.
Thanks, Oscar. So we have one more question from Thomas Marshall Eubanks.
Hi, good afternoon. A very, very good talk. I just really wanted to make the point that, as this is a NASA meeting, nature is a wily opponent too. And one of the things I see happening with the sort of Internet of Things type no deployment to the moon that we're working on is the ability to generate way more data than you just want to send down blindly. This sort of stuff will have to go on both for situational type awareness, i.e. who's doing what where, but also like what is nature doing? What is the moon doing? What are our sensors telling us? We can easily generate way more data than we can send down, so you have to put that closer to the edge too. So I think there's a lot of NASA should be paying attention to this in my opinion, because they're going to need it.
No, that makes immense sense. And I'll go back to my battlefield days with dealing with MASINT and other kinds of things. There was a lot going on, even with weather and terrain and so on. There was a lot of variables. Like there's things going on today. I'll use like smart islands as an example. There's a lot of things, drones flying around looking for, fires and looking for other kinds of things, trying to just pull in data so you can see what's going on just in the environment. But similar thing on the moon. The one thing where I mentioned a little about some of the ML at the edge, it's not just AI. The ML at the edge too is what features, what of the 50 columns of data I just collected really matters to creating a model that I can then do an inference engine from and so on. Us humans of those 50 columns might say, well, intuitively these 3 make sense plus these 5. But the computer may say, no, that's all that's all garbage. These 7 matter. The rest you can throw away. So a lot of it is understanding of all of the features that are collected, which ones really matter and which ones should get sent back versus which ones just noise. So I think we could condense the data significantly just by being more aware of that which the computers and the model generators think is relevant, as opposed to just catching it all because it's convenient or easy. So I think that's something to explore as well, as far as not only triage as far as like chunking the data down, but it's also being, a little bit, how I say it, you can tailor in some respects what you use. There's different techniques for leaving some things out and just pulling metadata back and so on. So I think you have to almost like be aggressively, discerning on what you leave on the floor and why, and practice it and learn in the lab and all that, because, there's just so much data that it's really important that, if you err on leaving too much on the floor, you can kind of get some of that back. But I think if you pull too much back, it could be a real problem as well. So I think that's kind of a trial and error thing. But I think that's something that's going to matter a lot, especially when you're dealing with, you have a lot of different applications queuing up data for these bursts as a part of the DTN transmissions in these bundles. So, it's almost like, the train build at eBay, getting a seat on the table or a seat in the train for a release was really important. Same thing with getting in the bundle to get into the DTN process to get bursted out. So there's a priority on that from a pecking order perspective. So I think there's a, in a sense, how you determine what gets into those bundles and how those get pulled together and so on is also kind of a, not Darwin type thing, but there's a lot of competition as far as what should be there and why, and as far as the metadata and so on. So I think if you do get connectivity, what gets sent why first and so on also matters. So I think variability in the bundling may help too, as far as, using some AI and all that to figure out what data and what bundles should get prioritized as well.
Okay, there we go. So I agree with what you say, because back in my day when I used to do data archives and try to do all this stuff, yeah, there's way more data than you could possibly look at. The issue though is as you start to apply an ML or an AI against it, all those data streams that you've collected randomly in a willy-nilly fashion, it turns out that there are underlying physics that you may get that if you were a little too clever in ditching your data, you wouldn't get that physics back. Right, and I'm thinking of solar weather, space weather type applications, because it turns out we did an experiment on AWS a couple of years ago where we brought in all the data that we could to the cloud, and then just in a stupid, simple-minded manner said, okay, look at things that are correlated in time on 150 different data streams. And we saw little solar storms that had never been seen before, for example, that are interacting with the upper, the magnetosphere. And at that point, you're going, ooh, what do I need to now understand to know? Because If I'm missing really obvious physics like that, which, supposedly we know how this stuff has been working for about 50 years, Van Allen, maybe 70 years, something like that, then the argument is almost the contrary of what you're saying, because there is so much data out there that we don't know how these complicated, complex, interconnected systems work, that if I do throw it away, I may actually lose some of the insight into how the physics works. So just a caveat.
Oh, no,
I don't disagree with you.
No, I totally understand your point. It's kind of like there was a presentation earlier, which I thought was excellent, where the professor was talking about the dimensionality of P, right? And so there is a trade space that says how much data, what bundles, and the kind of the trade space around what do I pull back and why? Because you absolutely agree, teasing out some of those insights requires just but where the bundles and the bandwidth to get all that back as a premium, right? That's kind of, yeah.
Totally agree. I mean, if ideally as an astronomer, right, I want every friggin' wavelength known to mankind so I can understand what's going on. Right. But at the same time, I understand the limitations of the technology can be only a finite number of things to look at.
The flip side though is that, as I mentioned earlier, so some of the two 1U nodes, a 2-node, they have 158 terabytes of storage, so you can store a bunch of it. But the problem is that when you're doing remote storage management and quota management, when you have literally hundreds of those micro data centers all over the place, it's such a fine-grained thing. It's hard to do operational management at its scale. Oh, yeah. So really it's around, so quota management, just because you can have, I mean, literally, if you put 4U out there, you could have 400 terabytes of addressable space, backed up, rated, the whole thing. That's so much, you'll never be able to pull all that back, and especially over DTN. So it's kind of like, you can store local a bunch. Now, if you have to, for your purposes or whatever, you could store it local and then pull it back if you want to do that analysis. Right. But what you shuttle back versus what you store local, kind of two different things.
Right. And so I guess the differentiation was the assumption that I made is there's stuff that is essential to know in near real time or real time, right? And then there's the curiosity-based science. That is, okay, let's take an infinite amount of science and fill up an infinite amount of disk space, and yay, somebody one of these centuries will look at it, right? And go, oh, we finally figured out how this piece of the physics works, right? Yeah. So I agree. I think we're in violent agreement, but I just wanted to put that caveat out there because we've actually run the experiment and went, oh, I didn't know that, which is both cool and actually kind of terrifying at the same time, right?
Well, yeah, I have to be super sensitive to our cloud operations team and our operations team, because if we had that many nodes out there with that much storage and having to dig it down, I mean, we'd have to have hundreds of people instead of tens. Yeah. It would be cost prohibitive. So.
Yep, that's why they're grad students.
Yep. So anyway, I mean, I know this hasn't been necessarily a deep protocol conversation, but I hope it's been, relevant as far as the apps and data side, as far as just us commercial folks are interested. No? Great. Thank you.
Okay, so we're going to take a break now for 15 minutes. If everyone can be back by 4:40. Thanks. Okay, welcome back, everyone. We're nearing the end of today's presentations. We are having our final presentation of the day, which is the Aerospace Corporation. We're joined by a few key leaders within their emerging technologies group, and they will be presenting virtually.
Again, I thank everybody for their time. I know this is the last presentation today, so I'm hopefully that you guys can just get through this and we'll be great. Okay, so my name is Eric Dela Cruz. I work at the Aerospace Corporation. Me and my colleagues, Ryan Williams and Peter Kim, will make some presentations as well. I just wanted to give a brief overview about our momentum at the Aerospace Corporation with DTN Ion and how we implementing the DTN Island and how to apply it to Near Space Network, to LunaNet, and as mentioned earlier in the presentation before for some terrestrial applications as well. So, hold on. We wanted to take a methodical approach in implementing a test bed. And in this DTN ion test bed, what our main focus was to have flexibility. We wanted to have the flexibility to be able to test different types of Linux environments, as well as different types of use cases. So that's definitely what we wanted to do. So we started at the very beginning using the SDK kit, where all the boxes were all on one box. They were all networked together. And then we moved from there to going to the virtual environment. Then we went to physical environment so that all our nodes became physical. And so at this point, we have in a test environment where we have 7 nodes. And we've broken up the nodes into 5 nodes were in the BP6 Bulger Protocol 6 protocol within 3.6.2. And then we separated 2 Bach test nodes where in the DTN IM 4.1.1 using Bundle Protocol 7. So we wanted to keep that type of flexibility. Within those test environments, we also wanted to have different flavors of Linux so we can make sure there's interoperability. We will use some flavors of CentOS 7, Ubuntu 16.04, and in our DTN Ion 4.1.1, we were using Ubuntu 20.04.
Hey, sir, excuse me.
Go ahead.
This is
Go ahead.
Scott.
Yep.
Do you intend to be still showing the title slide?
We can move to the next slide, but there's not many slides. Go ahead.
Okay, thank you.
Yep, no problem. Yeah, you guys were looking for much more animated slides. Nope, this is where we're at. Okay, thank you for the question, though. Okay, so another reason why we moved from the virtual nodes to physical nodes is we wanted to be able to introduce other types of interfaces. So right now in our test environment, we're using 1 gigabit copper. We can move over to 10 gigabit copper. We want to move over into the optical transceivers, and we want to have the flexibility to go even different type of maybe future or accommodate future types of modems or different type of transceivers into the point where we can maybe simulate free space optical as well. So we wanted to keep that type of flexibility. So with that physical flexibility, we ran a couple of tests. We did the basic the BP send file, sending traffic over, and then also doing the CFDP protocol. We were sending text files and image files, small images and large images, trying to see if we can break it or if we can do something to cause havoc. At the same time, we did some testing as well as introducing some disruptions. Not anything with the routing per se. We just wanted to make sure our basic testing was correct. We did look to move forward to the BP streaming, BSSSP. It's funny that Jay mentioned the blocks exceeding maximum limit. We definitely saw that. So that Jay Gao, when he mentioned that, I go, oh, that's what it was. So now we're looking forward to the new implementations of DTN Ion 4.12. We'll see where that goes. And at the same time, within our test environment, we have Wireshark on each one of the nodes so that we can track the traffic to make sure that the LTP is going through. We can see them, we can verify it, and at the same time, we see the source and destinations of where they want it to go. So in that effect, our main priority was to have a test bed that has the most amount of flexibility we can. Right now, they're in a serial where there's one after another. We look to put it into a star topology or a hub and spoke topology to get more flexibility and to do more verification or validation of testing of multiple different types of use cases. But that's the short story of our current momentum at the Aerospace Corporation for the DTN Ion efforts. That's all I have. So is there any questions so far? Okay.
Looks like we have one question.
Okay.
Yeah, this is Bill Polchuk from GSC ISS. You talked about your different nodes with the BPV6 and the BPV7. They are talking to each other, correct? With that,
correct.
Are they separate?
No, They are separate. So the one environment for BP6, there are 5 nodes, and then the other environment, which is just a pair of nodes, which are 4.11. So they're completely separate. Go ahead.
Okay, for those, what convergence layers are you using?
We're just using basic, the LTP, just basic.
Okay, between those 5 nodes, is that?
Yes, between the 5 nodes, correct. They're all in series. Yeah, go ahead. Thanks.
Oh, okay. Okay, thank you.
And looks like Oscar.
Yes, Oscar from the IPNSIG, from the PWG. We have a network running in different parts of the world with DTN, with Ion and micro DTN. If you would like, we can exchange and so you can connect your network with us as well, with our network.
That sounds interesting. Right now, our environment is basically an enclosed environment, so there's really no way for it out, but it does sound interesting. We'll definitely have that conversation.
Just for you to know.
Got it. Perfect. Thank you. And if that's it, then I want to turn it over to Ryan Williams. I think he's the next up as far as talking about some capabilities at the Aerospace Corporation.
Thank you, Eric, and good afternoon, everyone. My name is Ryan Williams. I'm with the Aerospace Network Systems Department, and today I'll be discussing our Space Network Analysis Testbed, also known as SNAT. So much of our department's recent space-based network modeling and sim work has been in the area of network proliferated low Earth orbit constellations. And I would say my team's recent analysis work leans more heavily on our simulation capabilities rather than, say, emulation. So in terms of our simulation capability, so I had mentioned we refer to it as SNAT, or Space Network Analysis Testbed. And we based it around a widely used commercial off-the-shelf tool, a discrete event simulator, that we've modified and developed software around to more effectively model the space-based or space-based network scenarios that could feature, say, multiple interconnected constellations or physical layer implementations. But I guess I'll get into our modifications shortly. The tool is capable of simulating various transport, networking, and MAC layer protocols, and also various physical layer effects, and the tool supports multiple types of propagation models. So it does basically a full stack simulation. It also has the ability to model different types of user applications and traffic. So we've done, say, constant bit rate traffic and also stochastic flows as well. And so I had mentioned that we had developed some custom features around this COTS tool, all of which are not available in the standard tool itself. So some of those features include the ability to more readily control directional antenna pointing, which is important when you're dealing with large space-based networks and you're needing to point your interfaces or point your antennas to forge connections with multiple neighbors over the course of an orbit. We've custom developed a mesh formation algorithm that where we try to find the optimal interconnection between neighboring space nodes. We've also developed an alternative routing scheme that leverages the peculiarities of a space environment to efficiently provide nodes with routing information. And I guess also we've developed a basic store and forward capability. So I guess the result of simulation is, of course, the data that we post-process to derive various network key performance parameters. And so using this tool, we're able to derive latency, throughput, jitter, bandwidth utilization, routing overhead and packet loss rate, hop count, etc. So those are all key parameters that when you're doing your analysis of network performance are all critical in the assessment. So part of this tool is also visualizing performance and what the network is doing. So part of this SNAP suite is we have a web-based visualization and plotting tool where you could see the position of space nodes overlaid on a globe in 3 dimensions or in 2 dimensions. And we also have the capability of showing paths through the network. And we also have I would say our post-processing capability that includes some fairly rich graphing features, as well as the ability to present data in CSV format, so it makes it easier to filter data and look for specific patterns in the data, and also troubleshoot. And I guess lastly, I wanted to mention some final points. At this point, we've used this SNAP tool in support of several Department of Defense customers, and also performance-wise, although it's variable and based on a number of and it's based on peculiarities in each simulation. We've seen results that are faster than real time in many of the scenarios that we've run. So our tool has matured quite well. I would say, in terms of further work, I would say that our tool needs probably more work in the visualization area, but it's seen vast improvements in recent months. And with that, are there any questions regarding the space analysis testbed?
There's one question in the room. Give me one moment.
Yeah, hi, it's Leigh Torgerson, JPL. My question is, since I haven't seen your email, well, your email address probably says the Aerospace Corporation. Where are you? Where is this test bed? Are you in Los Angeles where I can drive by and talk to you about it, or are you somewhere else?
Yes, we're based in El Segundo, California.
Okay, I know exactly where it is. We'll contact you later.
Okay, sounds great. Thank you.
Okay, there's one more question.
This is Jay from JPL. One question I have is for your simulation. Have you applied it for a delay tolerant network scenario? And also, I wonder if your route, since it's simulation, I assume it has a routing algorithm. Do you use CGR or something, some of the more prominent DTN focused routing algorithm out there? Thank you.
Yeah, that's a great question. So we have not leveraged this tool for DTN analysis as of yet, and it doesn't include contact graph routing at this point. Hopefully that answers your question.
Yes, it does. Thanks. Okay. Are there other presenters in your group, or were you the last presenter?
Yeah, so I'd like to hand it over to Dr. Peter Kim.
Okay, thank you. If Dr. Peter Kim is speaking, you may be muted. We still can't hear you here.
Yeah, I see him on the list. Like, I think you're correct. He's just looks like he's still on mute.
Could be a technical difficulty. Let me see if I can contact him.
Okay, thanks.
So yeah, he said he's talking. I let him know we can't hear him.
Okay, yeah, we still can't hear him.
Yeah, he's going to try to redial. We apologize.
Okay, perfect. Okay. Yeah, okay, so in the meantime, Philip Baldwin's going to come up and say some quick remarks.
Yeah, I was going to say some closing words now. That way, when we close, we can just run away, and so I'll buy us some time here. But it's been a great industry day, and I think this accomplished what we wanted to accomplish. We really wanted to hear from industry. We wanted to hear what's out there. Seeing that support outside of NASA is really critical for us. Seeing there's other applications. So when I have to go defend this and say, DTN's the way to go, we can use DTN, I don't have to point to myself and say, well, Philip, are you the only one doing this? Is it you who's pushing this? Like, no, it's a real thing. There's commercial industries doing this. There's other applications that we can use and leverage. That's the key part. Can we leverage something that's already being worked on in industry? I saw things about cave and climate and, even with the demonstration with the cell phone. There's things I can point to in industry and say, that's an existing product that's being worked. Let's use that. And so very helpful. That's what we wanted to see today. That's what we want to, there's pretty much the main goal of this industry day was to see that, have these presentations, and there's going to be more coordination in the future. So we're looking forward to that. We're going to right away start planning now our industry day number 2, or maybe it's a semi-annual. This morning I said an annual. Maybe it's maybe we just do them at every DTN face-to-face. So we'll be planning that. So please listen out. And if we need to extend, right? Because I know not everybody was able to have a presentation. If we need to do a day and a half, we can look into that as well. If we want to have more industry presentations, and if there's any feedback, and I actually we didn't put this in our email, but I'm sure Ali Hale, who's organizing this, may reach out to the industry to say, if there's things you want to see next time, if there's some feedback you have for us, you can email Ali Hale, I think you reached out, or to Wendy Evans here, who's hosting this. So let us know what you'd like to see next time. We'll work that in, and we can go from there. So definitely thank everybody for the great presentations, the great discussions and the questions, and looking forward to the next industry day that we have that I think will be very fruitful as we get Artemis 1 off the ground. and our lunar aspirations are fully realized in the next few years here. We want DTN to be a part of that. And so looking forward to the continued collaboration. So I'll check on the line again to see if we can do audio check. Is it working? I hear an echo, so almost.
Can you hear me? Ryan?
Yes, we can. Try one more time.
Can you hear me?
Yes, we can hear you. Perfect. Go for it. We can't hear you now, but we did.
Okay, can I start?
Can you hear me? I think we can hear you, but I'm guessing
some
you
reason
can't hear
I
me.
cannot hear their end, but
So you can start. Go for it. If you can see my thumbs up,
I prepared.
Go.
Okay, under DTN space networking capabilities, I'll talk about integrate modern connection network traffic to high fidelity physical domain matter, and also space architectures. So as Ryan said, aerospace is making a lot of effort on the space networking simulation and model sim here. And especially for the digital engineering, I'll talk about some background information here. Our customers are, interested in not just high-level requirements, architecture analysis, but what QoS metrics can be achieved for various data transport and services, and also how they can evolve or be refreshed over its life cycle. The other interest is that our customer is looking for how to adapt space network protocols for differentiated services and improve the QoS metrics, and how to deal with proliferated LEO, non-terrestrial 5G, and MEO, GEO, and beyond, cislunar connectivities. So our focusing area is that we are building, end-to-end integrated model sim of complex space networking scenarios in a digital environment, so that we can integrate MBSE with high fidelity domain models such as platform, propagation, comm, sensor payload with the network performance service metrics. The other area is that we are building a common framework for use across space CONOPS, such as airborne, LEO, MEO, GEO, HEO to cislunar and beyond, so that our capability can provide whole simulation environment for the networking model sim for any type of comm links, for example, RF, optical, 5G, and also we can extend this protocol stack to DTN. So one person asked this one. Yes, we are looking at CGR and DTN as a routing protocol. So we are extensively looking at DTN protocols for the space application. So we are looking at full protocol stack, also some of the light version of DTN for space application. That's we are doing it. So if I can talk a little bit more detail, then in terms of testbed, we are leveraging our SNAP tool, Space Network Analysis Testbed, with SDK toolset for high fidelity modeling, so that we are integrating network portion with SDK toolkit. That's the first piece. And then we are integrating those pieces with MBSE tool models. So we are using Cameo for the MBSE, and also interface with the model center for the general workflows, and then hook up with some other general programming and analysis tools. For example, Python, MATLAB, Excel file. Those are kind of an environment in the digital engineering world. So that we are targeting to support LEO, MEO, GEO, all cislunar domains. Also, we want to provide network performance, including all KPPs. So I think that's I covered. Sorry, I cannot hear any voice here. So that's the first piece. And then the second piece that I prepared is 5G for NTN. So these days, there is a growing interest in the integration of satellite components with the 5G technologies to improve, especially SATCOM capabilities. So Aerospace has been working on 4G and 5G activities, not only NTN. So, for example, we are researching on 5G architecture to apply to space applications, and also we already supporting some of the interference study for DoD and government. Recently, we did 5G space data transport study for DoD, and we are still supporting our customers in terms of spectrum sharing and some other area. So especially we are looking at some 5G waveforms to apply to space application. Also, we are doing some machine learning AI for 5G signal processing. So in terms of DTN, we have some capabilities here. For example, we have an in-house tool, SOAP. SOAP is Satellite Orbital Analysis Program. That in-house tool, we can provide 3D orbit visualization and analysis. And the second one is Aerospace member of ONF, that's Open Networking Foundation. So ONF can provide full portfolio of mobile broadband data center projects. So we are utilizing some ONF ongoing projects. For example, software-defined RAN and software-defined core. Those we are utilizing them. Also, we have MATLAB 5G license for NTN. Also, networking simulation tools to support some of features, especially 3GPP release 17 features. So those are our current capabilities. And also, lastly, our research topic regarding NTN is we are looking at some of NTN use case development because aerospace has expertise in the space area. So we try to develop a possible use case for the NTN, for the DoD and government. And we are working on NTN architecture trade study. So some potential area will be, we try to characterize some performance on propagation and Dopplers for LEO, MEO, GEO, and beyond that. Some of them is already in the 3GPP standard, but we can reassess that one realistically. And also we are looking at some of functions requirement in terms of practical implementation of spacecraft, user devices, and ground components based on our experience. And then also we are looking at using our new radio NTN end-to-end testbed. We try to get some performance on specific missions. I think I pretty much covered.
Okay, thanks, Dr. Kim. I'm not sure if you can hear us. If not, I will send it over in chat. Okay, so thanks, everyone. I would like to ask for a round of applause for all of the presenters. As our very first DTN Industry Day, I think it was a success. And as Philip already said, I hope we're able to do this again next year. One quick thing, I just wanted to thank both the Goddard and the SCAN team for helping put this together. We had to move it a couple of times, and I know that was difficult, so I just wanted to send out that appreciation. Okay, that's it. Have a good day.